R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Rohde & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rohde & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. Our platform is designed to support over 20 gigabits per second. Last but not least, the ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the internet, such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde & Schwarz has been synonymous with innovation and passion, quality and reliability. Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde & Schwarz SMW. For all your needs, the Rohde & Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde & Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 gigahertz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed, or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If two Rohde & Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, The SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rode and Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standard's requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rode and Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex standard compliant signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. Its macro recorder does the job for you. While you operate the instrument, the recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a second RF path or a second baseband. Add fading and MIMO capabilities to cover the requirements of advanced standards. Choose the wireless standards you need. Each standard can easily be activated by an option key. Finally, you might end up with an instrument capable of simulating multi-user PUCCH for LTE, or even generating LTE advanced scenarios with carrier aggregation and all MIMO configurations defined by the standard. The Rode and Schwarz SMW was designed to master wireless communications technology for a long time to come. Whatever goes up on your drawing board, the SMW will help make your visions come true, now and in the future.
Roder & Schwarz is the leading supplier of test and measurement equipment for the wireless communications industry and all industries leveraging wireless communications, such as the automotive industry, industries adopting the Internet of Things. We are driving the technology evolution by providing state-of-the-art test solutions for 5G industries and ecosystem. R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Roder & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Roder & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common Internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the Internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. Our platform is designed to support over 20 gigabits per second. Last but not least, the ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the Internet such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde & Schwarz has been synonymous with innovation and passion, quality and reliability. Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde & Schwarz SMW. For all your needs, the Rohde & Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde & Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 GHz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed, or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If 2 Rohde and Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, the SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rohde and Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standards requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rohde and Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex standard compliance signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. Its macro recorder does the job for you. While you operate the instrument, the recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a second RF path or a second baseband. Add fading and MIMO capabilities to cover the requirements of advanced standards. Choose the wireless standards you need. Each standard can easily be activated by an option key. Finally, you might end up with an instrument capable of simulating multi-user PUCCH for LTE, or even generating LTE advanced scenarios with carrier aggregation and all MIMO configurations defined by the standard. The Rohde & Schwarz SMW was designed to master wireless communications technology for a long time to come. Whatever goes up on your drawing board, the SMW will help make your visions come true, now and in the future.
Rohde & Schwarz is the leading supplier of test and measurement equipment for the wireless communications industry and all industries leveraging wireless communications, such as the automotive industry, industries adopting the Internet of Things. We are driving the technology evolution by providing state-of-the-art test solutions for 5G industries and ecosystem. R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Rohde & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rohde & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common Internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the Internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. our platform is designed to support over 20 gigabits per second. Last but not least, the ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the Internet, such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM Squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde & Schwarz has been synonymous with innovation and passion, quality and reliability, Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde & Schwarz SMW. For all your needs, the Rohde & Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde & Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 GHz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If two Rohde & Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, the SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rohde & Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standard's requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rohde & Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex, standard compliant signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. Its macro recorder does the job for you. While you operate the instrument, the recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a second RF path or a second baseband. Add fading and MIMO capabilities to cover the requirements of advanced standards. Choose the wireless standards you need. Each standard can easily be activated by an option key. Finally, you might end up with an instrument capable of simulating multi-user PUCCH for LTE, or even generating LTE advanced scenarios with carrier aggregation and all MIMO configurations defined by the standard. The Rohde & Schwarz SMW was designed to master wireless communications technology for a long time to come. Whatever goes up on your drawing board, the SMW will help make your visions come true, now and in the future.
Rohde & Schwarz is the leading supplier of test and measurement equipment for the wireless communications industry and all industries leveraging wireless communications, such as the automotive industry, industries adopting the Internet of Things. We are driving the technology evolution by providing state-of-the-art test solutions for 5G industries and ecosystem. R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Rohde & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rohde & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common Internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the Internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services.
안녕하십니까. 로데슈바르즈코리아에서 준비한 디지털 컨퍼런스에 오신 여러분들을 환영합니다. 네, 저는 로데슈바르즈코리아에서 근무하고 있는 최지홍이라고 합니다. 만나서 반갑습니다. 오늘 이 컨퍼런스로 저희가 준비한 내용이 순서가 참 지금 와서 생각을 해보면은 뭐 굉장히 여러 가지 과정을 거쳐왔던 것 같습니다. 뭐 주제도 주제고 또 저희 본사에서 강사로 활동을 지원을 해주신 그 저희 직원들도 그렇고 또 오늘 여기 이렇게 참석해주신 분들도 그렇고 정말 여러 가지 면에서 많은 경우의 수가 있었던 것 같습니다. 먼저 오늘 저희가 준비한 이 행사는 원래대로라면은 저희가 오프라인에서 여러분들을 직접 대면을 하고 여러분께 말씀드릴 수 있는 그런 부분이었던 것 같은데 여러분들 모두 마찬가지입니다만은 작년부터 지금 코로나 상황으로 인해서 이제 그렇게 할 수 있는 부분들이 모두 막혀버렸죠. 그래서 참 어떤 면으로는 참 안타까운 것 같기도 합니다. 또 하지만 반면에 또 이렇게 온라인으로 또 만나뵐 수 있는 길들이 있어가지고요. 그래서 또 어떤 장소에 또 시간에 구애받지 않고 또 여러분들이 이렇게 뵐 수 있게 된 부분은 또 반대로 또 참 괜찮은 부분인 것 같기도 해요. 그래서 저희 회사에 대해서 아마 여러분들 아시는 분들도 꽤 있으실 거라고 생각합니다만은 원래 저희가 1년에 한 번 내지 2번 정도는 저희 본사 기술팀 인원이라든지 이런 발표자들을 대동을 해서 지금처럼 이렇게 올데이로 진행을 하는 이런 이벤트들을 저희가 진행을 했었는데 이번에는 말씀드렸던 것처럼 이제 이런 상황으로 인해서 온라인으로 진행을 하게 되었습니다. 우선 오늘 지금 거의 제가 아까 듣기로는 한 170분, 180분 넘는 분들께서 현재 접속을 해주시는 걸로 보입니다. 그래서 아침부터 이렇게 여러분들 참석해 주신 분들께 대단히 감사드리고요. 오늘 진행될 내용에 대해서 간단하게 먼저 소개를 좀 해드리도록 하겠습니다. 저희가 지금 진행하고 있는 이런 컨퍼런스나 웨비나들은 아마 참석해 보신 분들은 거의 대부분 아실 것 같아요. 그래서 저희 본사에서 진행했던 어떤 녹화된 영상들을 기준으로 저희가 국문 자막을 포함을 해서 송출을 해드리는 방식을 취하고 있고요. 이번에도 사실 마찬가지입니다. 그래서 저희 로데슈바르즈코리아 직원들이 여러분들께 준비된 영상을 먼저 제공을 해드리고 그리고 세션의 끄트머리 부분에서 이제 중간중간에 질문해 주시거나 이제 의견 나눠주신 부분들을 저희가 또 답변을 드리거나 이제 추가 설명을 드릴 수 있는 이런 식으로 이제 진행을 하려고 합니다. 다만 먼저 조금 양해 말씀을 드려야 될 부분이 있을 것 같아요. 우선 먼저 말씀드려야 될 부분은 오늘 이미 시간표 다 보셨겠지만은 오늘 지금 시작한 내용이 지금 계획대로라면은 5시까지 이어질 예정입니다. 그래서 꽤 긴 시간이죠. 오프라인으로 여러분께서 한 자리에 모여서 같이 함께 해주신다면야 사실 그렇게 크게 어려움은 없을 수 있습니다만은 온라인 특성상 어쩌면은 좀 전체적으로 쭉 끝까지 들으시기가 쉽지 않은 경우도 있으실 것 같아요. 그래서 그 부분에 대해서는 좀 먼저 양해 말씀을 드려야 될 것 같고요. 두 번째는 저희가 먼저 말씀드려야 될 부분은 이제 진행을 쭉 들으시면은 보실 수 있으시겠습니다만은 저희 본사에서 보내온 발표 영상들이 조금 깁니다. 시간표를 이미 보셨겠습니다만은 제가 최대한 저희 본사 인원들한테 그 얘기는 전달을 했었어요. 이게 진행되는 내용에 대한 여러 가지 문의사항도 있으실 거고 또 궁금하신 점들이 있으실 거기 때문에 이런 부분들을 감안을 해서 시간을 좀 조절을 해달라고 요청을 했었는데 또 저희 또 본사 이 기술팀 이 설명해 주시는 분들께서 또 굉장히 열정이 넘치시더라고요. 그래서 굉장히 좀 시간이 타이트하게 좀 진행이 될 것 같습니다. 그래서 저희가 뭐 지금 이 자리에서 제가 말씀드릴 수 있는 부분은 그 여러분들께서 이제 편하게 이 채팅창을 통해서 지금도 뭐 그 바로 질문을 올려주시는 분들이 계시는데요. 이런 그 질문들을 편하게 올려주세요. 그래서 그 내용들을 올려주시면 저희가 모니터링을 하다가 내용에 대해서 저희가 그 세션 동영상이 끝나고 난 다음에 저희가 비록 시간이 그렇게 많지 않을 수 있습니다만은 최대한 저희가 답변을 드릴 수 있는 부분들을 답변을 드리는 식으로 그렇게 정리를 하고 다음 세션으로 이어서 진행하는 이런 방식으로 진행을 할 테니까요. 여러분들 그 궁금하신 부분이나 문의사항 있으신 부분들은 이제 편하게 올려주시면 되고요. 아마도 제 생각으로는 그 시간 관계상 올려주시는 문의사항이나 이런 내용들을 저희가 이 자리에서 다 답변 드리기는 쉽지 않을 것 같아요. 특히나 오늘 뭐 주제 보셨겠습니다만은 5G와 6G에 대한 내용들을 가지고 말씀을 드릴 겁니다. 그래서 뭐 규격에 관련된 이야기라든지 뭐 특히 5G나 6G에 대해서 뭐 최근의 동향 그리고 필요한 부분들 그리고 뭐 아시겠습니다만 저희는 계측기 업체이기 때문에 이제 이런 면에서 이제 추가되는 내용들을 말씀을 드릴 텐데요. 이런 부분들을 혹시라도 저희가 답변을 다 못 드리는 부분이 있다면 내용을 저희가 관련해서 쭉 취합을 해서 추후에 내용을 그 답변을 다 받으실 수 있도록 그렇게 모아서 진행을 하도록 하겠습니다. 네, 시간이 벌써 5분 조금 넘어가고 있네요. 지금부터는 그래서 첫 번째 세션 내용으로 먼저 말씀을 드리겠습니다. 발표를 맡아주신 분은 저희 본사의 라이너 스툴파우스라는 분이시고요. 기술 매니저로 활동을 하고 계신 분입니다. 그래서 지금부터 관련된 내용으로 세션 첫 번째 세션 그 발표 내용을 보시도록 하겠습니다.
Hello and welcome to our webinar today about 5G, the ongoing evolution. Release 15, beyond. My name is Rainer Stulfort and I'm working as a technology manager wireless with Rodeschwarz. So what are my plans for today? I'd like to delve with you into some topics. So release 16, starting with the non-public network, 5G broadcast, positioning aspects, unlicensed, integrated access ball, and the automotive, V2X. Release 17, non-terrestrial networks, industrial things, site link enhancements, reduced capability, and also some enhancements on positioning. And I'd like to conclude the session today with an outlook on what will be expected beyond. So quick outlook into release 18 and beyond. So I do apologize for all those topics I will not be able to mention, to talk about. There's much more than I can present due to lack of time. But I hope I can keep you entertained. So let's start. We see 5G is now. 5G is deployed. We have the first devices. And now in the next phase of 5G, we see some kind of vertical applications. So driven by the automotive sector, 5G automotive, and the other big sector is the industry, so industrial applications. But there's much more in release 16. So here like a summary of certain topics. If I try to classify them and cluster them, I would like to cluster some of the new items in release 16 as kind of release 15 enhancements. Like always, there's a certain established technology, and then in the next evolution, you go and make it better and enhance it. We also target at some operational enhancements. For example, two-step rush, so to reduce the call setup time. This is an example. But also, we focus on new applications, new use cases. I gave already 2 examples, the automotive, the industry. The other one will be positioning, that also offers new use cases, new business cases. In release 17, satellite, non-terrestrial networks. So this is where 5G is heading to. Let's have a closer look into the technology aspects. And I'll start with here with a photo of the Rodeschwarz factory, by the way, where we also have deployed our private 5G network. So there are now some new scenarios in a network deployment case. For example, on the left, we see these isolated, so non-public networks. So that could be that we have a campus network. A factory, for example, will set up its own private 5G. So then they're responsible for the infrastructure deployment, for the antenna, for the monitoring, the maintenance of the 5G network, etc. On the right side, another example is, let's say, using this concept of network slicing. So an operator provides 5G as a service Yeah, so 5G, let's say, as a use case, so I'm providing communication service. Let's say my 5G network will now be orchestrated by another company, let's say another tenant. And this is this concept also in 5G, that we have multi-tenant and also multiple orchestrators of the 5G network using this 5G orchestration. There are also some shared modes in between. Yeah, you'll see further details in the 5G ACAI. What is the important part, let's say, when we consider 5G in an industrial environment? And here there's one major aspect to mention. This is the timing. And the feature we introduce is this TSN, time-sensitive network. So, for example, here shown in this picture is an idea that I have an end-to-end, the two clouds, an end-to-end connection between two devices. And formerly this was done via a cable-based, via Ethernet. So then I have a kind of determined and predictable time how long it will take to send a message from A to B. And now we replace this cable connection with a 5G connection. So we have the 5G system in between. And the idea is that we have a deterministic delay. So it's not just the absolute delay when we focus on latency and round trip time. Here also what counts is the predetermined or deterministic kind of delay. And this is also, I gave an example on the upper part in the slide, is an example from the Ethernet. And here we call this isochronous Ethernet, so that we have fixed allocated time slots where a data packet can be sent for these time critical applications. And this is now also what 5G network provides. For example, that the network is aware of the quality of service profile, so that it is latency critical, that it is an isochronous deterministic data flow. So now the base station can react on this and knows it and schedules or reserves radio resources in its scheduling strategy to make sure the packets will be delivered in the right time. And we also have a kind of time labeling. So in the ingress of the 5G system, there's a kind of timestamp, a label, when the packet has been arrived. And at the egress of the 5G system, we also have a label, a timestamp, and then we can measure, let's say, exactly what is the time in 5G from ingress to egress. And if we know this time, then we can also do some compensation strategies. For example, timing advance, that the external source will deliver the packets before, for that we compensate this data flow propagation times through the 5G network. So just a few examples. Another topic in the 5G evolution is 5G broadcast. So where we see a trend, for example, using the existing frequency spectrum, using the existing infrastructure from broadcast, like here, a high tower, high power. And now you remember we have a feature in 5G that is called dual connectivity, or another feature, supplementary downlink. And now is the idea that beside or accompanying my 5G link, which I have here, uplink and downlink, and then on top of that, I can now apply a downlink only, and which is the content is broadcast or multicast. And that is a feature that was introduced in LTE already with further enhanced multimedia broadcast. And now in 5G, we are continuing and extending this service. For example, reducing the subcarrier spacing. There's one number which is defined, is 1.25 kilohertz subcarrier spacing, to allow a much wider coverage scenario. And in the next evolution, release 15, 16, 17, we also target a kind of update of the architecture in 5G. So there will be new functions available in the core network. And these functions, for example, allow to set off a virtual group, and then we can do data as a multicast. Yeah, so multicast, we can set up a virtual group of receivers. Yeah, so everybody who is interested in that, for example, and then we can deliver this information in a multicast and also in a broadcast. So it's not, let's say, one will try to replace the other. It's more like a convergence, that the traditional communication networks can outsource traffic, and advantage, they have a much wider coverage area. And from the broadcasters, they, for example, can combine their broadcast with the wireless connectivity, because then also we have a kind of feedback, an uplink. Yeah, we can introduce, let's say, some interactive television trends. Yeah, so that is one idea. then maybe probably you may say, oh, that looks like a déjà vu. Yeah, positioning. You're right. So it's not new in that way. So what is new? And probably those of you who have ever attended one of my training sessions and about 5G, and I'm known for this term, when I try to explain 5G in one single word, I would use this term flexibility. And here's another example of the tremendous flexibility in 5G. So when it is about positioning, so estimating my whereabouts, 5G offers various possibilities. There are positioning methods which are independent of our radio technologies. Satellite is a very known factor, GNSS for sure. Then we can use technologies like Bluetooth, Wi-Fi, near-field communication, UWB, etc. Also terrestrial beacon, and let's say an important also knowledge. For example, I know just recently from Europe, the European community, they launched a new mandate, the E112. So that means an emergency call, and then the mobile device has to deliver its position. And the position also in the vertical axis, so the Z-axis. So that requires now some positioning methods that also will be able to deliver the altitude information. And 5G, and I always made this statement, LTE is somehow part of 5G. Yeah, so we see it here in the positioning. So the 5G positioning supports the LTE-based radio technology positionings. Yeah, and also 5G introduces, let's say, some déjà vu, some known concepts, but in a more sophisticated and enhanced way. Just some examples. For example, 5G introduces the idea, I have to say it's not new, but 5G is now introducing the idea of measuring a time difference, TDOA, time difference of arrival. Here's just an example between 3 cells. So the UE is capable now to measure the time difference of the different downlink signals. Another methodology, for example, could be to measure the round trip time. Yeah? So that's what we know in the serving cell as a timing advance. Yeah? So the permanent control of the timing advance can also allow us to determine the distance. Yeah? But now in 5G, the advantage is that we do not only measure a round trip time in the connection to the serving cell, we are also able to measure a round trip time to neighbor cells. For example, the UE is commanded to send a sounding reference signals in uplink to a neighbor cell. The neighbor cell will now measure the time between reception of this SRS and transmission of a positioning reference signals. And the UE can measure now also the distance between its own transmission and the reception of the feedback. And last but not least, give you an idea, beamforming, it's a fantastic technology. Yeah? And now we can use with beamforming, if we know what beam is used to deliver the data and downlink, we have the angle of departure. Or if we use beamforming in the receive direction, then I can estimate the angle of arrival. Yeah? So what is then the impact? Just one example. In 5G Release 16, we introduce a new type of reference signals, the so-called positioning reference signals. Here, like an example, how they build pseudo-noise sequence, and we have a huge flexibility to map them on our, let's say, radio frequency resource plane. So here in the frequency domain, I have let's say, the distance between the subcarriers that contain such a PRS. Then we have in the time domain a kind of quantity, yeah, how often, how frequently, a kind of periodicity, and also the frequency, position, the distance. So very flexible, and also can be sent, let's say, indicated with positioning system information. Beside all the radio part, positioning is also have an impact into the protocol world, in the architecture. And here 5G offers in the core network a new function, this location management function, that is either capable to deliver assistant data, or it can do the position calculations, the computations. And as I said, 5G positioning supports LTE, supports satellite. And also we support protocol-wise this kind of user plane location, SUPL, so we can do positioning information at either assistance or computation results can be transferred over the application layer. And that's a funny abbreviation. In LTE, we introduced this protocol LPPP, so which stands for LTE Positioning Protocol. And now we keep the name, but we extend it also for 5G. Yeah, so now we can say we transfer 5G positioning information over the LTE positioning protocol. Okay, names are like that. So another part is in the hungriness for spectrum. yeah, we also target into the unlicensed spectrum, especially here the range is in the 6 gigahertz. So there's a unlicensed spectrum ISM band between 5.9 and 7.1 gigahertz. Of course, this also depends on some regulatory. Yeah, so for example, US and Europe, I also saw in Asia some trends where regulators will now open this frequency spectrum to be used by wireless, by 5G as well. One advantage compared to LTE unlicensed would be that 5G by default offers a much wider bandwidth, and 5G is more flexible in kind of deployment. So for example, here we see certain kind of unlicensed operations. That is, for example, 5G unlicensed combined with LTE licensed, or 5G unlicensed in dual connectivity with 5G licensed, etc., etc. And also interesting is here aspect C. That is a deployment of a standalone cell in 5G unlicensed spectrum. So also this is possible. Yeah? And still we want to behave as a good neighbor. So we have to pay attention that we do not collide and conflict with any other radio technology active. So therefore there's a listen before talk mechanism defined accompanying this unlicensed aspect in 5G. Infrastructure, integrated access backhaul. So like here shown some antennas. Yeah, and integrated access backhaul is a mechanism to allow a kind of faster deployment of additional cells. And here the cell, let's say, is kind of, yeah, for kind of simpler deployment, we are using now the radio as the backhaul connection. So we introduce a new term, and this is the so-called IAB node. So the IAB node is now, maybe you know this Roman god, this Janus, he has two heads, yeah, so two faces. And now this IAB node has one face, which is here the uplink, the blue color, to the donor cell, to the base station, to the cell. And this is like the 5G uplink. And in the opposite direction, which is the orange color, this is face to the user equipment. And here the IAB node behaves as a downlink. Yeah? So we can share the spectrum, and then we have these both directions. And the advantage would be that we can have a simpler and easier and faster deployment of new cells, for example, especially when you have to bridge some capacity issues, hotspot that is only temporary, etc. In addition to that, also 5G release 16 will contain couples of enhancements. I just mentioned it very briefly. Here, let's say an updated enhancement in the MIMO schemes. There will be, let's say, on the hunt, on the objective to achieve perfect knowledge of the channel status. Yeah, that is, let's say, the dream, the paradise we are looking at. I always say it like this with beamforming. So beamforming is a wonderful technology. And what is even better as beamforming is if you know where to beamform to. Yeah, so if I know exactly as a transmitter, what is my reflection situations, what is my distance, what is the direction, where is the receiver, etc., then I can adjust the beams in an optimized way. So now we work on sophisticated methodologies to provide a much better channel status information. For example, in time domain, to see about the multipath propagation reflection, to see about a wide bandwidth approach, etc. We do some kind of error compensation, PAPR. So it was figured out in release 15 that some of the demodulation reference signals, especially when you use this transition precoding, the single carrier FDMA DFT spread, then the DMRS will still have a high power. So we adjust this with a better peak to average power reduction. Beamforming is extended by various methodologies, for example, multiple beams operation. Yeah. So there's a better beam failure mechanism. And also if you consider with carrier aggregation that we can consider a kind of component carrier quasi-collocation. Yeah. So assumption is that we considered with safe signaling effort, and we consider the different component carriers to be quasi-collocated. So that means they have the same assumption in terms of channel conditions. And also this multi-TRP is in our target. So it's depicted here in this delineation in the figure. So that is an idea. Main focus is, for example, on indoor, on reliability, and also in enhanced mobile broadband, that we have multiple transmitters, here TRPs, who deliver the data to the receiver. Yeah? And if you do it in a time synchronized way, then you can also benefit from a kind of channel coherence. Just a very short example how to work on the operational enhancements, like here from a 4-step random access procedure, especially for load traffic, for small data packets only. It would be more beneficial to have a 2-step batch procedure, because then we can shorten the connection setup time. Or another example is due to the complexity of the UE capability. There's also now an idea, just a simple idea in that way, that we optimize the signaling in that way that we classify a kind of manufacturer type, this radio capability identity, which is then referring to a set of features, and then maybe, for example, okay, this manufacturer, it always supports this capability. So objective is to reduce the signaling overhead. Automotive. This is one big topic in 5G release 16. So we have the vehicle to network connection in the upper part of this slide. So here we have, of course, the evolution from LTE to 5G and also 5G release 16. All the advantages I presented, they can be used in the vehicle as well. I always like to say this joke that the next smartphone will be on wheels. So we see the automotive industry, let's say all these kind of modems, the entertainment devices, the navigation systems inside the vehicles, etc. So there are plenty of examples. You know them by yourself. On the lower part of the slide, we see here now the direct communication. It was first introduced in LTE for public safety. And then in release 14, the automotive started with the LTE side link, so to communicate from vehicle to vehicle, for example. But here the main objective has been safety. So safe operation on the road, so to reduce the number of injuries, etc., etc. And now we're going to extend this with release 15, higher data rates, introducing additional services, and with release 16 now we are introducing the 5G new radio interface into this direct communication mode, and this is either called PC5 interface when you talk about protocols, or this is called side link if we talk about the radio interface. So new services, new use cases, for example, could be, and for example, I know this one example only from James Bond movie. So James Bond is already ahead of us. So with a remote control, with his smartphone, he was controlling his car. Then we can introduce cooperative maneuvers, data offloading, sensor sharing, see-through, etc., etc. On the physical layer, I just have here a table summarized, let's say the different advantages. So, for example, 5G new radio V2X is first important is it is agnostic of the frequency band. For sure, first we always target at the ITS band at 5.9 gigahertz, but we are flexible. We can also cover any other frequency band if we want to. We have these flexible numerologies. We also introduce MIMO, and important is, for example, that we have a HARC process, HRQ, so get a reliable connection. And in terms of services, broadcast, unicast, multicast, I will introduce that. So summary on a high level, we have these 7 pillars in the 5G vehicle to X, so OFDM, introducing the high flexibility on the side link. We have this broadcast, multicast, unicast mode, and quality of service driven, and also probably supporting beamforming. One example, I do apologize for this. This is not the intention of being an eye chart. So no worries if you can't read those numbers. No worries. It's not the intention to read those numbers, but just give you the impression that we have more than 12 different lines and rows in a table corresponding to a quality of service flow. So this is the message here. So 5G side link introduces a quality of service flow management on the side link. So we can operate between the vehicles, between the users, different data connections, and each data connection inherits its own quality of service profile. So then we can optimize and have a management, a scheduler, knowing, aware of this. Also, we have either a coverage, so that the 5G network will schedule the side link resources. We have a situation for partial coverage, so one vehicle is in coverage, the other vehicle not. So then we can still use the scheduler from the 5G network to maintain the management on the side link. But we also have a mode, which is the mode 2, which works in out of coverage scenarios. So then we use a resource pool of radio resources on a pseudo-random situation, and the two vehicles will select and establish a connection vehicle to vehicle based on this kind of resource pool concept. In the different communication modes, we support three possible ways. The first one, I think that's self-explaining, is the broadcast mode. One transmitter will deliver the data to all receivers. Yeah? So based on, careful, in 5G new radio ethics, it's based on the destination layer 2 ID, which is based on the use case. Yeah? So that means I build a receiver group based on the vehicle applications. So if you support this application, then you belong to the group of people who are interested. Yeah. So this is the way how we communicate. So I'm not talking to you by your name. I'm talking to you based on the application or the use case you are currently running. Yeah. Then also we have a groupcast mode. This allows us to cluster the number of receivers in a further confinement based on the restriction on the use case. So I can build a group. Maybe also one example is we can also cluster this multicast group based on the region. Yeah, for example, here's an example on the bottom. You see an emergency vehicle that approaches a road crossing. Now it sends a collision warning. But as you can see, it's obvious that this collision warning is only important to be received by all the vehicles, all the receivers who are in the vicinity of this road crossing. On the right side, there's a vehicle depicted in red color. So this vehicle is already far away in a large distance out of this road crossing. So therefore, it does not belong to the zone anymore. So therefore, it will ignore and discard such a message whenever it is received anyhow. And we have this unicast procedure, unicast mode, so that we can establish like a device to device, vehicle to vehicle. And here, of course, we can use this sophisticated methodology with quality of service and establish a site link that maintains the required quality of service and also supporting with the HRQ, the HARC feedback. For this, 5G New Radio Release 16 introduces a channel structure. So we have, let's say, channels and synchronization reference signals supporting synchronization, supporting the channel status estimation, the demodulation, but also supporting the feedback. Yeah, that's shown here in the bottom light. This PSFCH channel, for example, this is a reverse channel. I don't want to use the term uplink downlink here because we have vehicle to vehicle, but let's say we have a so-called forward link and a reverse link. And now I have the advantage that I can send data in one direction, so the forward link, and I get in the reverse immediately a feedback acknowledgement. So we leverage and emphasize on reliability. And just give you a brief example about this flexibility in the site link. So we have here different allocation modes. For example, the network can schedule the radio resource on the site link in a dynamic procedure. So this is fast reaction, latency, and also a quality of service driven. Then also we can allocate a kind of pre-configured resources that allows to set up the connection time is faster. So the UE can transmit whenever data arrives before waiting for the permission. Yeah, so this is leveraging on latency. And also the network, for example, can configure some pre-static or semi-static resources. This is, for example, optimized for some kind of constant traffic. Example is like a voice call or video stream, for example. This is obvious in a voice call, for example. We have a kind of constant data is needed in both directions for voice call. Yeah, and this can be handled. And also we have this resource allocation mode 2. This is the principle how to select resources in a pseudo-random way to communicate with another entity in case of no coverage. Okay, then have a quick look into release 17. For those of you who love abbreviations and acronyms, I have some more for you, but I'm not going to read them. Just a quick overview. So one of the very important topic in release 17 is the satellite connection, non-terrestrial networks. So it's motivated by two major streams or two major motivational aspects. First one is called the new radio over NTN, non-terrestrial network. So here I call it a kind of human, the human-driven factor. So here focus is on eMBB. We want to provide internet access everywhere. So here remote areas. Then we see it currently also, let's say that we have some cataclysm, so disaster relief, so to recover communication as soon as possible, and also provisioning of data internet access into temporary hotspots. For example, I saw a statistic, I don't believe in statistics normally, but I liked that one. So there was a statistic, okay, I didn't dig into details, but it said about we have worldwide now about 70% of the population is in coverage with wireless connectivity. But if you look into the landmass, the globe, the landmass, we only have coverage in about 30 to 40%. That means there are many, many areas, yeah, like mountains, like the oceans, like the desert, yeah, like the rainforest, etc., where there's only poor coverage. And this is something we'd like to overcome with this non-terrestrial network. And the other motivation is this IoT over NTN. So use cases is Internet of Things, but massive, and massive here in terms of ubiquitous communication. I have selected here an example. I do apologize, this example is not 5G related, but I liked it, so maybe it shows the idea. This is a project where Rode and Schwarz, for example, is also involved in. It's an international project and it's named Icarus, like this Greek god, the messenger Icarus. He tried to fly, yeah. And like here, let's say we have in the International Space Station our transponder. So the base station is in the ISS in that way. And we have here, you see the photo of this bird. We have a very small transponder. It only weighs a few grams, 1 or 2 or 3 grams. It's a very short size. And now with this, the scientists can track the flight routes of the animals, of the birds, for example. And this shows like an example, what is our intention. So we have some monitoring equipment, for example, in the oceans, the waves, the water levels, the Arctic can be monitored. We can have some monitoring in the desert areas, fire detectors, smoke detectors, and so on and so on. So that is the idea. Non-terrestrial network in one slide. We target at space-borne space station. So that will be a paradigm change for the wireless world, because I would say now we have a base station that is learning to fly. Yeah, so we have a moving. So I mean that's a crazy term, like the base station. Base normally that means static, but now we have a space-borne transceiver. Yeah, and the base station is flying, and we have also different types of UEs. They can be kind of stationary or either vehicle-based, in ships, in airplanes, in vehicles, etc., but also handheld. And we target at 2 frequency bands. The sub-6, so the S-band is one target, and the other one is the Ka band, so in the range up to 30 gigahertz. But as there's no free lunch, also for non-terrestrial network, we face a couple of challenges, and I only depicted a few of them. Yeah, I also have a webinar on NTN that it goes into more details. But let's say, of course, we can see some of the challenges. The first challenge is obvious, of course, is the time. Because of the long distance satellite to user equipment, even in LEO constellation, we have 1,000 kilometers, for example. So this causes a very long round trip time. So this has some impact, for example, into the random access channel. So we have to make sure that our RATCH window is set properly. Then, of course, we have an impact on the HARC process. Yeah, you send data and you wait very long for the feedback. So then you may need a very large number of HARC process. We definitively have a free space path loss. So we like to mitigate this with beamforming methodologies. Another impact, as I said before, I mentioned that we have the objective to obtain perfect knowledge of the channel status. But that is a challenge in satellite, because it's obvious, because of the long delay, our channel status is no longer valid. Yeah, so it's not like in television, the latest news anymore. Yeah, the news is outdated. Yeah, if I'm going to tell you the stock market information from last week, then you say, hey, come on, that's boring, that's old stuff, I'm not interested in this anymore. And this is our dilemma we're in. So a feedback about the channel status information is maybe not valid anymore. So we also have to redesign our, let's say, selection mechanism for modulation and coding scheme, for beam adjustment, so beam management, etc., etc. And also one critical impact is the Doppler shift, because we have a moving transmitter. So here, in this case, our satellite base station is moving. Also the devices on Earth, they may move. Yeah? And then we have a kind of carrier frequency offset, Doppler shift, depending on the elevation angle and depending on the speed of the satellite. Yeah, so just to mention a few challenges that we are facing and we have to cover. Industrial Internet of Things is also going to be enhanced. And here the focus is, let's say from release 15, we set the fundament with numerologies, with mini-slot, latency focus. Then I mentioned it already in release 16, we have this time-sensitive network and also isolated or, let's say, the network slicing different deployment options. And now in release 17, on one side, we focus on new use cases. For example, this augmented reality that probably requires some new quality of service profiles to handle such connections. And also we identify additional needs, additional improvements. One example, I mentioned in the release 16, this TSN, time-sensitive network, where we have a deterministic delay. We'd like to compensate, or first to measure, to get the awareness of the overall delay, so the ingress to egress in the 5G system, like here in this, let's say blue color, in the 5G system from end-to-end synchronization. Yeah, so ingress, egress, this is the time delay we'd like to see. And now you can guess that every of these timing factors has a kind of error, the epsilon. And that is now the idea that we get the uncertainty of each of these smaller interfaces here depicted, let's say of these small connections. So we have, let's say, the interface inside the UE. So it receives the data coming from the bridge, from the external, then the UE. This is the first kind of time uncertainty. Then we have the radio uncertainty. So UE to G node B. This is our 5G radio link. Do we have a certain kind of time? We know propagation time, at least speed of light. But then also we have a kind of time delay, a time budget, an uncertainty. Then also here it's a kind of two radio link description. So we have two UEs, two radio interfaces, which are used here. And this is something we would like to compensate to get the awareness about, and then we can compensate this. Another example is how this industrial applications will derive and will require new kind of parameters. And here's one example from the quality of service. Typically in 5G we have parameters like guaranteed bit ratio, like the block error rate expected, like a priority, etc. Now we introduce another term which is especially important for industrial application, especially when you consider a periodic data flow, like shown here in the orange color, between source and destination device, target device, we have a kind of periodic permanent data connection. Yeah? And now if there's an absence, something happens on the radio link, and now the question is, when do we consider the radio link to be dropped? Yeah? And now we get a new quality of service, a parameter which is here named as survival time. So I have a time, survival time, and during this survival time, I consider the radio link to still be alive. So then we have a faster recovery if the radio link recovers. And this is then also a new quality of service parameter that is introduced. Side link in release 17, we have lots of study work items to optimize the side link. So I have to say in release 16, that's shown in the upper part, the focus has been on the automotive. Yeah, so even if this was called V2X, but now we more or less worked on the V2V, vehicle to vehicle. And now we really focus on the X, so everything. Like shown here, like vehicle to pedestrian. Yeah, so introducing an energy safe mode like DTX, DRX on the side link to have some power saving methodologies that we can allow some variables. For example, here this pedestrian or this children playing football, this has maybe a watch, a smart watch, which is capable of V2X communication. Then we get a collision warning. We have for industrial applications also the idea of introducing the side link in a direct communication side link for industrial application. Yeah? So then wider spectrum, reliability, and also, for example, for proximity services, here for like policemen, an idea could be like an enhanced relay that we use side link relay. Yeah? And that is also another topic, to use the side link as a relay. For example, like here on the mountain side, there's one UE that is in coverage to the base station, and this UE now provides its side link connection to a second UE which is out of coverage. Yeah, so by this way we extend the coverage from a network. Yeah? And this also is designed in this the right side. We have the three vehicles, and we extend the coverage range of the side link communication by using another vehicle as a relay. Yeah? And for this, we introduce a new adaptation protocol, this ADAPT. So this has to map the quality of service and the data flow onto this lower layer site link information. Yeah? There are different scenarios discussed. Let's say, like shown here, one UE is in coverage, the other UE not. We can also have site link communication when both UEs will be in coverage. Yeah? Or even an interesting field is when one UE is in coverage to one cell and the other UE is in the other cell. Then we have a kind of site link relay between two different cells. And also the idea is to use the site link relay. Yeah? So certain scenarios will be discussed. The hunt on Internet of Things. And then also we introduce this reduced capability, yeah, in 5G. Maybe just very quick, but I skipped that slide, is when we have our IoT expression, and then more now when we have certain services, and I quote here the Ericsson report, they did a kind of classification of IoT into these terms like a massive IoT, like sensor style, then we have broadband IoT, and also we have critical IoT, where we have different requirements like latency, like data throughput, etc. And with this information, we take now a closer look into our 5G flow. Yeah, so we see 5G, and I start with, on the bottom line, we have LTE-M and narrowband IT. So these technologies have been designed for Internet of Things application, and they will stay. This is the good news. In release 16, we have now a change in the core network, that the 5G core network will become the manager for a new type of LTE base station, an updated LTE base station, this next generation eNote B. And now the next generation eNote B will provide the NB-IoT radio link, but the 5G core network will maintain and guarantee the survival. And on the other side, we see on top, we see the eMBB, the high throughput, yeah? Like we see, like let's say, like 7.5 gigabit, which recently demonstrated, and even higher beyond that. So this is, let's say, of course, the obvious, the devices, high-end devices, high data throughput as much as possible. We talked about the critical application in URLLC, and now you'll see here in the green color, this reduced capability. This is now the target. We want to bridge, let's say we want to offer a little bit more data compared to LTE-M, but less than 5G, yeah? And this is, let's say, to focus in between. And therefore we introduce, let's say, new kind of, requirements in that way, that we allow, for example, a UE that offers only, let's say, 5 megahertz bandwidth, that only has 1 or 2 antennas, so doesn't support all the MIMO schemes, that maybe we have a kind of half duplex operation, etc., etc. So this is a kind of relaxation strategy to allow also complexity reduction. With power saving, the trend is to introduce, let's say, DTX, DRX, etc. They have been defined in release 16. And now in release 17, where will be some enhancement, for example, and we consider also an impact of power saving is, let's say, measurements. Yeah. So now in 5G, for example, as I said, for channel status information, it's obvious that user equipment is a measurement device and monitors and measures on multiple different reference signals over a wide band frequency spectrum, very often in time domain, etc., etc. This allows us to get a perfect knowledge of the channel status, for sure. Or even for mobility, handover to a neighbor cell, you need to monitor the neighbor cells. This is also obvious. But now let's talk about such type of devices. For example, I have a stationary device, Internet of Things. It will not do a handover. So why should it be forced to monitor the neighbor cells? There will not be a handover. And that means now we are discussing on reducing the effort for measurement, because measurement is also consuming electric energy. And that is now, let's say, a new idea for this reduced capability power saving, that we have a relaxed measurement reporting and also paging groups. Paging is also a feature that requires, because then you have to pay attention to receive in the downlink. But if you're kind of stationary device, and now another methodology would be paging subgroups with different priorities. So that also reduces the energy consumption. In the positioning enhancements, we have first new use cases. That's the interesting part in 5G, that we do not only consider the so-called commercial use cases, but also that we have much tougher and more stringent requirements, especially for industrial IoT. So here, like horizontal position in 20 centimeters, vertical position, less than 1 meter, and also very fast reaction time. So like time to first fix needs to be speed up. I have to say with release 17 now, there won't be any, let's say, dramatic new technologies to measure the position. But where do we see the optimization and the enhancement? For example, the enhancement is like aggregating various positioning methods. Yeah. So do not only rely on one measurement, yeah, that you can get reliability that you prove and verified with other measurements. For example, I'm using beamforming in combination with the round trip time. Or we have the TDOA, time difference of arrival, but measure the TDOA over various carriers in carrier aggregation scenarios. Yeah? So this is some of the features that are discussed in release 17. The next step is an important field is, of course, one is the measurement accuracy. So high accurate positioning. But the second question is, can you trust? Yeah, it's like in security discussions, it's a matter of trust. Can I trust my position estimate? For example, a GNSS spoofing system. Yeah, somebody is faking the satellite information. And now, for example, an idea could be that we have the GNSS positioning signals, GPS, Galileo, Beidou, whatever. Yeah? But to verify it, to trust it, we are now delivering an authentication code, an integrity check over a 5G radio interface, for example, over 5G broadcast. Yeah? And like shown here, this, I don't want to go in details in this, is this the estimation theory, we call it the Stanford plot. So now we have, let's say, different kind of probabilities with alert limits and target limits. And then when this is trespassed, we set an alert. And this is a matter how to determine the trustworthiness of the positioning signal. And a quick outlook in release 18. What's going to happen in release 18? I have to say, sorry, this is, let's say, current status. Probably, I hope you understand, this slide is subject to be changed. And it just presents, let's say, a very brief overview what are the discussion topics in release 18. Let's say I start, let's say, 12 o'clock on top, the narrowband operation. So, for example, here we allow operators to use their chunks of spectrum to be aggregated, yeah, so that we may aggregate like a carrier aggregation scenario, chunks in spectrum, and such spectrum chunk will not contain a 5G synchronization signal. There are features like network energy saving, so that we have downtimes for base stations coordinated with neighbor cells. Artificial intelligence is a big topic introduced for features, for example, like link evaluation, positioning prediction, as I said, quality of service prediction, beamforming management, etc., etc. We discussed about this reduced capability that will be evolved with more narrow bandwidth, power saving enhancements like a wake up signal, which is quasi permanent off mode, etc. The 5G broadcast is extended for much wider scenarios and flexibility for broadcast and multicast. For augmented reality, we introduce new quality of service and KPIs. The side link is then extended for ranging positioning, so relative differential positioning. So let's say two vehicles on a motorway, and you want to do not only estimate your absolute position, but I would like to estimate the distance beside the other vehicle. Yeah, so am I still, let's say, 1 meter beside, and I avoid a collision. Yeah, side link enhancements with this relay, and also we have coexistence between LTE and new radio on the side link. Duplex operation is an interesting topic, that we allow a flexible TDD scheme. For example, also this full duplex XDD that we transmit and receive at the same time, and we have an enhanced interference management. Protocol stack mobility to shrink the layer 3 impact to make it, let's say, faster, predictable. Uplink enhancements that we consider more than 4 transmitters, 4 TRX, so 4x4 MIMO is not the upper boundary. CSI reporting, multi-beam, again, we are not yet there that we have perfect channel knowledge. So again, some enhancements. Multi-radio is an interesting topic, that we combine 5G, for example, in dual connectivity with Wi-Fi, for example. Yeah, like this enhancements of Wi-Fi offloading. And also, let's say that we increase the dual connectivity, the number of links. Yeah, so then maybe I have in future a 3-cell dual connectivity. Yeah, so forgive me. Let's say we have more than 2 dual connectivity scenarios. smart repeaters, IAB with mobile devices like the IAB node can now be on a vehicle based, moving vehicle. Internet of Things with short interruption times, including also the side link introduced into these public networks. The satellites will now be extended to everything that can fly. So then I can put my base station into, let's say, a so-called hubs. That's an abbreviation for everything that flies, like a helicopter, drone, etc. And also for V2X, and let's say this is obvious, that we look into the frequencies beyond the 52 gigahertz range. So this is also clear in release 17. But now let's say discussion is, of course, let us use the ISM band in the 60 gigahertz, for example, for V2X communication or for industrial applications, let's see. And also probably we extend our 5G frequency range up to, and you see here a number up to 114 gigahertz. That's just a line in the sand. Okay, so just a brief outlook what we may expect. Let's say just to give you one example of this discussion, in release 18 is, for example, here in the vehicle, this relative positioning that I'm using a number of multiple arrays in my vehicle. Then I can estimate due to time of flight, so round trip time, and angle of arrival with beamforming methodologies. And I can now use a lot of mathematics here from the estimation theory to get a kind of probability and likelihood information, the most likely distance between the vehicles. So here the goal is, objective is to have a kind of differential position. Okay. And then, of course, it's clear 5G will not be the end in that way. We already started research on this expression like 6G, like here from the timeline. But we expect 6G, let's say in the range of 2030. But research is starting now. Academic people are starting working. We have the first kind of event starting. Also in today's event, there will be additional presentations about the trends and the way towards 6G. Rodenschwarz, we are proud to support the industry and the academics with our test and measurement expertise, for example. One feature, of course, seems to be obvious, that goes for wider bandwidth. And that's why, for example, we introduced our spectrum analyzer going up to 8.3 gigahertz, wider bandwidth. And we have many, many more products to introduce into the 6G market. So coming to my last slide, and I hope you clear and you understand that with 5G, there's much more than beyond, and just much more than only release 15. So there's more beyond release 15, 16, 17, and 18 is going to come. So 5G is a marathon and not a short distance run. So we are proud, Rodenschwarz, that we can help the industry with our expertise in test and measurement. And I'd like to thank you very much for your time, for your watching and listening. And if there's any questions, now feel free, and I'm happy to take any questions. Thanks a lot for your time, and stay healthy. Goodbye.
네, 지금까지 첫 번째 세션 Ongoing Evolution of 5G 내용을 들으셨습니다. 네, 내용상으로는 이제 마지막 부분에 6G에 대한 내용까지도 잠깐 언급을 해주신 내용이었었고요. 뭐 저도 내용을 쭉 한번 봤었습니다만은 저희 강사로 발표해 주신 라이너 스툴파우스 씨는 이 이동통신 분야에서 이제 굉장히 오랫동안 테크놀로지 매니저로서 활동을 해 주셨어요. 그래서 굉장히 많은 내용을 말씀드릴 수 있는데 시간 관계상 이제 조금 빠진 내용들도 발표를 말씀을 못 드린 부분도 있었을 거고요. 또 게다가 이제 또 최대한 많은 내용을 말씀드리려고 하다 보니까 조금 말이 빠르지 않았나 이제 그런 생각도 들긴 합니다. 그래서 어떠셨을지는 모르겠어요. 어쨌든 뭐 내용을 쭉 들으셨고요. 그래서 뭐 결론은 그겁니다. 5G라고 하는 이 기술 자체가 이미 우리가 쓰고 계신 분들 많으시죠. 그런데 이 기술 자체가 이미 이걸로 해서 완전히 끝난 게 아니라 현재에도 계속 발전하고 있는 단계이고 뭐 포지셔닝이라든지 뭐 여러 가지 그 기능들을 말씀을 드렸는데요. 이런 내용들이 계속적으로 또 확장될 개념들이기 때문에 추후에 이런 기능들이 더 확장이 된다면 더 많은 어떤 그 어플리케이션들이 가능할 거다. 뭐 이런 내용으로 말씀을 드린 것으로 보시면 될 것 같고요. 뭐 가장 중요한 내용은 그거죠. 5G가 여기서 끝이 아니다. 뭐 이런 부분들로 기억을 해주시면 될 것 같습니다. 그 진행되는 동안에 이제 채팅창 내용을 쭉 봤는데요. 뭐 아마 여러분들도 같이 보시고 계실 것 같아요. 근데 오늘 5시까지 진행이 될 예정인데 결론을 벌써 나왔네요. 채팅을 보니까. 예. 5G를 벗어나서 6G로 가야죠. 이승우님께서 올려주신 코멘트인데요. 예, 오늘 제 생각으로는 적어도 지금 뭐 이제 1시간 정도 지났습니다만은 예, 오늘의 그 베스트 코멘트가 아닐까 하는 생각이 들어요. 그래서 이런 부분들은 참 정말 뼈를 때리는 말씀을 해주셨지 않나 이제 그런 생각이 듭니다. 그래서 쭉 그 올려주신 내용들을 한번 보겠는데요. 예, 우선 그 히스님도 그렇고요. 요 아래쪽에 그 정영규님도 같은 얘기 질문해 주셨어요. 그래서 그 5G 자료 오늘 세미나 자료를 어디서 다운받을 수 있는지 요거 물어봐 주셨는데요. 예, 뭐 그 저희가 자료는 제공을 해드릴 예정이고요. 그 관련된 링크나 이런 부분은 저희도 이제 그 준비해야 되는 시간이 약간 필요합니다. 그래서 이런 부분들은 오늘 참석하신 분들께는 추후에 전체 메일 공지를 따로 드릴 겁니다. 그래서 어디서 어떻게 링크를 다운받으실 수 있는지 이런 부분들은 확인하실 수 있도록 드릴 예정이니까요. 아마 제 생각으로는 한 일주일 정도면은 저희 쪽에서 관련된 내용으로 그 참석 감사에 대한 내용과 이 링크 그리고 다시 보기에 대한 내용, 지금 다시 보기도 중간에 보면 그 정대령님 포함해가지고 두 분께서 이제 그 내용을 문의를 주셨어요. 그래서 같은 내용으로 해서 저희가 링크 및 그 접속하실 수 있는 내용 그 사이트 내용들을 저희가 관련해서 아마 따로 회신을 드리게 될 것 같습니다. 그리고 여기 정성수님께서 이제 질문을 해주셨어요. 저희 그 시작할 때는 질문이 꽤 많이 있지 않을까 이렇게 생각을 했었는데 의외로 오늘 지금 적어도 지금 첫 세션 지나갔습니다만은 질문이 그렇게 많지는 않네요. 그래서 5G와 6G를 구분하는 가장 큰 특징이 뭔가요? 라고 질문해 주셨어요. 예. 아마 그 쭉 들으셨을 겁니다만은 현재까지는 그 5G가 되어 있는 상황이고요. 6G는 이제 뭐 아주 초기 단계입니다. 보통 제가 기억하기로는 이동통신 기술들이 이제 다음 차세대 기술들에 대한 그 내용들을 이제 준비를 하게 되면은 뭐 그 기간이 딱 정해져 있는 건 아닙니다만은 통상적으로 보면은 한 10년 이상 정도 준비를 하는 것 같아요. 그래서 지금 5G가 나오자마자 상용화 되는 시점부터, 그러니까 아마 우리나라 기준으로 하면 2019년도가 될 거고요. 이제 글로벌하게 얘기를 하자면은 2020년도 정도가 될 것 같습니다. 그래서 이렇게 해서 지금 상용화되고 이제 실제 사용들을 하고 있는 상황이죠. 그런데 사실 그 상용화와 거의 비슷하게 6G에 대한 어떤 이니셔티브라고 해야 되겠죠. 이런 부분들도 시작이 된 걸로 여러분께서 기억을 하시면 될 것 같아요. 그래서 오늘 지금 마지막 7번째 세션이 6G에 대한 내용들을 이제 주로 말씀을 드리게 될 텐데, 뭐 결론부터 말씀드리면 그렇습니다. 6G는 아주 지금 정말 극초기 단계라고 말씀을 드릴 수 있을 것 같고요. 그래서 어떤 특징이라고 얘기할 수 있을 만한 부분이 사실 정해진 거는 없어요. 하지만 뭐 지금 얘기 나오는 내용들을 놓고 봤을 때에는 그 더 넓은 그 주파수 대역폭 뭐 이런 부분들을 위해서 뭐 그 목적을 가지고 있다고 생각을 하는데, 결과적으로는 그 테라헤르츠라고 보통 표현을 하죠. 100기가 뭐 사실 엄밀하게 따지면 테라헤르츠는 그 1000기가헤르츠가 되겠습니다만은 뭐 그 100기가 이상도 테라헤르츠라고 표현을 하시기도 하더라고요. 근데 어쨌든 그 서브 테라헤르츠, 테라헤르츠 이런 주파수, 더 높은 주파수 대역으로 기술이 아마 올라가게 되지 않을까, 뭐 이런 예상들을 하고 있는 상황이고요. 사실 이런 액션은 뭐 뒤에서도 다시 세션별로 이제 말씀을 드릴 것 같습니다만은, 내용상으로 봤을 때는 4G에서 5G로 넘어오는 과정에서도 비슷한 어떤 어프로칭이 있었어요. 이제 이런 부분들 때문에 어떻게 보면은 이제 비슷한 맥락에서 접근이 되는 게 아닌가, 뭐 이렇게 생각이 되고 있고요. 이런 부분들이 이제 적어도 지금 아주 말씀드렸던 것처럼 극초기 단계이기 때문에 실제 이런 부분들 어떤 윤곽을 우리가 볼 수 있다거나 좀 더 파악할 수 있으려면은 아무래도 적어도 한 뭐 1, 2년 이상의 시간은 필요하지 않을까, 뭐 이런 식으로 생각이 되고 있는 상황이라고 말씀드릴 수 있을 것 같아요. 그래서 이런 부분들 좀 더 시간을 두고 같이 함께 저희와 함께 좀 보셨으면 하는 바람이 있는 거고요. 이런 부분들에서 혹시라도 뭐 마지막 세션에서 이제 뭐 그 채널 모델링이라든지 이런 부분에 필요한 어떤 솔루션에 대한 이야기도 잠깐 나오게 될 텐데요. 그런 부분들 중에서 혹시 필요하시거나 관심 가는 부분이 있으시다면 언제든 저희 로데슈바르즈코리아로 문의를 해주시면 관련된 내용으로 저희가 같이 도와드리고 저희도 함께 그 내용을 넓혀나가는 이런 액션이 가능하지 않을까, 뭐 이렇게 생각이 됩니다. 예, 그래서 오늘 뭐 일단 첫 번째 세션에서는 지금 말씀드린 것처럼 이제 질문은 그렇게 많지 않으셨기 때문에 뭐 바로 두 번째 세션으로 넘어갈 수 있을 것 같고요. 두 번째 세션은 제목이 5G IP throughput performance and 5G voice over NR이라고 되어 있습니다. 뭐 당연한 얘기입니다만은 뭐 그 5G도 결과적으로 이동통신이잖아요. 우리의 스마트폰을 위해서 사용될 기술이기 때문에 인터넷 연결을 위한 IP 연결에 대한 성능 측정이라든지 그리고 음성 지원에 대한 부분들을 확인을 해야 되겠죠. 이제 그래서 이런 부분들에 대해서 어떤 면에서 뭐 측정이라는 개념으로 접근을 할 경우에 어떤 부분들을 볼 수 있을 것이냐, 이 기술들이 과연 어떤 지향점을 가지고 있는 거냐, 이런 부분들에 대해서 아마 말씀을 드릴 수 있을 것 같습니다. 그래서 두 번째 세션은요, 저희 본사의 크리스찬 호프 씨, 저희 본사에서 이제 내용상으로는 시니어 프로덕트 매니저를 담당을 하고 있습니다. 그래서 저희 솔루션 관련된 부분과 함께 실질적인 내용들을 좀 더 보여드릴 수 있지 않을까, 말씀드릴 수 있지 않을까, 이렇게 생각을 하고 있습니다. 그래서 실제 IP 스루풋에 대한 내용들, 왜 IP 스루풋을 우리가 봐야 되는지, 이런 부분들에 대해서 신뢰를 들어가면서 아마 말씀을 드리게 될 것 같습니다. 그래서 지금부터는 그 두 번째 세션이죠. 5G IP 스루풋 퍼포먼스, 5G 보이스 오버 NR, 요 내용들을 함께 보시도록 하겠습니다.
So welcome everybody to this presentation about 5G IP throughput and 5G voice over NR deployment technology and testing aspects. My name is Christian Hof. I'm product manager at Rodeschbarz's for mobile communication testers, and I'm responsible for our mobile communication testers CMW500 and CMX500 with a strong focus on application testing. During my presentation, I will explain a little bit more in detail what application testing means. But let's have a look on the agenda of today's presentation. We will start with a cellular evolution. Have a look here, the changes from 1G up to 5G. We will talk about application testing and why application testing is in the meantime so important. And I brought with me two use cases with the focus of application testing. One is a performance test for 5G throughput testing. Here we will talk a little bit about the theory, and then I will also do a quick demo. And the second use case is functional and performance tests for 5G audio speech testing. Also here a little bit theory, and also I will end up here with a demonstration. Finally, we will have a quick summary of this presentation. And let's start now. Okay, the cellular evolution. We started in the late 80s, early 90s with 1G and 2G technology. So the first mobile phones came out and they supported voice services and SMS. With 3G, first time the internet became available. So with UMTS, we had data rates available so that you could do some web browsing. WAP technology was introduced and so on. With 4G, the real mobile internet became available. Here, first time smartphones were available, where we had where we have a lot of apps running on our phones. We use it for social media, video streaming, music streaming from different platforms. But the phones here use also voice services for communication, but we also have instant messaging tools available. With 5G, we want to add new verticals like the EMBB, enhanced mobile broadband, massive machine type communication, and ultra reliable low latency are in the focus of 5G. For that, the numerology changed dramatically, and a lot of parameters were changed to achieve these targets. It is important to understand that since the 4G network, also the technology and the infrastructure behind the network changed. In the past, we had in 2G and 3G a circuit switched area for voice communication, and the data was transmitted over packet switched. But since 4G, everything changed, and we changed to an all IP network. So this means everything which is done in this network happens over IP. So IP plays an important role within 4G. And this is the same for 5G. For example, if you want to place a voice call in a 4G network, you need to have a dedicated infrastructure. It's called IMS, IP Multimedia Subsystem, which is a service enabler for voice services. And that's why it's also important to focus on the IP layers and to test the functionality of the applications using IP technology to provide their service. So what is mobile device application test? To understand this, we need to have a look on the protocol. We have here the user plane protocol structure, where we have in the lower layers, the RF, so the connection of the device with the network. In the higher layers, we have the IP layer, and on top of these, the application. And application testing describes the process in which an application is tested for its functionality, usability, and consistency. We use the IP layer to communicate with the World Wide Web. So this is also what the end user at the end is used, and where he or she feels the quality of service and quality of experience. So that's why it's important to test also these layers. And we have here several test possibilities. So we do, for example, functional test. Functional test, for example, when we talk about voice services, we have here to verify, for example, the IMS protocol, that you can set up a call and everything works properly. But also performance tests, and here, for example, the throughput testing belongs to. But also performance tests for voice services, because we have packet losses, jitter, and so on the IP layer, and we need to verify the performance and the quality of service of our device under test also on the IP layer. Usability tests, very important, are also security tests, that you verify, for example, that the communication of your application is secure through the internet and to the servers in the internet, that, for example, the correct encryption protocols are used. And at the end, also certification tests belong to this area, where the applications are certified by dedicated test houses. In my presentation, I will have a closer look on the performance test for 5G throughput, and we will talk also about functional testing and performance tests for audio speech. So let's start with the performance test for 5G throughput. At the beginning, I want to remember you on the triangle of 5G use cases. And we have here the EMBB, Enhanced Mobile Broadband Use Case. Here, everything is about data, speed and capacity. This is an important topic for EMBB. Here, this use case is data-driven. We require here high data rates over a wide area to support all these new verticals and use cases with 5G. The second use case is ultra-reliable low latency. Here we have strict requirements in focus of latency. So, for example, for a remote surgery where a doctor is doing a surgery via the internet with his patient. Autonomous vehicles, when we want to have autonomous driving, also here low latency is important, that the car reacts correct on the information, for example, it gets from another car or a pedestrian or from the internet. And also tactical internet is also part of this area. Massive machine type communication, here keyword is IoT, Internet of Things. We have here a lot of devices which are connected to the network, They just transmit some data packages from time to time. Here, a long battery lifetime is very important because these devices typically stay several years in the field without getting any service. So we have here these three use cases, and the throughput use case belongs to the eMBB enhanced mobile broadband. Here we need to take care to achieve high data rates, 10 gigabits per second, 20 gigabit per second. For that, a new and flexible numerology for 5G was introduced, and we will have a look on this now. Yeah, modern phones rely on multiple technologies to achieve high data throughput in 5G. So to achieve this 10 gigabit, the numerology was changed, and we have here different technologies which are introduced and used to achieve this target of 10 gigabits and more. Let's have a closer look here. So to meet these requirements, higher frequencies were introduced. We have the problem that in the lower frequency range, up to 6 gigahertz, a lot of spectrum is already occupied by operators, and it's not so easy to have here new frequencies, and especially with the focus of wider bandwidth. This is the second important topic here. So the frequency range in FR1 up to 6 gigahertz is already occupied. That's why a new frequency range was introduced, FR2 in the centimeter or millimeter wave frequency range. And here it is possible to have spectrums and frequencies also with a wider bandwidth to achieve the target for higher throughput. Also, higher modulation scheme is used in 5G to transmit more bits. So 256 QAM is used here for data transmission. More streams, so massive MIMO is used. And another topic is multiple bands, so massive carrier aggregation, so up to 16 streams could be combined. Also here to achieve a wider bandwidth, to have more capacity to transmit data to the end user. And due to the fact that we have here also new frequencies, also new antenna technologies were used, multi-antenna technology, and for example in FR2 you have to test over the air. There's no cable connection possible anymore. And so we have here also multi-antenna technology in use to achieve better signals for high throughput. So the higher frequencies in this slide, it's quickly explained what are the frequency ranges. So we have FR1 from 410 to 7.1 gigahertz. Here the frequency range. So it's in the meanwhile a little bit more than 6 gigahertz, and we have FR2 here starting from 24 gigahertz up to 52 gigahertz. So this is the range of FR2, and we have already here specified a few bands which could be used for data transmission. When we have here a little look on the numerology taken from the specification, then we can see, so we have here FR1, FR2, higher frequencies. Multi-band is supported by up to 16 carriers, so carrier aggregation is here the technology. A wider bandwidth, so we have here specified in FR1 up to 100 megahertz, and in FR2 it is possible to use up to 400 megahertz, because here more space is available. And then we have here the higher modulation scheme, 256 QAM to increase the throughput, and here also MIMO schemes, so more streams could be transmitted. Just here a quick summary. And we can see this as well in the formula, which is used to calculate the maximum throughput rate. Yeah, I don't want to bother you here with too much details. Nevertheless, we can see here number of aggregated component carriers. In this case, yeah, it could be up to 16 to increase the available bandwidth for data transmission. We can see here the number of layers. So MIMO is here included. And here also the modulation and coding scheme. We can see 256 QAM 8 bits could be transmitted with this modulation scheme. Yeah, other visualization. So we combine multiple carriers addressing wider bandwidth and multiple bands. This is in one direction. We have the different modulation scheme, adding here 260 QAM, the other area, and more streams, and this increases at the end the throughput in 5G. To be able to test these throughput in your lab, you need to have test equipment which supports, on the one hand, the different flavors of the network, because 5G is not just pure 5G. We have here different rollout scenarios, and your test equipment need to support this. On the one hand, we have here the option 3, called non-standalone mode. The rollout here, we have a running LTE network in place, and we add a 5G cell for data transmission in parallel. The control is running over the LTE network. So LTE in this case is a master, and 5G is just used to transmit data. In option 2, we have standalone mode. So we already have operators which use 5G in standalone. In Germany, for example, the first operator started with a rollout here of 5G standalone. And so this is also a use case which need to be verified. And our test solution looks like following. We have here the CMW500 communication tester, the #1 test equipment for LTE. This is used to provide, for example, in the non-standalone mode, the anchor cell for 4G. We support here the baseband and the RF. And it is also used in this scenario to send out the FR1 RF signal. It also carries the data application unit, which is very important if you want to test on the IP layer. We have here a dedicated hardware available, an infrastructure, which is handling the IP. You have the possibility to hook up your company LAN. It supports IPv4 and a lot of measurement tools. Some more details about this later on. And the CMW500 is extended with the CMX500. And the CMX500 is here running the 5G and R layer 1 stack and responsible for the baseband here. And also it carries interfaces for the millimeter, so the FR2 frequency range. We have here the IF boards included, up to 2 could be added here in this case. For example, if you want to test MIMO. And to these interfaces, we have our remote radio heads, CMX Head 30, which could be connected here. And with this, it is possible to support the bands in FR2 up to 43 gigahertz. The remote radio heads does here the up-down converting of the signal, and you can test with this remote radio heads, for example, in a chamber, because in FR2 we have to test over the air. As I said, and from the beginning, my first slide, it was mentioned, IP is key for mobile application test, because here everything is about end user, quality of experience, and quality of service. We have to test the performance of the IP layer, because also the end user can verify, and he finally feels the quality on the IP layer. If you just perform tests, RF tests, for example, here on the lower layers, and for example, just measure throughput on the lower layers, you will not identify bottlenecks between these layers, and the end user maybe could have a bad quality of experience on the IP layer, and because he doesn't reach the throughput rates we achieve on the lower layer. So not just performance on the lower layers are important, also performance tests on the higher layers are important. And very often we see press releases, we reached high throughput, and typically it's just mentioned the throughput on the lower layers, but as I said, it's important also to check the higher layers. When we have a look here, how test setups for IP testing look like, so typically they are very complicated. So we have here a communication tester, which is connected with a throughput server, providing here a data generator. We have here a control PC, additional servers, external servers with IMS running, and so on. So the setup becomes very complex and not so easy to handle. Also, when you want to communicate with the internet, the extra gateway is required. You have firewall settings, all the IP settings need to be correct, and you need to take care that they are correct. Firewalls are running on standard PCs typically block the communication, and you have to also take care that the network you use here is configured correctly, that it fits to the RAT you want to support. So in LTE, or especially in 5G, where we have high data rates, also the network here behind need to be configured for this high data rates. And this is complex, and very often it causes a lot of trouble. With our CMX 500, we have the solution for that. We already supported this environment in the CMW 500, and it is called the Data Application Unit. It's an integrated server PC, which supports you with pre-configured network settings for IPv4 and IPv6. These settings are optimized for high throughput, and it's also easy to connect here to the internet. You just hook up your company LAN to the test instrument, and then you could get IP addresses from your company LAN, and the CMX is taking care on the distribution of these IP addresses to your device under test. But also additional tools could be hooked up here. But we also provide a lot of internal functionality and internal servers. For example, when you communicate with the internet, you also need to verify the used protocols to the internet. Like we have integrated here a DNS server to verify the translation of web addresses to IP addresses. Or a file transfer server is available. If you want to verify file transfer and the FTP protocol, so the common protocols could be tested with our internal servers. An IMS server, very important. Today, normally you don't get a registration of a device without an IMS server. This IMS is also used for voice service testing and SMS over IMS. This is integrated within the CMX, so this keeps your test setup small and also easy to handle. And yeah, of course, a web server is available with a lot of additional tools. We have here a throughput app you could use on your mobile phone. A streaming server is available. We have logging capabilities and a packet generator running on this web server for quick testing. Just have a look and investigate what kind of functionalities our data application unit provides. But it not just carries servers, it also provides measurement tools. Throughput testing, IPERF, IPERF 123 is included. Ping measurement with proper charts that you can see the latency of your network. And a new tool is becoming available. It's called IPTune. So it's an automatic service to tune your IP parameters that helps you to achieve also the highest data rates on the IP level. IP analysis for security checks. Here you can monitor the communication of your device under test to the internet. You can also check, for example, where are the servers based around the globe, or for example, if the proper encryption protocols are used and you communicate secure to the internet. IP logging, PCAP files for Wireshark are supported, and you can record these IP logs with a data application. So a lot of functionality is included, and it's still extended. The good thing is that everything is included in our common user interface theme squares. You can control it with a graphical user interface. We have here remote interfaces available like Skippy and XLAPI, which means Python. So you can remote control all these functionalities of the data application unit also with scripts. And with the integrated sequencer we have in theme squares, it is also possible to create test scripts and run these test scripts automatically and get a test report at the end. So the good thing is we have all these things required for application tested integrated in our test equipment. So it's a unique solution, but it simplifies your test setup dramatically. You have a very small test setup for testing IP applications. And we have comprehensive toolset available for testing throughput. Traffic generator, throughput app is available from the system directly. You can download it from the web server. Packet capture, a tuning mechanism to improve the throughput rates on the IP level. Everything is integrated within our CMX500. And this guarantees best reproducibility and stability wherever you need it. And you can also compare the test results. For example, from Korea in the US, you always have the same test setup and can use the same tools to verify the throughput values. Let's have a look on my demonstration, which I will show in a few seconds. The test setup here in this case looks like we have here our CMX500 minimum footprint setup, and we will use it for high throughput testing. The target here is 7.3, 7.4 gigabit per second. And we have here a device under test from Viavi. This device under test is controlled, and we have here also a data generator from Viavi, which is hooked up to the data application unit, and we generate here the traffic from this throughput generator. We use FR2, so we use here the IF interfaces of the CMX500 with remote radio heads in a chamber. The ATS 1800 is used here. And we have here a scenario where we have a LTE anchor cell and 8 times 100 megahertz FR2 carriers with 2x2 MIMO. So if you want to do the math, you can use the formula. We have here the format 31, subcarrier spacing 120 kilohertz, 256 QAM is used, 8 component carriers with 100 megahertz. And a little bit of LTE, and you come up here with 7.38 gigabit per second. I posted here also the link that you can do it by your own and calculate it by your own with this throughput calculator. Okay, let's switch to the demonstration. I start now the CMX. Okay, here it is. So we have here the scenario. It's already built up. We have the LTE cell. I start now the script. So we use here the Python interface of the CMX, and you can see that it remote controls the CMX. The cells are activated. So we wait now for the registration on the LTE cell. That the device register here we use for 5G 8 times 2x2 MIMO, and the modulation scheme 27 to reach here the high throughput values. I switch on the device. We wait until the device is registered on the LTE cell because we have here this non-standalone mode. Now it happens. So the device is now registered on the LTE cell, and in a few seconds it will also register on the first NR cell. If this is done, we can see it with the triangles on the left of the left corner. Also the 5G cell is now available, and now we have all the carriers combined in carrier aggregation. The first test, of course, is we do a verification on the lower layers. So we use a blare measurement. We can see no packet losses or nearly no packet losses, have 900 megabits per second on the NR cells. This ends up in a total 7.3 gigabit per second. And we have a little IP on the LTE. Okay, we also can monitor this on the tools from our device in the test. Here we have the 7.3 gigabit running, as I said already, or still on the lower layers, and we activate now the IP layer. We start here the packet generator, start a little script which enables the IP traffic on this device, and we can see here the green line is the IP throughput, and this is a little bit less because we also have headers and so on, which are involved here on the IP layer. So roughly 7 gigabit per second on the IP layer. This is a pretty good result, and you can see that it is also important to verify the throughput on the higher layers. This was a quick demonstration of this throughput testing we achieved here on the lower layers 7.4, and on the IP layer 7 gigabit per second. There is some room for improvements, but it shows that you are already able, with a small setup consisting of one CMW 500 and one CMX 500, to reach high throughput rates with this setup. And I also want to emphasize the flexibility of the user interface. We have here seen I remote controlled the CMX 500 via with a Python script, and we monitored everything on our graphical user interface. We saw the cells which were set up and switched on. We saw the registration of the device. We used the blare measurement in manual mode, and we run a script to prepare the network. The good thing is you can jump between the worlds. Also, if you have involved the sequencer, for example, you have created test scripts for your device, you can run this. You can switch to the interactive mode, change some additional settings, make a test before you change your test script. And jump between the different worlds and use the different interfaces to get your job done and to get your test done. And this is unique in the wireless test industry, that you have a user interface where you can decide what you want to do here in this environment and how you want to use it. Interactive mode, jump to sequencer, use a script and go back to the interactive mode. Everything is possible here with this user interface. Okay, so this was the use case for throughput testing. Let's have a look on the audio speech testing. For that, I want to jump back to my first slide. I mentioned at the beginning that all networks from 1G, 2G, 3G, all of them were supporting voice, and also 5G will support voice service. The reason for that, a smartphone will stay a phone, and it will be also used for communication, interaction with other people. And operators, they want to take care that you could stay in the 5G network. They don't want to do always handovers in case a voice call is arriving. So also that's the reason why voice service will be supported in 5G. And voice services will remain a central role in mobile networks, also in 5G, because people want to talk to each other. And there are things, you directly want to talk to your friend, you want to talk to your person. For example, when you do a business trip, you come to Korea and want to meet some friends and want to have a nice dinner at Takalpi with your friends, and typically you do this in person. You call them, you let them know, hey, I will be there. And you don't do this just with text messages. Also, for example, in emergency cases, yeah, you don't want to write text messages to your paper. Oh, I feel not so good. You want to talk to a person, and you want to tell them, hey, I don't feel good. Or in case of an accident, you also need support from another person. And that's why voice services still play an important role in the cellular networks. Some facts. So how will voice services look like in 5G? Yeah, it's a matter of fact that it will be a multi-step deployment strategy, because as mentioned also in the throughput demo, we have this option 3 non-standalone, where the voice or where the LTE network is having the control, and then we have standalone and so on. And yeah, step by step, the 5G coverage will grow, and then more and more voice services also in 5G will become available. It is also clear that IMS, so IP Multimedia Subsystem, will stay as infrastructure for 5G voice services. So it's like we had it in voice over LTE. The same infrastructure will be used. EVS will play a more important role. It was already introduced in LTE, but we have use cases in 5G where high quality voice is used, and that's why EVS will play a more important role. Yeah, and yeah, 5G at the end will also enable a lot of additional use cases like real-time voice translation, real-time interaction with others, and here also voice will play an important role. And that's why it's also required to analyze the voice quality services of your device under test. Let's have a look here on the multi-step deployment strategy. So as mentioned, we have here this ENDC mode where LTE is taking the control and 5G is just used for data transmission. In this case, we just have voice over LTE. It's the same like we had in pure LTE, because the 5G network is just used for data. If a voice call arrives or you want to do a voice call, it's a simple wall to call. But we have also scenarios where the call or where the network is already able to handle voice calls. In this case, we would have a wanna call, or in a pure environment, we would get a fallback to voice over LTE. This is called EPS fallback. Here in this case, the network doesn't support, 5G network doesn't support voice calls, and we do a fallback to LTE, and also we do here a voice over LTE call. So we have here scenarios, EPS fallback or EPS handover, which also need to be tested and need to be supported. And then we have standalone networks where everything is going via the 5G network and also via the 5G core. And here we really talk about voice over NR. Yeah, and your test equipment need to be able to verify these different scenarios. We have here, for example, a scenario where we have this non-standalone mode, and you need to check if the call is properly handled via voice over LTE. We have the EPS fallback scenario. Your device is registered in the 5G cell. A call is done. Does it a proper fallback to the LTE network? In this case, or for example, you have your 5G cell available, and also voice services are supported. And can I do here a voice over NR call with my device? As I said, IMS will be the service enabler for voice over NR. So that's why it is important also to support this IMS. IMS is a technology or access independent infrastructure. So it's also used for Wi-Fi calling and also in LTE already. And this will also the service enabler for multiple services in 5G. SMS over IMS, voice over IMS, video calls are supported, and other things. And it will stay also as enabler in voice over NR. We have this infrastructure available in the CMX 500. So you have here also for WANA testing a very small setup, pre-configured server, which could be used for voice over NR testing. And you can perform here also functional tests with this environment. Some words about the EVS codec, or in general, the codecs. In WANA, we will be able to use the already known codecs, AMR narrowband, AMR wideband, and EVS will be supported in 5G as well. And here also the super wideband and full band mode will play an important role for high quality audio service. For example, I think it was 2 years ago on the Mobile World Congress where a company was demonstrating the EVS codec. So they had placed different instruments around in the exhibition hall, and they transmitted their music via the cellular network to, at the end, one phone. And there was a loudspeaker connected, and at the end you had nice, proper music where all instruments played together. And here also the EVS codec was used for this demonstration. And at the end, yeah, we had a great voice quality or audio quality, in this case, transmitted over the network. So with the EVS codec, it is also possible to transmit music. And that's why it's important also to have a focus on this codec and that you can test it. And because we have here more than 40 combinations with different code rate, bandwidth, code rate and bandwidth combinations available. And also there is an AMR wideband I/O mode available. And yeah, this is something which is supported by the EVS codec, and you need test equipment which is able to test it. And our CMX is able to test it. We have implemented this EVS codec in this, with this full flexibility. So you can verify the different code rate bandwidth combinations with our instrument. And we are ready here to support you to develop 5G mobile phones with high quality audio with our instrument. Okay, let's have a deeper look on the different testing areas for voice services in 5G. So first of all, we have the area of functional test. We need to take care that the device is properly registering on the 5G cell, of course, and also register on the IMS server. We have to verify the session initiation protocol so that the call could be set up properly. A quick audio verification in loopback mode is done. But we also have to verify functionalities like emergency call or the EPS fallback scenarios I mentioned. This could be done with our setup in the interactive mode in CM squares or using the sequencer or in combination with the test systems and in contest. When it goes into the direction high quality audio testing, we have here a cooperation with Head Acoustics, and we already verified that their lab core system could properly work with our CMX 500 for 5G and also for 4G with the lab core system. Here, these tests are typically done with acoustic in an acoustic chamber, and artificial head is used here to measure the audio signals, and the analysis is done on an external PC. When it goes to performance tests, we support this with our CM squares and CM sequencer. So for example, here, the verification under non-ideal conditions is required, like IP impairments, fading, and so on. And you can perform here also polka measurements over the non-ideal channel. And typically we have here operator test plans available, like we had it for voice over LTE. So dedicated test cases from operators which need to be performed and to verify the performance of the audio quality. The last field is field testing. This is not part of the CMX test environment, but we also have tools for verification in the field, and also here the QualiPoc could measure audio quality. Yeah, let's have a deeper look on the carrier acceptance and NetOp test solutions. This is the functional test. So we support here operators around the globe to test devices, and the operators have specified device acceptance tests, and this could be performed with our instruments. And also here the CMX 500 plays an important role. All the important operators in US and China, they have such kind of test plans, and these are supported with our test instruments. And we cover here all aspects so that you just have a one-stop shop, and everything could be covered with our instruments, from RF, RRM, performance tests, and also functional tests for voice over NR. When it comes to audio quality testing, your test system need to be flexible, because not everyone is using a head acoustic system. We have multiple audio analyzers available, and our solution supports with different interfaces also the different audio analyzers available on the market. We have a dedicated interface here via IP for head acoustic that we can hook up the LabCore system and do the audio quality testing. Then the audio quality test system is supporting here the acoustic tests. But we also support an analog interface, which could be used, for example, to connect audio precision, or a customized solution, which sometimes is also used in audio test labs, to do audio and acoustic tests with our setup. So here, maximum flexibility for you, nearly every audio analyzer could be connected to these two interfaces. Okay, this was a quick introduction of the functionality and the use cases, and I want to perform here also a demo now for the voice over NR call. I need to switch back to the CMX, and I've prepared here another demo for this voice over NR testing. Okay. Yeah, we have here already set up the NR cell. I switch on this NR cell, so the signal is now available and present, that we can do a voice over NR call. We have here a 5G core simulated. We have the DUT state. You can now switch off the airplane mode. We can see a direct registration of the device, indicated here by this purple triangle on the left side. We can see the device is registered on the IMS server. And now we need to perform a voice call. So yeah, we can see that the device is also registered on the 5G cell and is WANA enabled. First I want to do a mobile terminated call. So for that, I go to the IMS server. We have here the buttons available used, and when the device is registered, these buttons become active. I can press here this voice call button, and I click this button, and we can see that the voice call arrives on the device under test. Also the state was changing, and we answered the call, and we have now a running loopback call. If I would speak to the microphone, I could hear my own voice. Unfortunately, this is not possible with this online demonstration. This was a mobile terminated call. Let's do also a mobile originated call. For that, I have to hang up the call. It's a bit complicated here to control the instrument. I hang up the call now. Okay. I go now to the phone app on the phone, can dial any number, and it's picked up by our virtual phone inside the IMS server. And now we have a mobile originated call up and running. And so this was a quick demonstration of this user interface here, in this case, in the interactive mode for voice over NR with the CMX 500. There are more possibilities. As I mentioned, you also can test the EPS fallback. You can verify also Volta calls within this environment. If you want, you can write your test scripts and remote control this application, as I did it for the throughput testing, or demonstrated for the throughput testing. Same is possible here also for the audio. And also hooking, connecting audio analyzers for audio quality test is possible. Let us know if you have here questions, or we should do a on-site demonstration. Let's switch back to the presentation, and I want to finalize my presentation now with a quick summary. During this presentation, we had an overview about the different infrastructures. We learned why it is necessary to do application testing. And you are ready now to design and test 5G devices also on the IP layer, to create and to deliver devices with a great quality of service and a great user experience, because you also take care on the IP layer, because this is what the end user at the end will use and what he also feels when he uses devices. You learned what is important to maximize the IP throughput, and what kind of tools are available to do this with our instruments. And you also got an introduction into audio quality testing. You are ready now also to develop devices with high quality EVS audio, with high quality audio service. And we are, as Rohde & Schwarz, will support you to test here high throughput in 5G and also voice over NR services. Please let us know if you have more interest, and my colleagues in Korea are happy to support you. Thank you for your time. Thank you for giving me the chance to speak to you. It was a pleasure. Thank you very much.
네, 지금까지 그 두 번째 세션이었죠. 5G IP 스루프 퍼포먼스, 5G 보이스 오버 NR 관련된 내용으로 세션을 들으셨습니다. 뭐 결론적으로 말씀드리면 아무리 속도가 빠르더라도 이제 애플리케이션에서 결국 사용자가 직접 느낄 수 있는 어떤 접점이라고 할 수 있는 부분은 실제 애플리케이션 경험과 그런 면에서 이제 음성까지 포함해서 이제 이런 부분들이 이제 사용자가 직접 피부로 체감할 수 있는 내용이기 때문에 이런 부분까지 내용들을 확인을 해야 되지 않겠느냐, 정말 그런 속도가 나오는지 제대로 돌아가고 있는지 봐야 되지 않겠느냐, 이런 부분에 대한 어떤 니즈에 대한 부분을 말씀드린 거라고 생각하실 수 있을 것 같고요. 그에 연관된 솔루션들, 어떤 식으로 시험을 하셔야 되는지 이제 이런 부분들을 간단하게 소개를 드렸습니다. 예, 그래서 그 지금 나온 질문들을 이제 잠깐 말씀을 드려야 될 것 같은데요. 예, 뭐 아까 첫 번째 세션에는 질문이 그렇게 많지 않았던 것 같은데요. 갑자기 이렇게 많이 또 질문을 주셨네요. 고맙습니다. 그래서 첫 번째 그 질문에 대해서 답변을 드려야 될 것 같고요. 먼저 시작하기 전에 그 이번 세션에서는 이제 그 Q&A를 위해서 저희 쪽에서 이제 솔루션 프로덕트 매니저로 저희 로데슈바르즈코리아에서 근무하고 있는 김종원 매니저님이 지금 답변을 드릴 예정입니다. 그래서 인사 한번 하시죠.
네, 안녕하세요. 로데슈바르즈 김종훈이라고 합니다.
예. 그래서 질문 주신 내용들 첫 번째로 정영규님께서 질문 주셨네요. V1R 테스트는 보이스 룩백 테스트인가요? 데이터 트래픽 테스트인가요? VONR과 VOLT 차이점이 궁금합니다. 예, 어떤 식으로 말씀을 드릴 수 있을까요?
네, 보이스 루프백 테스트가 맞고요. 그 VONR과 VOLT의 차이점은 랏을 어디를 쓰냐에 따라서 다릅니다. 그러니까 백본에 있는 IMS 서버를 이용하는 건 동일한데 NR망을 이용하냐 아니면 LT망을 이용하냐 그 차이점밖에 없습니다.
예, 뭐 거의 이름 그대로 차이네요. VO는 똑같으니까
네.
NR이냐 LT냐 이제 그 백본 망이 뭐냐에 따라서 차이가 난다고 말씀을 해주신 건데요. 예, 그런 면에서 보면은 사실 큰 차이는 없을 수도 있을 것 같은데 어떻게 보면 스마트폰도 결국 전화기이기 때문에 이제 보이스에 대한 부분도 결국 필수적인 부분이 아닐까 이제 이렇게 생각이 되고요. 두 번째 질문으로 이제 5G, 6G의 차이점에 대해서 윤성원님께서 질문을 주셨네요. 속도만이 차이인 거냐? 이제 이렇게 문의를 주셨는데요. 아마 지금 그 위에 있는 이은미님께서 올려주신 코멘트는 지금 요 내용에 대한 그 연관된 코멘트로 주신 것 같아요. 근데 아마 제 생각으로는 이제 속도라고 하는 부분이 결국은 이제 가장 핵심적인 부분인 건 맞죠. 다만 이 6G라고 하는 부분은 아직 규격도 나와 있지 않은 상황이기 때문에 말씀드렸던 것처럼 정말 극초기 단계이다 보니까 현재로서는 정말 이것뿐인 거냐 아니면 더 어떤 활용성이 있을 거냐 이제 이런 부분들에 대해서는 조금 더 시간이 걸리지 않을까 싶습니다. 그래서 현재 나오고 있는 어떤 진행 상황이나 이런 부분들은 그 오늘 마지막 세션에서 또 한번 내용을 좀 깊게 말씀을 드릴 수 있을 것 같아서 그때 내용을 한번 더 보시면 좀 더 도움이 되지 않을까 이렇게 생각이 듭니다. 그리고 장상철님께서 저 질문 주셨어요. FR1이 7.16기가까지인가요? 라고 질문을 주셨는데요. 어떤가요?
네. 질문 주신 내용과 같이 언라이센스 밴드도 FR1에 포함입니다.
지금 다 7.125기가까지
네.
해서 예. 그래서 언라이센스 밴드로 지금 FR1이 그 지원을 하고 있는 상황이니까 뭐 이런 부분들은 앞으로 이제 관련된 어플리케이션을 참조하실 수 있을 것 같습니다. 지금 시간이 거의 12시가 다 돼가지고요. 아마 요 질문까지만 답변 드릴 수 있을 것 같아요. 그래서 여기 유두식님 맞으시죠? 영문으로 적어주셨는데 5G 밀리미터 웨이브 이동통신이 활성화되는 시기는 언제 정도로 예측되느냐라고 문의를 주셨네요.
근데 일단 밀리미터 웨이브 같은 경우에는 지금 국내 사업자도 아직 서비스가 안 되고 있는 상황이고 지금 미주 버라이즌 사업자만 지금 상용화가 시작된 상태인데 일단 주파수 특성에 따른 문제랑 그 다음에 활용도도 지금 떨어지고 있어서 활성화 시기를 좀 점치기는 좀 어려울 것 같습니다.
예, 특성상 좀 쉽지 않은 부분이 있다. 뭐 이런 정도 뜻이 될 것 같아요. 그래서 이런 부분들도 이제 계속적으로 앞으로 더 확장해 나갈 수 있는 그런 부분이 되지 않을까 싶습니다. 예, 지금 뭐 시간이 거의 다 돼가지고요. 지금 이 아래쪽으로도 지금 그 질문 주신 내용들이 보여요. 그런데 이런 부분들은 다시 한번 말씀드립니다만은 저희가 오늘 답변을 현장에서 못 드리는 내용들은 전부 취합을 해서 한꺼번에 나중에 또 메일이나 또 따로 연락을 드려서 회신을 드릴 수 있도록 그렇게 준비를 할 테니까요. 계속적으로 좀 궁금하신 부분들 편하게 올려주시면 뭐 내용을 저희가 드릴 수 있도록 하겠습니다. 예, 지금부터는 그래서 점심 드시고 오후 세션은 1시부터 시작을 하겠습니다. 그래서 점심 맛있게 드시고 1시에 다시 이어서 말씀드리도록 하겠습니다. 오전 동안 수고 많으셨습니다.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rode and Schwartz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. Our platform is designed to support over 20 gigabits per second. Last but not least, The ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the Internet, such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM Squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde & Schwarz has been synonymous with innovation and passion, quality and reliability. Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde & Schwarz SMW. For all your needs, the Rohde & Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde & Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 GHz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed, or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If two Rohde & Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, the SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rohde & Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standard's requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rohde & Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex, standard compliant signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. Its macro recorder does the job for you. While you operate the instrument, The recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a second RF path or a second baseband. Add fading and MIMO capabilities to cover the requirements of advanced standards. Choose the wireless standards you need. Each standard can easily be activated by an option key. Finally, you might end up with an instrument capable of simulating multi-user PUCCH for LTE, or even generating LTE advanced scenarios with carrier aggregation and all MIMO configurations defined by the standard. The Rohde & Schwarz SMW was designed to master wireless communications technology for a long time to come. Whatever goes up on your drawing board, the SMW will help make your visions come true, now and in the future.
Rohde & Schwarz is the leading supplier of test and measurement equipment for the wireless communications industry and all industries leveraging wireless communications, such as the automotive industry, industries adopting the Internet of Things. We are driving the technology evolution by providing state-of-the-art test solutions for 5G industries and ecosystem. R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Rohde & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rohde & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. Our platform is designed to support over 20 gigabits per second. Last but not least, the ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the Internet, such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM Squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde and Schwarz has been synonymous with innovation and passion, quality and reliability. Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde and Schwarz SMW. For all your needs, the Rohde and Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde and Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 GHz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If two Rohde & Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, the SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rohde & Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standard's requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rohde & Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex, standard compliant signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. its macro recorder does the job for you. While you operate the instrument, the recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a second RF path or a second baseband. Add fading and MIMO capabilities to cover the requirements of advanced standards. Choose the wireless standards you need. Each standard can easily be activated by an option key. Finally, you might end up with an instrument capable of simulating multi-user PUCCH for LTE, or even generating LTE advanced scenarios with carrier aggregation and all MIMO configurations defined by the standard. The Rohde & Schwarz SMW was designed to master wireless communications technology for a long time to come. Whatever goes up on your drawing board, the SMW will help make your visions come true, now and in the future.
Rohde & Schwarz is the leading supplier of test and measurement equipment for the wireless communications industry and all industries leveraging wireless communications, such as the automotive industry, industries adopting the Internet of Things. We are driving the technology evolution by providing state-of-the-art test solutions for 5G industries and ecosystem. R&S is committed to take the 5G industry forward. Our multiple solutions are developed to assure 5G success in new radio access technologies, including waveforms, channel sounding, millimeter wave, and massive MIMO OTA measurements. The current 5G test solutions address the growing demand for advanced applications developed by our collaboration with global operators, research institutes, universities, infrastructure vendors, chipset suppliers, and manufacturers. Our high-frequency and high-bandwidth signal generators and analyzers allow engineers to test new waveforms for both frequencies below 6 GHz and the emerging centimeter and millimeter wave spectrum. Our instruments can provide up to 2 GHz of bandwidth for a wide variety of measurements. Wireless technology is evolving quickly, and T&M equipment must enable 5G progress. Rohde & Schwarz has been dedicated to this challenge for decades and will continue to stay tuned.
Remember how complex end-to-end testing was in the past? That's what throughput settings with a communication tester used to look like. Rohde & Schwarz revolutionized this setup with our CMX. For a consolidated solution, we moved the entire setup into the tester. The advantage offered by the CMX is a pre-configured setup, ready for testing right away. The CMX offers a common user interface and a data testing solution for all applications, and support for IPv4 as well as v6. Let's take a closer look at the integrated services. With the CMX, you'll be able to test the most common Internet protocols and services. Its integrated FTP server enables up and download throughput tests for the file transfer protocol. The CMX also provides an HTTP server to test web browsing. For testing communication with the Internet and over-the-top applications in controlled 5G RF conditions, the integrated DNS server of the CMX is able to translate requested domains into IP addresses. Another important service is IP Multimedia Subsystem. It enables phone calls via IP networks. Via this server, different types of calls in LTE and 5G, as well as SMS and video calls, can be realized and tested. 5G technology defines new goals in terms of latency and high data rate services. Ping measurements can easily verify that the latency values are achieved. For active measurements of the max achievable throughput in 5G, the iPerf tool in the CMX generates traffic that allows you to monitor the data rate along the different layers, from physical to the IP layer. Bottlenecks between layers can be immediately identified and addressed. Are you worried about the extreme high data volume? There's no need to be. Our platform is designed to support over 20 gigabits per second. Last but not least, the ePDG interface enables wireless LAN offloading tests, securing smooth transitions from cellular networks like 5G and LTE to wireless LAN access points. The CMX offers a number of additional tools to facilitate the analysis and debugging of the IP data communication. IP logging, capture and storage of PCAP files with flexible filter options. IP impairments, controlled error insertion to simulate real IP network conditions. IP analysis, providing the overview of the established connections to the Internet, such as IP source and destination address, protocols, and certificates. All these services are integrated in the common graphical user interface of the CMX, the CM Squares. All tests and measurements can be operated manually in the workspace or built as test sequences in the integrated sequencer tool, or remotely controlled via XLAPI and Skippy interfaces. With the CMX platform, Rohde & Schwarz offers a unique integrated solution for application testing. It simplifies the test setup so you can concentrate on your DUT. Thanks to the full integration, the CMX delivers the best reproducibility and stability wherever you need it. With the application services inside the CMX, Rohde & Schwarz defines the benchmark for today's end-to-end testing. A fully integrated solution with best reproducibility and stability, and absolutely future-proof to cover the 5G demands of tomorrow, even today.
For 80 years, Rohde and Schwarz has been synonymous with innovation and passion, quality and reliability. Our new high-end signal generator remains true to these principles. Experience a new dimension in vector signal generation with the Rohde and Schwarz SMW. For all your needs, the Rohde and Schwarz SMW is just what you want it to be. Configure it as needed. The SMW high-end vector signal generator from Rohde and Schwarz is all you need to simulate the complex signal scenarios found in today's communication systems. It combines baseband generation with a fader, interference signal, and RF generator. Users will appreciate its easy-to-use touchscreen operation and the ability to configure options to suit any application. In the simplest case, you can take advantage of the SMW's excellent RF characteristics by feeding it with an external IQ signal of up to 2 GHz bandwidth. In this minimal configuration, the SMW is equipped with an IQ modulator and an RF front end. If you add the baseband option with up to 160 MHz bandwidth, the SMW can generate wideband digital signals using only built-in tools and without a PC. If you need to simulate fading or noise, you simply add them to the signal path. Another unique feature is that the entire signal chain can be duplicated within the instrument, up to 20 GHz in both paths. This two-path capability allows you to elegantly implement complex scenarios, such as carrier aggregation, multi-standard radio, and higher-order MIMO modes with just one SMW. Simplify your setup. Generate complex signals intuitively in a minimum of time and with minimum hardware. No matter how complex a communication system with both MIMO and interference signals may be, the SMW lets you confidently control all parameters. The large touchscreen displays the setup and serves as an intuitive operator interface. If, for example, you have a multi-carrier signal and need to add baseband signal B to the signal from path A, then you only have to drag and drop it into place. Frequency offsets and relative levels can be set in the baseband to create a realistic scenario. The resulting single or multiple carrier signal is available at the RF outputs. The result of the settings can be immediately visually checked. The SMW's preview monitors capture various parts of the signal in real time and generate different informational views. In this example, you see the spectrum of the configured dual carrier signal after the AWGN block. Space-saving icons are used for functions that are not always needed, such as configuration of the baseband inputs and outputs. The signals generated in paths A and B can be dragged and dropped to one of the instrument outputs. For example, you can drag the IQ signal from stream A to the analog IQ output B. The integration of a baseband, fader, and RF section and the multipath capability of the SMW solve many of the problems facing users of distributed solutions. In no time at all, higher-order MIMO scenarios such as 4x2 can be quickly and easily configured with just one SMW and no additional instruments. Even 4x4 MIMO, which used to require bulky hardware setups, is easy with the SMW. The SMW takes care of all baseband generation and calculation of the fading scenarios. The two additional RF paths that are required are supplied by two small SGS-100A vector signal generators. The SMW is now the core of a unique, compact solution for 4x4 MIMO scenarios. Bring reality to your lab. Utilize all the sophisticated technologies that are a feature of advanced communication standards. Advanced communication standards such as WLAN 11AC and LTE use diverse techniques to increase the data rate and also take advantage of the physical properties of the transmission channel, such as multipath propagation. Simulating these properties is quite demanding, but essential for testing under realistic conditions. The Rohde & Schwarz SMW masters this task perfectly in a user-friendly manner. It only takes seconds to completely configure a complex setup such as MIMO LTE, thanks to operating menus oriented to the standard and complete presettings for all important signal scenarios. For easier, straightforward handling of a 4x4 MIMO scenario, the SMW allows configuration from a single baseband block. The coupled sources setting turns the 4 basebands into a single operational element. Additional fading can be manually configured as needed, or conveniently set using one of the predefined standard scenarios. This LTE example demonstrates how easy this is. An informative path graph immediately shows the RF impact of the selected setup. The effect of noise can also be simulated in a next step. If two Rohde & Schwarz SGS-100A vector signal generators are connected to provide the additional RF channels needed for the 4x4 scenario, the SMW recognizes them via the LAN interface and automatically takes care of all the necessary settings. Make your device even better. The Rohde & Schwarz SMW's excellent RF performance lets you design your products to exacting specifications. The SMW's excellent specifications in all areas give you the margin you need to economically design and manufacture products to specification. The key to reliable measurement results is signal purity. With a specified phase noise of better than -136 dBc at 1 GHz and 20 kHz offset, the SMW impressively proves that it is high-end. Amplifier tests demand high output power combined with excellent signal performance. Not a contradiction for the SMW, with its specified output power of 18 dBm up to 20 GHz. This power, of course, should only show up in the wanted channel and nowhere else, which it doesn't thanks to the SMW's excellent adjacent channel suppression. When it comes to digital modulation, the error vector magnitude is the benchmark for signal quality. With an EVM of only 0.3% for a 160 MHz wide 256 QAM modulated WLAN 11AC signal, the SMW provides plenty of headroom, outperforming the standard's requirement by a factor of 8. You often need to know the precise power before and after a DUT. Just connect an NRP USB power sensor to the SMW, and this information is immediately available on the screen. Speed up your development. The Rohde & Schwarz SMW's intelligent tools let you concentrate on creative work. Thanks to the SMW's intuitive operation and short signal setting times, you can work full speed ahead. Even complex, standard compliant signal scenarios can be quickly and correctly set up with the test case wizard. The LTE test case shown here generates a 3-carrier signal consisting of the wanted signal, a CW interference signal, and an interfering signal to test receiver intermodulation. What usually requires 3 generators can be accomplished with just 1 SMW. Obtaining guidance or further information is easy with the SMW. The context-sensitive online help ranges from short statements to detailed background information, eliminating the need to consult the manual. Writing a remote control program normally is a time-consuming and error-prone task. Not so with the SMW. Its macro recorder does the job for you. While you operate the instrument, the recorder logs your inputs and automatically converts them to a Skippy remote control program. Grows with your needs. Make use of the SMW's high versatility to keep your signal source aligned with your demands. You set the agenda. The SMW is ready to follow. From early R&D to integration and verification. Start with what you currently need and expand the instrument's capabilities in line with your future demands. Begin with a classic configuration consisting of a single baseband and a single RF section. Upgrade the instrument with a
안녕하십니까. 로데슈바르즈코리아의 최지홍입니다. 예, 식사들 맛있게 하셨죠? 예, 오후 세션으로 다시 돌아왔습니다. 오전에 지금 두 개의 세션을 통해서 그 기술적인 해설 부분과 또 IP 스루프 퍼포먼스라든지 이런 부분에 대한 내용들을 이제 쭉 말씀을 드렸습니다. 그리고 이제 쭉 채팅 올려주시는 내용들을 보니까 뭐 질문도 이제 올려주시는 분들이 꽤 계시는 것 같아요. 그래서 그런 내용들도 이제 저희가 말씀을 드려야 되는데, 뭐 오전에도 잠깐 말씀드렸습니다만은 오늘 좀 시간이 타이트한 편이라서, 예, 그래서 저희가 중간중간에 최대한 뭐 답변을 드릴 수 있는 방법을 찾겠습니다만은 오늘 현장에서 지금 라이브로 답변을 못 드리더라도 추후에 저희가 모든 질문들은 다 취합을 해서 다시 여러분들께 답변을 드릴 예정이니까요. 필요하신 부분들은 언제든지 활발하게 문의사항 올려주시면 내용이 더 풍성하게 진행될 수 있을 것 같습니다. 예, 그래서 지금부터는 이제 오후 첫 번째 세션으로 제목은 Let's get ready for testing of 5G 터미널입니다. 먼저 발표자에 대해서 잠깐 말씀을 드리면 요그 콥이라고 하는 분입니다. 저희 본사 근무하고 있고요. 그 와이어리스 커뮤니케이션 마켓 세그먼트 매니저로 활동을 하고 있습니다. 그래서 기존의 뭐 5G 터미널에 대한 부분도 마찬가지입니다만 특히 또 우리 요즘 핸드폰 보면은 와이파이나 블루투스처럼 소위 논셀룰러라고 부르는 기술들이 많이 들어가 있죠. 그래서 이런 부분들에 대해서 특히 좀 많은 경험을 가지고 계시기 때문에 지금 이번 시간에 말씀드릴 내용은 뭐 블루투스라든지 와이파이라든지 뭐 이런 부분들, 그래서 이런 부분들이 또 어떤 식으로 스마트폰에 접목이 되고 있고 어떤 식의 어떤 시험 요구사항을 가질 수 있느냐 뭐 이런 얘기들을 좀 말씀을 드릴 거고요. 사실 내용으로 이따 오후 시간에 뒤에 보시게 되면은 이제 Empowering the Mobile Device라고 해서 이제 와이파이 6, 7 그리고 UWB에 대한 이야기를 말씀을 드리는 부분이 있는데요. 이쪽하고도 약간은 일맥상통할 수 있는 부분이라고 생각할 수 있을 것 같아요. 그래서 좀 단말에 대한 오버럴한 어떤 내용들을 본다, 이런 정도 개념으로 생각하고 접근해 주시면 좋을 것 같고요. 그래서 내용을 쭉 말씀을 드리고 뭐 오전에 했던 것처럼 동영상 시청하신 후에 비디오 시청하신 후에 관련된 내용으로 저희 쪽에서 이제 중간에 올려주시는 질문들 간단하게 답변 드릴 수 있는 부분들 또 찾아서 말씀드리고 이런 식으로 진행할 수 있을 것 같습니다. 예, 그래서 지금부터는 오후 첫 번째 세션 발표 비디오를 시청을 하시도록 하겠습니다.
Hello, welcome to the session Let's get ready for testing 5G terminals. My name is Jörg Köpp. I'm Market Segment Manager for Wireless Device Testing at Rohde+Schwarz. I would like to give you in this session a kind of teaser and a kind of introduction in the topic of 5G terminal testing, looking a little bit on the market, looking a little bit on the challenges in design and testing, and of course give you a brief introduction of our test and measurement solution. First of all, 5G is now, let's check it. Then looking a little bit about other technologies that we see very often on 5G terminals, like Wi-Fi, ultra-wideband or Bluetooth. And finally, let's test it. It will be exciting, looking on some test solutions. Let's start with 5G. If you look on typical reports, and I was looking here on the GSA report about the 5G ecosystem from June this year, we can see that we have a tremendous growth on the support of the device ecosystems for 5G. For example, 1 year ago in June 2020, we had 296 announced devices which are supporting 5G technology, mainly phones and CPEs, but of course also already modules and other devices. In the meantime, 1 year later, in June 2021, we have already more than 800 devices announced, and 350 of this are 5G commercial phones, 56 fixed wireless access CPEs, and also 46 modules which are commercially available. That means, in the meantime, the growth of the the number of devices were growing by 178%. And if you look how many vendors are providing this, these are 128 vendors which are announcing these devices, and overall 500 are commercially available. But availability of devices is one thing. The other thing is 5G now also meeting the customer expectations? And here the GSMA was making some survey and asking 5G users whether 5G is meeting their expectations. And the result is quite interesting because, or quite positive, 67% are saying yes, 5G is meeting my expectations. On the other side, 32% are saying no. What are the reasons? There are several reasons to say yes or no. Just looking on the speed. For example, 41% were saying yes, I'm satisfied with the speed that 5G is supporting. I'm quite happy with this. On the other side, 21% were saying no, I was expecting much more. This is not what I am expected. So that means, of course, 5G is now. We have devices, we're seeing more and more rollouts, but we have to look on now how we can really meet the customer expectations regarding speed and other criteria. I was also looking here on in a report from OpenSignal. OpenSignal users are a kind of community that supporting their data to OpenSignal, that you can see what is the customer experience of certain areas. For example, here for APAC, and I would like to take here one example in detail, it's South Korea, which is of course quite advanced, which is number one in the average 5G uplink speed with 380 megabit per second, and number 2 in these regions for the downlink speed with 30 megabit per second. And if you look also on the video, game and voice experience, they are more or less number 1 or number 2. Also interesting to see, if you think about the availability of 5G and the availability in terms of times, how often these users have access to the 5G networks, then they see here 27% of the time that they have access to the 5G network. Other countries, you see here, for example, Thailand, Taiwan, and also Japan, which are also quite good values, but quite different. For example, Thailand has not this high uplink speed, but compared to this, a quite high download speed, and have still a kind of good video and gaming experience. Japan, probably worthwhile to mention that at least on this survey, the time that they have access to a 5G network was quite low, with just 2%. So, as I said, we are still on the beginning, but it's quite exciting. If you are looking on the frequency bands, and it's the ongoing discussion, which are the most important frequency bands, the low, the mid, or the high bands, then we see that, especially if they would like to meet the customer expectation for speed today, and probably more important for tomorrow, that millimeter wave bands become more and more critical. And you see this also in the support of the ecosystems. 2 years ago, there were just 5 phones that are supporting millimeter wave technology. In the meantime, there are more than 100. And also for fixed wireless access, we see more and more devices supporting this. In general, we see more and more demand for additional spectrum, of course, which is a kind of very important resource for any wireless technology. For example, the trend for to go in the FR1 area also to this 7.1 gigahertz for unlicensed bands, also looking on additional bands in the range from 10 to 20 gigahertz, but also looking on even higher bands, higher than actual FR2 in the range of 60 gigahertz. So this is a continuous trend what we have to deal with, and of course this has related impact on test and measurement. If you are looking a little bit in the future, and here I'm referring to the Ericsson Mobility Report from June this year, no surprise, it's more or less stable, this kind of forecasts. In the year 2026, they are expected 8.8 billion mobile subscriptions, and in this time there will be probably still the majority in LTE, but a lot in 5G. Most interesting probably to mention that the 5G subscription are estimated to reach this kind of 1 billion threshold 2 years earlier than we saw this in 4G. That means the adaptation in the market, the drive of 5G is much faster than we saw this for 4G. And to add on this, when we're talking about 5G terminals, we are not only talking about phones, we are also talking about IoT. And there's a quite interesting trend in this area, and this is a little bit changes on the forecasts that we saw over the last couple of years. There's, of course, in IoT the legacy, which is 2G, 3G, IoT, very low power, very basic, very often just using SMS services for IoT. Then we have this massive IoT, the growth that we saw already the last years, and we will see even more grow in the coming years with LTE-M or Cat-M and narrowband IoT. What is new, or what was not expected so far in this size, was really the broadband IoT. Really IoT applications which need higher throughput, lower latency, and so on and so far, which is mainly served by 4G and 5G technology with eMBB and ultra reliability, low latency. And you see that, for example, in 2026, the majority of connections or subscriptions in this IoT is related to this broadband IoT. Quite interesting trend. Let's have a look now on some other technologies, or first of all, back to mobile technologies. I think you notice all the history of mobile technology, starting with 1G. I'm already old enough that I still remember on this, which was really focusing on making mobile phone calls, nothing more. Then we got the second generation, digitalization, SMS was coming, messaging. The third generation, much more related to web, and the fourth generation, really the full IP enabled with voice, audio, video applications, and so on and so forth. Change in 5G in the sense that now they are looking at much more applications beyond this, what the consumer is doing with the phone and with the internet. For example, starting with the beginning with massive machine-time communication and also ultra reliability communication, for example, for connecting a trash can or a robot or a vehicle or something like this. But this was not all. In parallel to this, we saw also that, for example, on mobile phones, in every generation, additional wireless technologies were coming in to improve the customer experience. For example, Bluetooth were coming on these devices very early to connect peripherals. I think we are only using these headphones now with Bluetooth connections to our phones and other peripherals. GNSS was very important for all this kind of map services, also coming on the phones already 20 years ago. And Wi-Fi, quite important, especially for the first smartphones. The real app and smartphone experience was mainly enabled by Wi-Fi. NFC for payment especially, and other security stuffs. And just recently we saw that ultra-wideband was entering the phones. And who knows what will coming in the next couple of years. Let's have a look on some of these technologies and what it means for 5G terminals. First of all, Bluetooth. Here you see that Bluetooth will still stay very relevant for mobile phones and also peripherals. It doesn't look like that it will be replaced by another technology, at least for the moment. The blue bars that you see here are more or less the shipment of Bluetooth-enabled phones, PCs, tablets, and so on, which is quite stable, of course. But the number of peripheral devices that will be connected to this kind of systems will constantly grow. And this is also related to some latest development in Bluetooth, especially Bluetooth Low Energy. For example, with the latest generation related to Bluetooth 5, to Bluetooth 5.1 and Bluetooth 5.2, we saw a couple of new features, improving the speed and the range, broadcast mesh features, something for location services, direction finding, and so on. And the latest version, something about power control, and probably most important, especially for the phone industry, about audio. What they were doing for audio? In Bluetooth, we had so far, at least by the technology, only supported by Bluetooth Classic. Now with Bluetooth 5.2, also Bluetooth Low Energy has a kind of native support of audio services with isochronous channels, which is also including, for example, support of hearing aids and also for broadcasting, so that you can use this in events and so on. And also introducing a new audio codec, the LC3, which is very efficient and provides low latency and so on and so forth. Then we saw in the last couple of years the trends for making, I would say, Wi-Fi more powerful by giving them more spectrum. So far we had just the spectrum in the 2.4 gigahertz band, quite crowded, quite small. Here Wi-Fi was competing with other technologies like Bluetooth, like Zigbee and so on and so forth. Then we had this 5 gigahertz band. But looking on the latest standards for Wi-Fi, which defining already the use of 160 megahertz channels, it was hard to find such kind of channels, so you were probably not able to use this kind of features because the spectrum was simply not available. And as we saw, especially also in this COVID period, home offices, homeschooling and so on, Wi-Fi was becoming more important. The regulator decided to open up more spectrum for this. You see here, for example, Korea was the first country in Asia releasing the 6 gigahertz band, FCC, Europe, and so on and so forth over the last couple of years. Based on the forecast that you see here from the Wi-Fi Alliance, we can expect that we will see more and more Wi-Fi 6E devices in the future. Of course, not every Wi-Fi device needs to support the 6 gigahertz. It's of course also additional effort and so on and so forth. For example, for IoT devices, for a couple of them, they will still operate in 2.4 gigahertz only. But if you would like to address the full power of this kind of technologies, you have to go to the 6 gigahertz bands. And how this looks like today, if you look on the landscape of Wi-Fi, 6 gigahertz band regulation on this map, and this is essentially the status of July 2021. There is a North American market quite advanced with Canada and US. We have Europe, South America, and also in Asia, as I mentioned before, in Korea. Essentially, there are three areas or three categories where the spectrum is used in the 6 gigahertz band. One is for very low power, which we see especially in Europe, for example, in Asia. This is more for device-to-device communication, which can be used outdoor and indoor. Then it's in standard which is used also across the world. In all this regulation, it's for low power indoor. This is a limited power and limited also just to use indoor. And then there's standard power, which is so far only available in North America by FCC and Canada, which is also requiring AFC and automated frequency coordination. That means the access point has first to ask whether they are allowed to use the spectrum by a database and then can use the full power and so on and so forth. So quite interesting trend and very important for future technologies in Wi-Fi. And future technologies in Wi-Fi is a good point. Let's have a look on the next Wi-Fi standard, which is Wi-Fi 7 or 802.11be, which is also called extreme high throughput. And what they are doing now, after the former Wi-Fi standard, Wi-Fi 6, was looking on efficiency, they are really looking on improving the throughput. And they are doing on the physical layer the usual thing. They're adding more bandwidth. For example, 200 megahertz channels are now possible. Also for this, you need more or less a 6 gigahertz bands. Otherwise, you cannot find 320 megahertz channels. Then they are going to higher order modulation, which of course needs related good RF conditions. Otherwise, this will not work. And of course, the related transmitters and receivers able to deal with this. And they are adding also the support of additional special streams from 8 to 16. This is the usual thing what we saw over the last decades in the development of Wi-Fi. In addition to this, they try to improve also the usability or the efficiency by introducing multi-resource units per user. In Wi-Fi 6, they introduced OFDMA and resource units. Now they make this a little bit more flexible. And then it becomes quite interesting what happens on the MAC layer. For example, they introduced multi-access point coordination in Wi-Fi 7. So that a station can, for example, communicate in parallel with 2 access points, or also that 2 access points coordinate which resource units or which beams they are using to a certain station. And multi-link operation, especially interesting for small devices, which are not able to provide 16 spatial streams, but which can run several links in parallel on different channels. Here is the support via a single MAC layer, for example, for a channel in the 2.4 GHz band, 5 GHz and 6 GHz band. This could be in parallel simultaneously in both directions or just in one direction. This will also improve finally the application throughput in Wi-Fi. If you are looking now on ultra-wideband, then we have to go a couple of years back in the history, because the original RF or radio communications was built on pulse radio. For example, here you see Heinrich Hertz with a kind of first tool or setup, lab setup to create electromagnetic waves. Also, Mr. Marconi was then sending the first letters via the Atlantic using pulse radio. After that, we saw pulse radio especially for radar systems, but now we see this a large adaptation in consumer devices, especially mobile phones. Let's have a short look a little bit on the environment. So it started more or less in the year 2002 that the FCC was opening this spectrum for ultra-wideband systems for radar, public safety and data communication applications. This was more or less a starting point for that what we saw now. Then there was a first standard related or driven by the Y-Media Alliance. Later, the IEEE was taking over and making the standard, which is still relevant for us, the 802.15.4a. Then we had some organizations like Ultra Wideband Alliance, the FIRA Alliance, and the OMLOGs. FIRA, very important for test and measurements, and Rode und Schwarz is also a member of the FIRA consortium because they are defining certification specs to ensure interoperability of ultra-wideband devices. Most relevant actually is the 802.15.4z standard, just released last year, because here they introduced the kind of ultra-wideband standard which meets actual application requirements, including secure ranging, which is also very important, for example, for the car connectivity consortium, which are using this technology for digital keys. If you look on the market for this, you also see a high growth, especially on the smartphones. I mean, the first smartphones were coming out in 2019. Supporting ultra wideband, we see now also more and more techs, more home devices, and so on and so far. And you see here that they're expecting really a high growth in this technology. So it will become a kind of common wireless technology on mobile devices like Wi-Fi, Bluetooth, and cellular technologies, I believe. Let's test it. It will be exciting. I was saying, let's have a look on this. If you think about on wireless technology evolution, design challenges, and finally about technology challenges, we are very often talking about higher frequency, wider bandwidth, higher modulation schemes, more spatial streams. I explained this just some minutes ago for Wi-Fi. We see the same in cellular technologies, of course. So we have to deal with this. This is a usual thing, but of course it becomes more complicated, especially if you going now with bandwidth to 500 megahertz, 300 megahertz, or if you go in frequency ranges in the microwave area with 6G, probably in the terahertz area. In addition to this, it becomes also more complex on these devices. We have this multiple technologies that these devices have to support. It is Wi-Fi, it is ultra-wideband, it is Bluetooth, it is 4G, it is 5G, and some more. And you have to deal with all the kind of interferences and so on and so far, how to integrate this in this small devices. Then you have support all these multi-bands. You have to support high band, mid band, low band. Sometimes you have to do carrier aggregation. That means you have two operators all together and so on. And we see also more and more antennas on the devices, multi-antenna configuration, also antenna arrays with beamforming and so on and so far, which makes this all more complicated and drives also the test and measurement demands. And not to forget, at the end of the day, and this is kind of loop to our beginning, it's all about customer experience. And the customer experience you can just verify in your labs, for example, if you look on dedicated application requirements. This could be the voice quality, it could be the video quality, it could be the gaming experience, latency for certain applications, power consumption, and so on and so far. This kind of end-to-end testing and application testing, verifying of application requirements becomes more and more important. I would like to add here some aspects which we will not address in the other sessions, which are really focusing on the topics that I explained before. If you look on the new 5G network architecture, then there is a kind of support of virtualization. This is that you have, for example, network slices with different categories and properties to support the different traffic and the different applications accordingly. This is one thing. And the other thing is, for example, mobile edge computing, that you have running your applications close to the base station or on the core and so on and so far. And the question, of course, is, if you think about the application requirements, how devices have to support this kind of stuff. Of course, the device has to know to which network slice they would like to connect and have to support the signaling and so on and so far. And has also to look how to deal with mobile edge computing and so on. Here, I think it's still a couple of things open, and we have to look how this will develop in the future and what it also means for testing of devices. Another aspect, and this is here highlighted as IoT, but it is also important for other things. A lot of applications can only be successful if the customers trust in this application, and this brings us to the topic of security. We from Rohde & Schwarz see that there is necessary to address three essential pillars on this. This is the network security, the device security, and the continuous monitoring of networks. And if you think about device security, then this means security by design, verified probably by certification. And here we are looking what happens in security certification for IoT devices and other devices, which is driven actually by a couple of organizations. And you have also to think about how to maintain this over the life cycle. And just to give you one example, this device security, you can think about, for example, the IoT security guidelines by the GSMA and also other documents. And what is important here is, for example, the endpoint security is very important. Endpoint security means secure communication of the endpoints with the applications. And here it is important that you also test this and also look what is your device doing. Is this really using only encrypted traffic? Is it only communicating to the servers that you are expecting? And just as one example, we are supporting with our inbuilt DPI engine in our CMX 5G tester the possibility that you can check this kind of behavior. You can check what kind of applications and protocols are used. You can look this IP connections, which cryptography algorithms are used, and also the details about. And you can also look on the geolocation of the endpoints, look in which areas to which countries your device is connecting, which gives you a lot of interesting information about what the security behavior of your endpoint and your application is. Finally, what we are doing, we are providing a comprehensive portfolio for 5G terminal testing for all phases of the product lifecycle, from the starting point for the RF measurements, probably on the chip level, on the device level, signaling test, testing the application performance, throughput, power consumption, and so forth. Everything about conformance test, regulatory conformance, GCF, PCF, and so on and so forth. Carrier acceptance testing, very important in some areas. Production testing, not to forget, and also service and repair. And on the button you see a couple of our devices and solutions that you will see later also in the other session. Our generators, analyzers, the CMX 500 as 5G tester, related OTA setup, test system TS8990, CMW100 and CMP200 for testing several wireless technologies in R&D and production, but also the CMP180 as a new product which is supporting now also Wi-Fi 6E and Wi-Fi 7, so looking for higher frequencies and higher bandwidth. So a full product portfolio, and this is just a selection to support you in 5G terminal testing over the whole product lifecycle. And it is, of course, not only about the wireless interfaces. We have also to think about everything around this, because these wireless radios or cellular radios are not standing alone in these phones or terminals. There is a lot of digital around. There is a lot about power, analog and clock, and so on and so far. Really complex designs, fully packed with very powerful hardware. And of course, you have to make sure that all this works together based on your requirements and so on. And we have also solutions for this. Just one example, or some examples, for example, vector network analyzers, ZNA, for a new scope, for example, the RTO6 or others. For the digital design, multi-domain analyzers, you can also use this for RF analyzers with the related software and so on. And not to forget power consumption, power supplies with power analyzer functions that we are supported with NGM. And with this, I would like to close this session, and I hope you are ready now for testing 5G terminals and for the other sessions, giving you much more details about our 5G test solutions and related test channels. Thank you very much. Enjoy.
예, 지금까지 오후 첫 번째 세션이었던 Let's Get Ready for Testing of 5G Terminal이라는 내용을 쭉 보셨습니다. 내용 보신 것처럼 그 5G 단말에 포함된 여러 다양한 기술들에 대해서 쭉 설명을 드린 부분이었었고요. 아마 꽤 재미있게 들으실 수 있는 내용이 아니었나 싶습니다. 지금부터는 간략한 서머리 부분하고요. 이제 질문 올려주신 내용들에 대해서 답변을 드리기 위해서 저희가 말씀을 드릴 거고요. 이를 위해서 저희 쪽에서 솔루션 프로덕트 매니저로 활동하고 계시는 저희 황재현 매니저님께서 같이 자리해 주셨습니다. 안녕하세요.
네, 안녕하세요.
예, 그래서 지금 말씀드렸던 내용들에 대해서 간략하게 정리 한번 해주시죠.
네. 지금 오늘 보신 내용은 전반부 부분에는 5G 시장에 대해서 우선 나와 있고요. 그래서 모바일 상황이 얼마나 증가했는지 그런 부분, 그리고 그 다음에 나온 부분이 이제 사용자 경험이 얼마나 향상되고 실제 유저들이 어떻게 느끼고 있는지에 대해서 5G 고객 경험을 확인을 했고요. 그 다음에 5G에 연결해서 다음 부분으로 다른 테크놀로지에 대해서 보셨는데요. 거기에는 이제 블루투스 부분, 블루투스가 이제 클래식부터 BLE 5.2가 되면서 오디오가 지원되고 하는 발전 현황을 보셨고, 다음으로 보신 부분은 와이파이도 이제 기존 레거시 와이파이에서 그 11BE까지 증가되는 그런 모습, 어떤 부분들이 차이가 있는지 그런 부분들을 보셨고요. UWB 이런 부분, GNSS, 그리고 그 모바일이나 이쪽에 적용이 가능한 여러 다른 테크놀로지에 대해서 보셨고요. 그 마지막 부분에 이제 요약해 드리는 부분이 저희 장비에서 이런 포트폴리오들에 대해서 테스트를 하시려면 어떤 식으로 어떤 장비를 테스트하시느냐, 그냥 간략하게 개괄적으로 보여드린 상황입니다.
예, 그 뭐 말씀 들으신 것처럼 오늘 뭐 여러 가지 주제에 대해서 다루고 있는데 시간 관계상 뭐 너무 깊게 또 말씀드리기는 좀 부족한 것 같아요. 그래서 이런 부분도 혹시라도 또 필요하신 분들 있으시면은 그 저희 로데슈바르즈코리아 뭐 오늘 지금 보신 것처럼 제 프로덕트 매니저들도 같이 자리를 하고 있으니까 관련된 내용으로 뭐 문의를 해주시면 좋을 것 같습니다. 예, 그래서 지금 뭐 그 채팅창으로 올려주시는 질문이나 이런 내용들을 지금 좀 보려고 하는데요. 예, 방금 장상철님께서 마지막 제품 관련된 제품 자료를 받아볼 수 있으면 좋겠다고 해주셨는데, 이런 부분들은 저희 쪽에서 한 번 더 그 말씀드렸던 것처럼 한 일주일 안쪽으로 저희 쪽에서 아마 또 메일로 그 관련된 내용들을 쭉 그 정리해 드릴 수 있을 것 같아요. 그래서 이런 부분들 저희 회신 드릴 수 있도록 준비를 하고요. 그리고 UWB에 대해서 윤성원님께서 우리나라에서 생소하다고 이제 그 질문을 주셨어요. 근데 사실 국내에도 이미 국내 제조사에서 차량에 적용을 하고 있는 상황입니다. 그래서 특히 이제 스마트키 같은 경우에는 UWB를 적용을 하고 있고, 해외 자동차 이제 수입차 제조사에서도 사용을 하고 있는 상황입니다. 그래서 실제 시장이 물론 뭐 이름 자체는 생소하실 수 있겠지만은 이미 사용을 하고 있는 기술이다라고 보실 수 있을 것 같고요. 동일하게 또 윤성원님께서 또 질문을 올려주셨네요. 와이파이 7 공유기에 대해서 2.4기가, 5기가, 6기가 3개 네트워크 지원되는 것인가요? AP가 2개를 생성하는 것인가요? 이런 내용들 문의를 주셨습니다. 이거 어떻게 답변을 좀 해주시죠?
네, 이게 교육 자료를 되게 열심히 봐주신 분 같고요. 제가 봤을 때는 이제 멀티링크 오퍼레이션 부분에 대해서 문의를 하시는 것 같은데요. 일단은 뭐 와이파이 7 공유기에서는 이론상 이제 피지컬 레이어 상에서는 2기가, 5기가, 6기가 대역의 네트워크를 같이 연결을 하실 수는 있다고 나와 있고요. 근데 그게 연결됐을 때 뭐 제가 예상하기로는 이제 QoS 부분은 이제 2.4기가 대역의 신호가 양호하다면은 양호하고 5기가, 6기가가 신호가 나쁘다. 그런 상황이면 2.4기가에 좀 더 많은 데이터가 가는 식으로 동작하지 않을까 생각이 됩니다.
예, 뭐 특히 와이파이 7 같은 경우에는 지금 현재 얘기 나오는 부분들이 이제 추후에 더 많은 어떤 활용 예나, 특히 그 우리가 뭐 5G를 이야기를 합니다만은 뭐 5G를 3GPP 기술 규격으로 만들고 있다라고 얘기를 하더라도 뭐 와이파이가 그렇다고 해서 손을 놓고 있는 건 아니잖아요. 그래서 계속적으로 이제 와이파이도 확장을 하기 위해서 뭐 어떤 새로운 어떤 그 개선점을 계속 찾고 있는 상황이고 계속 발달하는 부분이기 때문에 이런 부분들은 좀 더 내용을 같이 보실 수 있으실 것 같고요. 말씀드렸던 것처럼 그 관련돼서 혹시라도 어떤 테스트 솔루션이라든지 이런 부분들이 필요하신 경우에는 저희 쪽에 좀 더 자세한 자료를 또 따로 말씀드릴 수도 있을 것 같습니다. 예, 그리고 좀 더 밑으로 내려볼까요? 지금 오후 세션에서 답변 주신 거, 질문 주신 거 이 정도고요. 뭐 시간이 조금 있기 때문에 그 오전에 주셨던 질문을 잠깐 좀 더 내려보면은, 예, 여기 또 있네요. 저 김주만님께서 문의를 주셨어요. 통신 사업자 입장에서는 볼테, EPS 폴백, VONRC 각각 설정에 따른 성공률이나 모스 측정, BQC, CBQ, SIP 셋업 타임 등의 그 음성 영역의 KPI 측정으로 볼 수 있는데요. 솔루션이 있을까요? 이제 문의를 주셨네요. 측정 솔루션에 대한 문의를 주신 것 같아요. 네, 이 부분은 이제 그 오늘 두 번째 세션에서 이제 연결되었던 부분이긴 한데요. 지금 오전에 말씀드렸던 세션, 두 번째 세션에서 말씀드린 부분들은 이제 개별 단말에 대한 어떤 시험 항목, 시험 지원 솔루션이라고 생각하실 수 있습니다. 이건 어디까지나 어떤 그 실험 환경, 뭐 랩에서 시험을 하신다든지 또는 그 양산 라인에서 시험을 하시는 경우로 이제 상정을 해서 준비되는 솔루션이라고 할 수 있고요. 지금 말씀드린 내용은 어떻게 보면 이제 실제 필드에서 시험을 해야 되는 내용이기도 합니다. 그래야 이제 이런 내용들을 가지고 사업자 네트워크의 어떤 퍼포먼스라든지 이제 이런 부분을 연결시켜서 생각할 수도 있는 부분이거든요. 실제로 현장에서 이제 사용하게 되는, 그래서 실제 라이브 네트워크를 기준으로 시험을 하는 경우에는 오전에 보셨던 그런 그 솔루션들보다는요, 이제 실제 필드에서 시험하는 솔루션이 따로 있긴 있습니다. 그래서 예를 들자면은 실제 뭐 단말을 이용해서 음성 호우라고 보통 표현하죠. 그래서 콜을 붙이고 그 콜 상태에서 음성 퀄리티에 대한 측정, 지금 적어주신 모스 측정이 이제 그런 경우가 되겠죠. 이런 모스 측정과 같은 그 음성 퀄리티에 대한 부분을 이제 실제 측정을 하고 이런 거를 이제 실제 그 점수로 표기를 해드리는 이런 부분들도 솔루션이 충분히 가능해서 실제 상용화되어 있는 부분이고요. 저희 쪽에서도 이제 그 관련된 부분을 저희 쪽에는 이제 모바일 네트워크 테스팅이라고 부릅니다. 이런 분야로 해서 솔루션들을 제공을 하고 있는 상황이기 때문에 이런 부분들은 필요하시다면은 또 저희 쪽에서 좀 자세한 내용이나 세션을 또 마련할 수 있지 않을까 싶습니다. 그래서 지금 주신 내용에 대해서는 일단 솔루션이 있다라는 정도로 정리를 해드리는 게 뭐 시간 관계상 어쩔 수 없이 이제 이 정도만 말씀을 드려야 될 것 같고요. 한 1분 정도 남았네요. 한 번 더 내려가 볼까요? 네. 예, 프라이빗 5G, 6G에 대한 내용 말씀을 해주신 부분 박완주님이시네요. 예. 프라이빗 5G라고 하는 부분이 이제 국내에서는 5G 특별망이라는 이름으로 아마 나와 있을 겁니다. 저희가 기억하기로는 아마 올해 초였던 걸로 기억을 하는데요. 이제 과기부, 지금 제가 정확히 이름이 기억이 안 나는데 과기정통부가 되는 거겠죠? 나왔던 그 내용 중에서 이제 5G 특화망이라는 이름으로 해서 나와 있는데 우선 말씀드릴 부분은 주파수 대역이 이제 와이파이하고 좀 다른 걸로 기억을 합니다. 그래서 이런 부분들이 이제 어떻게 보면은 약간 그 특정하게 이제 생성이 되는 어떤 그 마켓, 시장이라고 해야 될 것 같은데요. 아마 제 생각으로는 이제 5G, 프라이빗 5G는 이 와이파이하고는 어떤 그 기본적인 무선 연결이라는 점에서 비슷하겠지만은 활용에 대한 면에서는 서로 지향하고 있는 점이 좀 다른 것 같아요. 그래서 이런 부분들에서 봤을 때 아마 서로 이렇게 시장을 서로 다른 쪽에서 마켓을 어드레싱을 하면서 쭉 계속 유지가 되는 그런 상황이 되지 않을까 싶은데요. 특히 6G에 대한 부분은 좀 더 이제 특히 5G 프라이빗 5G도 마찬가지입니다만 스마트 팩토리와 같은 부분을 통해서 계속 현재 논의가 되고 있는 부분이기 때문에 이런 부분들은 조금 더 시간을 두고 보시면 이런 어떤 측면에서 서로 비교가 또 가능한 부분이 생기지 않을까 이렇게 생각이 됩니다. 예. 일단 그래서 여기까지가 일단 그 오전 세션 질문까지 포함해서 저희가 좀 더 말씀을 드린 부분이고요. 지금 시간 관계상 뭐 나머지 아까도 말씀드렸습니다만은 나머지 다른 저희가 답변 드리지 못한 내용들은 또 이어서 그 저희가 말씀을 드리거나 혹은 추후에 또 따로 말씀을 드릴 수 있도록 그 답변을 드릴 수 있도록 그렇게 준비를 하겠습니다. 예, 그래서 지금 여기까지가 이제 그 오후 시간을 포함을 해서 이제 관련된 내용으로 말씀을 드린 부분이고요. 지금 40분부터는 이제 지금 약간 넘어가려고 하고 있는 것 같은데요. 그 잠시만요. 죄송합니다. 예, 네 번째 세션이네요. 죄송합니다. 예. 네 번째 세션으로 NR New OTA 테스트 매트릭이라는 주제로 해서 내용을 말씀을 드리겠습니다. 발표해 주실 분은 저희 본사의 하인츠 멜라인 씨고요. 이분은 저 테크놀로지 매니저로 저희 본사에서 근무하고 있습니다. 그래서 아마 OTA 측정에 대해서 굉장히 깊은 부분을 말씀을 드릴 수 있을 것 같아요. 이론적인 백그라운드가 풍부하신 분이셔가지고요. 그래서 혹시라도 OTA의 어떤 이론적인 배경이나 어떤 그 구체적인 측정 메소드에 관련된 부분들이 어떤 그 테크니컬한 백그라운드가 필요하신 분들이라면 아마 크게 도움이 되실 수 있는 그런 내용이 아닐까 싶습니다. 그래서 관련된 내용 보시고 또 저희 다시 한번 세션 끝날 때쯤에서 Q&A로 다시 돌아오도록 하겠습니다. 지금부터 비디오 보시겠습니다.
Hello and welcome to this session entitled NR New OTA Test Matrix. This presentation will discuss about novel test matrix and test needs alongside with the introduction of millimeter waves in 5G mobile communications. My name is Heinz Millein, Technology Manager with RNS, with focus on wireless communication test systems. I am based in Munich, Germany. The fostering of the millimeter wave frequency range, alongside with the introduction of the 5th generation of mobile communications, also known as NR or New Radio, requires new radiated or over-the-air, in short OTA, test methodologies and metrics. This transition from the conducted measurement domain towards a wireless domain will be highlighted with this presentation, based on a few examples. First of all, we will have a look at the transmit power measurement metric, as it was required to be reconsidered along with the transition from the conducted measurement domain towards the radiated measurement domain. The second example is about an OTA-specific system performance metric, which is described as the spherical coverage of a mobile device. This metric has been introduced by 3GPP for user equipment conformance testing purposes and is maybe the most comprehensive radio system performance parameter from an operator's perspective. The third example is about a new approach to create virtual conducted test conditions, which is required in particular when we need to control the OTA radio channel characteristics. For example, the creation of multipath conditions to test the receiver performance in a true simulated environment. So let's start with the transmit power measurements. So far, we are mainly familiar with the conducted power measurements in different domains. At least since the introduction of GSM, we are used to measure a mobile phone's transmit power in the time domain and the spectral transmit power density in the frequency domain. Furthermore, the third generation CDMA technology taught us to consider power in the code domain. Now, when we need to measure power over the air, we still are interested in all these domains, however, with a spatial perspective which brings in the dependency of the transmit signal's direction of departure. This introduces the spatial measurement domain based on a virtual sphere around the transmitter under test. This kind of radiated power measurement is not entirely new. It has been developed for the assessment of antenna patterns in particular a long time ago. For instance, for the measurement of spatial antenna transmit patterns illustrated here for a standard gain horn antenna. The entire conducted feed power of a radiating device is spread into its surrounding space when neglecting any antenna mismatch or other radiation losses. Consequently, any measurement antenna, such as a standard gain horn antenna or a dipole antenna, will capture a fraction of the entire feed power only, depending on its position on the virtual measurement sphere. So, when we are interested in the amount of the total radiated power, known as the TRP, we need to scan the entire sphere around the transmitter to collect all radiated power fractions. The starting point for the measurement of the total radiated power, which corresponds basically to the conducted antenna feed power, is of course the electromagnetic wave radiating that power. Thus, the total radiated power can be expressed as a closed surface integral of the magnitude of the vector product of the electrical and magnetic field components E cross H. In other words, we accumulate the directional power fractions spread towards all possible directions of departure from the transmitter's perspective. In far field distance, this integration becomes more simple, as the pointing vector E cross H becomes more simple. The E and H field are orthogonal in the far field, and the field components are simply connected by the known free space impedance. Thus, it is sufficient to measure the electrical field component in far field distance only, which simplifies measurements significantly. This ends up in the integration of EIRP measurements using an appropriate probe antenna, applying a regular sphere as the sampling surface with the transmitter under test in the sphere center and a radius meeting the far field criterion. The integral to calculate the total radiated power covers the full 360 degrees azimuth range and 180 degrees elevation range. So far, this approach is taken from classical antenna pattern measurements. However, it still is pure maths. In a realistic setup, however, we can collect a finite number of EIRP values only. Therefore, we need some numerical approximation of that TRP integral. So far, the numerical approximation was straightforward as shown here. It is a sinus of theta weighted accumulation of discrete EIRP samples collected over a full spherical scan. By the way, this sinus theta weighting is simply a compensation of the different grid point densities near the poles or near the equator of a virtual measurement sphere. The sphere around the transmitter is typically scanned by a constant step-size grid collecting the EIRP samples along the azimuth angle phi and the elevation angle theta. This approach is the classical one for antenna pattern measurements, where we typically know what kind of radiation characteristics we can expect. But this numerical approximation may fail when we don't know anything beforehand about the transmitting characteristics, in particular looking at highly directive antennas as they are required for 5G millimeter wave communication. If, as we can see here, by accident, the main beam of the antenna under test or the device under test points towards the poles of the virtual measurement sphere, that is theta equal to 0 degrees or theta equal to 180 degrees, a big portion of the power would be ignored due to this sinus theta weighting in our approximation. Thus, this approach is not really suitable for conformance measurements where the black box approach applies, which means we don't know anything about the device under test and in particular its transmit characteristics beforehand. And we cannot take the risk to reject a device due to such obvious approximation uncertainties. (3GPP), the 5G standardization body, with significant contributions of RNS, by the way, identified this problem in a quite early stage and recommends a quite simple solution. Instead of using this classical constant angular step size grid, we scan the sphere around the device using a constant density grid, as illustrated here, which means the samples are evenly distributed across the spherical surface, this virtual spherical surface, and not across the individual azimuth or elevation axis. Modern high-speed and high-resolution positioning systems are allowing this approach. The numerical approximation is simplified by doing so, and we don't need to weight the measurements due to the grid pattern anymore. Consequently, we avoid fully or totally this risk of ignoring significant power portions by accident for an a priori unknown transmit power pattern, which finally reduces the risk of wrong assessments significantly. The second example I want to talk about is about a unique OTA metric that is not applicable in the conducted world at all. and not known there. The range of solid angles a transmitter can cover is of important interest from the network operator's perspective. To achieve a minimum spherical coverage, a single antenna or antenna array is not sufficient, as we will discuss now. So millimeter wave frequency operation, as we know, requires high directional antenna systems in order to compensate the free space path loss between the base and mobile station in particular. So there is a need to implement antenna arrays with high gain in our devices. However, this comes along with a quite limited spherical coverage. So the bigger the gain or the bigger the directivity, the lower or smaller is the spherical coverage. On the other hand, the randomness of a mobile radio channel requires a large spherical coverage because, for instance, the direction of an incoming signal and the device orientation at the same time is pretty much random, as you can imagine. So therefore, in that sense, an isotropic antenna transmit or receive characteristics would be needed. So as usual, again, we have contrasting requirements to be met at the same time. So consequently, in the device, multiple cooperating antenna arrays are needed in conjunction with some high-speed beam adjustment algorithms. And to test exactly this performance of this cooperation of the antenna arrays and the beam adjustment algorithms, 3GPP has introduced the spherical coverage requirement. And in fact, the spherical coverage requirement applies to both the transmitter and the receiver. And obviously, the spherical coverage is a statistical metric, in particular due to the randomness of the environment. And the constant density grid that we have just discussed a few minutes ago is the preferred approach because it avoids the need for any weighting of measurement values. Spherical coverage is a statistical metric dealing with the random distribution of actual measurement values collected across this virtual measurement sphere. Let's discuss this with the example of EIRP, so transmitter power measurements, we have gathered with a constant density grid, for instance. The frequency distribution of the actual power measurements illustrates how often a certain power value, for instance within an interval size of say 1 dB, has been measured. In statistics, this corresponds to the approximation of the probability density function, PDF, of that random variable EIRP, as we can see here on the top left corner. Now, from that starting point, we can derive the so-called cumulative density function, CDF, of the same EIRP measurements, which allows us the definition of conformance limits. As we can see here in the formula, the CDF provides us the probability that a given random variable, in our case, for instance, the EIRP power measurements, does not exceed a certain threshold or limit. So therefore, it is suitable perfectly to specify an upper bound for a requirement. On the other hand, the complementary CDF, the CCDF, provides us the probability that a given percentile of a random variable does not drop below a given threshold. Therefore, the CCDF is pretty much suitable to specify lower bounds for requirements. Typically, transmit power shall not exceed given limits, for instance due to regulatory limits, and therefore the CDF of EIRP measurements is suitable to specify spherical coverage conformance requirements for transmitters. On the other hand, the receiver sensitivity level shall typically not drop below a certain limit, which means that the CCDF of measured receiver sensitivity levels is the right metric to specify spherical coverage conformance requirements for receivers. 3GPP, the standardization body, has therefore introduced spherical coverage requirements for the transmitter based on the CDF and spherical coverage requirements for the receiver based on CCDF. To give you an idea why the spherical coverage is really a comprehensive system parameter rather than a single RF component parameter, we see here a set of spherical coverage measurements for different antenna configurations on the left-hand side and different form factors on the right-hand side. To describe the different performance, you may look at different percentiles. For instance, the 50 percentile for two different antenna configurations, like the blue and the black one on the left-hand side. They both provide the same maximum output power of approximately 23 dBm. However, their spherical coverage is different when we set a 50 percentile requirement. The 50 percentile of the blue sample remains below approximately 9 dBm, while for the black sample, the 50 percentile threshold is almost 15 dBm. So the spherical coverage of the black sample appears much better than the blue sample. These measurement samples emphasize the influence of not only individual electrical RF components or the antenna itself, but also all other design aspects of the entire device. So this slide shows an example of an RNS contest-based test system transmitter spherical coverage measurement for a 5G user equipment. On the left-hand side, we see the three-dimensional transmit pattern from different angles. On the right-hand side, the cumulative density function of the 400 samples taken across the virtual measurement sphere using a constant density grid. We can see that the measurement spread is about 24 dBs. So the lowest and highest measured EIRP are approximately 24-25 dBs apart. And the 50 percentile value in this example would be approximately 14 dBm, which would then correspond or would then be compared against the limits given by 3GPP with respect to the spherical coverage. So let's have a look at those limits. 3GPP specified various radiated transmitter output power limits for conformance assessment, depending on the device's power class. This includes for it the different FR2 frequency bands, for instance the maximum total radiated power, which is here in the third column, and this basically corresponds to the conducted power measurements we are used to. So TRP, the total radiated power, basically corresponds to the antenna feed power minus any mismatch or implementation losses. However, other purely radiated limits are specified on top, which we are not used to from the conducted measurement world, such as the minimum peak EIRP value here in the second column, which sets the minimum expected gain of the transmit antenna implementation, as well as a maximum EIRP, which is possibly or probably derived from regulatory limits in particular. And finally, there is this spherical coverage requirement here in the fourth column, specifying a limit for a certain percentile, here in this case for 85 percentile, of all power measurements across the entire virtual measurement sphere. So power class 1, which is shown here, or the so-called fixed wireless access devices, are designed to be highly directive. Therefore, full spherical coverage is not the main goal, as those devices are used for fixed wireless access based on a kind of radio link between the device and the base station. Thus, the majority here of 85% of directional EIRP measurements shall not exceed a certain limit, while the residual directions may, to maintain the radio link with the base station, however, still limited by the maximum EIRP value. On the other hand, power class 3 devices or handheld devices, so typical smartphone devices, are designed for a good average coverage in any circumstance. So therefore 3GPP has specified a 50 percentile requirement with respect to its spherical coverage. Finally, other devices come with different spherical coverage requirements as summarized in these tables. We do have 4 power classes at the moment for 5G devices, and those are listed here in the 4 different tables. Receiver spherical coverage requirements are setting lower limits accordingly, depending on the bandwidth. Again, FWA devices are expected to be highly directive also from the receiver's perspective. Thus again, an 85 percentile requirement is specified, the same as for the power class 1 transmitter. Again, power class 3 devices are expected to have an average spherical coverage expressed with a 50 percentile CCDF limit. Power class 4 devices are expected basically to get as close as possible to an isotropical coverage pattern expressed by a 20 percentile CCDF lower limit. Finally, we discuss a measurement approach where we need to manipulate the OTA environment in a way to create quasi-conducted test conditions. It's about the tap delay line modeling of multipath environment, as it is required in particular to test the receiver's baseband performance. Just to recall the way how tap delay line models simulate a multipath channel. Based on channel sounding measurements, we gain the environmental specific channel impulse responses in a time domain function. Such measurements basically provide the basis for the development of such tap delay line channel models, where each echo or each major echo is represented by a delayed, attenuated pulse with a certain statistical behavior. This type of model approach, a simple baseband domain simulation of the multipath channel. And 3GPP developed a lot of tap delay line multipath models so far for the conducted test environment. And in order to reuse them, or to be able to reuse them in an OTA environment, 3GPP decided that with some means the test environment should come back, the OTA test environment should come back somehow to a kind of conducted test environment. And they really call it into a virtual cable environment. So let's recap. As long as we can test conducted, a baseband channel emulator prior to the output of a base station emulator has been sufficient. So now, however, in an OTA environment, there is already, let's say, kind of test setup and device under test antenna configuration specific multipath channel, known or called here the OTA channel A. And this channel we don't have under control yet, or beforehand. In the typical case of two orthogonal downlink and receive antennas, say two orthogonally polarized antennas, we end up in such a 2x2 channel matrix A. And this channel matrix, unfortunately, is unknown. And as it is also related in particular to the UE's receiver antenna configuration. So this is not only depending on the test environment, it's also depending on the device under test, I'm afraid. Now, as we want to create a known, reproducible, comparable multipath environment for testing the receiver's baseband performance and using a baseband channel emulator, we have to get rid of this unknown and unwanted OTA channel, as it would basically manipulate the wanted multipath emulation in an unknown way, which is not acceptable for conformance testing in particular. By the way, 3GPP clearly requires this approach for any kind of receiver performance test, and they really call it a virtual cabling approach. However, they unfortunately they didn't specify in detail how to achieve this condition, but they request that the UE shall support setting up such conditions to come up with this kind of virtual cabled test environment, and they required the UE vendors to provide dedicated per antenna branch power measurement reports, which are typically, or which are not part of the default radio communication. Those measurement reports required on top by the UE vendors to support this kind of measurement are called or known as the reference signal receive power per branch value, in short RSRP-B. So to compensate the OTA channel matrix, basically the approach is to implement a kind of pre-equalization or calibration matrix before our OTA channel matrix. So let's call this calibration or pre-equalization matrix G. So, and to design this calibration matrix, or to feed this calibration matrix with the right values, we would need knowledge about this actual OTA channel matrix A. In order to create a kind of an identity matrix with the combination of the calibration matrix G and the channel matrix A. However, to get knowledge about this downlink channel matrix A, because in the end it's a downlink channel matrix, we need some feedback from the receiver, and unfortunately that receiver is in the device under test. So the best way, of course, would be if we would get the complete complex knowledge of the channel matrix, or the channel measurements by the device under test, and feed it back to the test equipment, so we could use standard equalization solutions like zero forcing or minimum mean square error based equalization methods. However, the only thing we get back from the device under test are these RSRPB values, so the reference signal receive power values, and they come on top of that with a limited resolution of 1 dB only. So the problem we have to solve gets even worse due to the fact that the information we have available is not sufficient to use standard equalization solutions, so we have to go for a different approach. And the different approach means that we simply have to rephrase the goal based on the information we have. And that information is, as we said, the RSRPB values with limited resolution as a feedback from the device under test. So due to the lack again of the really required or the full required information, we cannot compensate this OTA channel matrix entirely, but we can try to minimize the crosstalk and isolation, or to minimize the crosstalk, or in other words, to maximize the isolation in the combination of the two matrices G and A. And in maths, basically, we have now this kind of optimization task to minimize the crosstalk with the existing means or screws we have, like phase shift and gain balance from the G and B emulator's perspective. As this example shows, this kind of virtual cable calibration with the approach we have just discussed really gains significant improvement. We can see here the two different receiver paths from the mobile's perspective, and by phase shifting the signals, the relative phase between the downlink signals, we really can modify or basically optimize the isolation between the two receivers. And in this example, we see we could gain up to 90 dBs of isolation between the two receivers with the right phase shift. And on top of that, with additional power balancing, we can even gain a couple of dBs more in that respect. So this is the approach, basically, as it is also offered by Rode and Schwarz solutions, in order to create this kind of virtual cable connections and to offer 3GPP compliant conformance testing. So this concludes my presentation, and just a brief summary on what we have talked or discussed so far today. So we have seen that conducted measurement metrics do not necessarily work for OTA measurements. So there was a need in some cases, for instance, for adaptations. One example was for such an adaptation or transformation from the conducted into the OTA space, the power. So we transformed the conducted power measurement into a total radiated power measurement, which, as we have seen, is much more complex and much more time consuming. On the other hand, we have seen that some metrics we have been used to, like receiver performance under multipath conditions, require this kind of virtual cable connection. And this is what we have discussed. And we have seen also a metric that is unique for radiated measurements, and that was spherical coverage. And finally, there was a need to ask the device under test to support certain measurements, in particular to ask the UE to report its receive or reference signal receive power per branch back to the test system or to the base station emulator to support the setup of a virtual cable connection. So this concludes my presentation. I want to thank you for your attention and hope to see you soon in person again.
네, 지금까지 그 오후 두 번째 세션이었죠. NR New OTA Test Matrix라는 제목으로 내용을 쭉 보셨습니다. 그 자막 작업을 하고 그러면서 이제 저희도 이 동영상들을 쭉 봤었는데요. 뭐 제 개인적으로도 이번 좀 전에 보셨던 세션이 사실 좀 가장 내용이 깊었던 내용인 것 같아요. 뭐 어떻게 보면은 좀 강의 같기도 했었고요. 그래서 좀 들으시는 분들도 좀 어떠셨는지 잘 모르겠습니다. 어쨌든 그 테크니컬한 백그라운드를 위해서 굉장히 그런 부분들을 보실 필요가 있으신 분이었다면 굉장히 도움이 되는 내용이 아니었을까 이제 뭐 그렇게 생각을 하고 있습니다. 관련돼서 이제 그 아까 세션에서 이제 내용 들으신 부분들 뭐 서머리 해드리고 이제 그 답변을 드리기 위해서 저희 로데슈바르즈코리아에서 그 프로덕트 지원팀에서 그 팀장으로 활동하고 계시는 저희 안수현 매니저님을 자리에 같이 함께 모셨습니다. 인사해 주시죠.
안녕하십니까, 안수현입니다.
예, 그래서 지금 그 쭉 내용을 보셨고요. 말씀드렸던 것처럼 좀 강의같이 좀 어려운 내용이 아니었던가 하는 생각도 좀 들긴 드는데요. 한번 어떻게 좀 간단하게 요약 한번 부탁드리겠습니다.
네, 이번 세션은 그렇게 좀 최종 매니저님께서 말씀드렸던 것처럼 좀 이론적인 부분들이 좀 많이 소개가 돼서 좀 다소 좀 힘드셨을 수도 있는데요. 일단 이제 간단하게 말씀을 드리면 5G FR2 쪽은 이제 OTA 환경이다 보니까 기존에 이제 수십 년간 이제 진행했던 컨덕티드 방식하고는 많이 다릅니다. 그래서 그 부분에서 주의해야 될 좀 사항을 몇 가지를 이제 요 강의를 통해서 말씀을 좀 드린 사항입니다. 뭐 간단하게 또 추가적으로 말씀을 드리면 일단은 이제 그 기존의 OTA도 이제 TRP 메저먼트 쪽 부분이 있는데 그 일반적인 이제 TRP 메저먼트하고 좀 약간의 차이점을 그 컨스턴트 덴서티 방법이라는 소개가 하나가 있었어요. 이제 그 부분이 좀 기존의 TRP 메저먼트하고 다른 부분을 좀 소개를 해주셨고, 그리고 이제 중점적으로 이제 CDF 메저먼트 쪽이 좀 소개가 되어 있어요. 아무래도 이제 빔포밍 방식을 쓰다 보니까 기존의 그 LTE까지는 4G까지는 안테나 패턴 자체가 등방성 안테나하고 비슷한 형태로 뭐 이렇게 방사 패턴을 유지를 하다 보니까 어느 지점에서 측정을 하더라도 그 문제가 되지는 않았어요. 근데 5G FR2 쪽은 특정 방향으로 이제 빔이 형성이 되다 보니까 그 TRP 메저먼트 하는 방법이라든가 CDF 메저먼트가 좀 그 스페리컬 커버리지하고 이제 관련된 부분이긴 한데 그 부분이 지금 요구가 되는 부분이 있어서 아마 그 부분에 대해서 좀 집중적으로 요 세션에 대해서 소개를 해드리다 보니까 약간은 좀 기존하고 좀 다른 방식의 이제 측정이나 아니면 이론이 적용이 돼서 다소 좀 버거운 세션일 수도 있어요. 그리고 뭐 여기서 소개된 내용 말고 OTA, FR2 OTA 환경에서 검토를 해야 될 부분들은 요 소개된 내용 외에도 좀 많이 있거든요. 근데 시간이 아무래도 오늘은 제한적이다 보니까 뭐 그 중에 중점 사항만 말씀을 드린 거고요. 추가적으로 필요한 부분들은 더 있는데 뭐 혹시나 궁금하신 사항이 있으시면 추후에 저희 쪽으로 연락을 주시면 그 부분에 대해서 좀 추가 설명을 드리도록 하겠습니다.
예, 그 특히나 지금 이 OTA에 관련된 부분을 이야기를 하게 되면 이제 FR2 이야기를 주로 많이 하게 되는데, 그래서 결론적으로는 그러면 FR2라고 하는 쪽에 대해서 이 고주파수 대역이 될 텐데, 이쪽에서는 결과적으로는 OTA 시험이 꼭 필요한 부분이 된다, 뭐 이런 백그라운드로 우리가 생각할 수 있는 거겠죠?
네, 거의 필수라고 보면 됩니다.
네, 그래서 뭐 어떤 부분으로 보자면 이제 필수적인 부분이기 때문에 더더군다나 특히나 뭐 이런 부분들을 감안을 하자면은 이제 이런 테크니컬한 백그라운드가 더 필요할 수도 있는 거고요. 이제 그런 면에서 한번 그 우리가 복기해 볼 수 있는 그런 뭐 특히 저도 뭐 봤습니다만은 공식도 많이 나오고 해서 좀 복잡해 보이는 부분들이 있었는데 그런 면에서 좀 복기해 볼 수 있는 부분들이 아니었을까 하는 생각이 들긴 합니다. 예, 그래서 지금 특히나 이번 세션 같은 경우에는 그 시간표 보셔서 아시겠지만은 네, 그 다음 세션이 지금 사실은 5G 오버 더 에어 테스팅이라고 해서 그 실제적인 어떤 프랙티컬한 얘기를 좀 말씀을 드릴 수 있을 것 같아요. 그래서 챔버, 뭐 제가 그 동영상 내용을 봤을 때에는 챔버에 대한 얘기도 나오고 뭐 그 실제 측정에 관련된 이야기가 굉장히 많이 나오게 되는데 지금 좀 전에 보셨던 세션 내용과 연결시켜서 생각을 해보신다면은 좀 더 이렇게 이론과 실제를 결합한 이제 그런 모습의 내용으로 이어서 좀 보실 수 있지 않을까 이제 이런 생각이 들기도 하고요. 그래서 뭐 그런 면에서 보자면은 좀 더 테크니컬한 백그라운드를 말씀을 드렸다. 뭐 이 정도로 생각을 하면 좋을 것 같습니다. 예, 그래서 일단 저희 쪽에서 이제 시간표 상으로 봤을 때는 지금 거의 25분이 되어 가고 있는데요. 지금 질문을 주신 부분이 있네요. 저 한승우님께서 FR2 RCT RRM 시험 시 버추얼 케이블 커넥션 및 RSRPB 관련 설정이 UET 모두 진행이 되고 있나요? 라고 이제 질문을 주셨네요. 이 버추얼 케이블 커넥션과 RSRPB 관련된 설정에 대해서 조금 말씀을 해주실 수 있을까요?
일단 솔직하게 말씀을 드리면 이제 저기서 문의해 주신 버추얼 케이블 커넥션은 제가 솔직히 그 내용은 제가 현재까지 확인된 내용은 없어서 좀 답변 드리긴 좀 어려울 것 같고 그 부분은 제가 추후에 확인을 해서 뭐 메일이나 아니면 다른 방법으로 이제 말씀을 드리겠고요. 추가로 RRM 시험 할 때 주의사항을 좀 말씀을 드리면 주의사항이라고 해야 될지 모르겠지만 중점 포인트일 수도 있어요. 그러니까 기지국이 보통은 하나의 기지국이 있고 RRM 시험할 때 고려가 돼야 될 게 이제 two angle of arrival이라고 해서 두 개의 기지국에 뭐 예를 들면 30도 편차 혹은 60도, 90도, 120도, 150도 다른 각도에서 두 가지 기지국 시그널이 내려왔을 때 좀 측정해야 될 요구사항들이 있어요. 그 2AOA 컨디션인데 그렇게 되면 이제 기존에 이제 FR2 쪽은 이제 챔버가 필요하고 챔버가 이제 CATR 챔버가 필요한데 거기는 보통은 반사판이 리플렉터가 하나가 있는데 그 2AOA 조건을 조성을 하려면 환경 조성을 하려면 리플렉터가 뭐 저희 기준은 4개가 들어가고요. 하나의 챔버 안에. 그래서 기존 챔버에서는 절대 그 환경을 구성할 수가 없습니다. 새로운 타입의 챔버가 필요한 부분은 있습니다. 그래서 그 부분을 좀 참고를 하시면 좋을 것 같습니다.
그 말씀하신 부분 중에 아까 CATR 챔버라고 말씀하신 부분이 이제 우리가 보통 캐달이라고 부르는
네.
그쪽을 말씀하시는 게 맞죠?
네, 맞습니다.
예. 좀 전에 말씀드렸던 멀티 AOA 케이스 같은 경우에는 지금 제 기억으로는 아마 이번 세션에서 관련된 내용을 또 말씀을 드리는 부분들이 있는 걸로 기억을 합니다. 그래서 관련된 내용으로 한 번 더 쭉 보시게 되면은 어떤 식으로 시험이 구현이 되겠구나라는 걸 좀 더 보실 수 있는 그런 부분이 아닐까 싶습니다. 그래서 지금 또 시간이 또 거의 다 됐네요. 그래서 관련된 내용으로 이제 아까 말씀드렸지만은 테크니컬한 부분들이 실제 상황에서 어떤 식으로 이제 테스트 환경으로 구현이 되는지 이런 부분들을 함께 5G 오버 디 에어 테스팅이라는 제목으로 군터 파이퍼 저희 발표자죠. 저희 본사 프로덕트 매니저입니다. 그래서 군터 파이퍼 씨의 발표로 내용을 쭉 같이 함께 보시도록 하겠습니다.
Hello and welcome to an introduction to 5G OTA testing. My name is Günter Pfeiffer and I'm working with Roland Schwartz in the headquarters in Munich, Germany as a product manager. In my presentation, I want to talk about OTA in general and why it is important. What are ways to test over the air? How to do especially RF tests over the air, and what the specification bodies such as 3GPP, but also some others, have to say about it. Then, of course, we want to take a look at the products that we can use for testing OTA, and finally come to a short conclusion. So let's get started. Why is OTA important, or why should I care about OTA? And how can I test OTA? What options do I have, or what alternatives are available? So first of all, why OTA testing at all? You might think OTA, that's kind of this niche where some geeks are working in, and it's kind of like spooky and special. And I would say you may be right with that to a certain extent when you look at the history, but nowadays, and especially with millimeter wave and 5G FR2, this is not the case anymore. And the reason is actually very simple and logical. 5G is looking to address higher data rates, much higher than we know at the moment. But high data rates require a lot of bandwidth. That's Shannon's law, so that the throughput of the channel or the capacity of the channel is directional proportional to the bandwidth. A lot of bandwidth is only available at high frequencies. It's very congested down at convenient frequency ranges, so to speak, in like 1 to 3 gigahertz or maybe up to 6 gigahertz. So you have to go to much higher frequencies. This is why we address millimeter wave bands at the first place, right? So the reason to go to millimeter wave is the capacity and the data rate. These high frequencies, however, suffer high path loss, and high path loss is not nice. We don't like that, right? So this will reduce the capacity again because we'll have a bad signal to noise ratio. So to countermeasure the high path loss, we use beamforming techniques. So we have active antenna arrays with phase shifters, amplifiers, and they will help us to overcome the path loss to some extent. But these active antenna arrays that we absolutely need to have to achieve the goals of 5G do prohibit us from using cable connections because it's an integrated part. It's like active, everything is in there, integrated in the transceiver together with the antenna. And that means we have no chance to connect the cable, and therefore we have to test wirelessly or over the air. So over the air testing is a logical consequence out of the fact that we want to have this high data rate and therefore need to go to the high frequencies. So there is no way around OTA when it comes to millimeter wave or 5G FR2. Now, if we look at a radiating aperture, we have to look a little bit on the field properties now to understand where we are and what we need to do. So if you have a radiating aperture, that should be here, this antenna here on the left, so this line. It's radiating. In this case, it's a 8x1 active antenna array, so we have some certain beam forming, and you see the main lobe or the main energy is going this direction, and then there are some side lobes and so on, but this is like the direction apparently that we are transmitting in. Then we have different field ranges, I would say, that we need to take a look at, or field regions maybe better. So here, this region very close to the antenna, defined by this formula down here, where D is always the radiating aperture size, so the size of this antenna. This region is called the reactive near-field region. And the reactive near-field region is something where, for RF measurements especially, you don't want to be there, because as soon as you bring some material into this reactive near-field region, it couples to the antenna, and it becomes itself part of the antenna. It radiates. And basically, you detune the antenna with just having, for example, a probe going into the near-field region. So this is not what we want for RF testing. There's other things that we can test here, like specific absorption rate. So if you hold your phone next to your ear, you want to know how much energy is going into your skin. Then this is, of course, happening in the reactive near-field region. But for RF measurements, this is no good. Then if the waves propagate, you come to the next field region, that is the radiated near-field region. So in the radiated near-field region, we can do nice measurements, but the problem here is that we have to measure phase and magnitude. So we have to make a complex measurement around the entire sphere of this antenna to understand how the RF propagation is actually at a certain point, or how the waves propagate around the antenna. So these tests are possible. You don't have this problem of detuning the antenna, but they take more time, they take more effort. So possible, but not ideal, I would say. So ideal is what we call the far field region. So here, this is where we actually want to be, because then things are nice and easy. We can just do magnitude measurements, we can do point measurements. So if I want to know the power at this point where my laser pointer is now, I just measure it. The reason is that here we have now already plane waves. So we have where the antenna is typically emitting a spherical wave. It's already here evened out to a certain extent, and we have a plane wave, and we can do this easy measurements. The region starts at the so-called Fraunhofer distance. This is given by this very popular formula 2D square over lambda, where again d is the aperture size and lambda is of course defined by the frequency, so it's the wavelength. And so we want to be 2D square over lambda away ideally, or more if we wanted to. But here's the problem now with more, or with too close. So 2d square over lambda is where the far field starts, so we have a so-called quiet zone, but the quiet zone is pretty small, is exactly at that point. The quiet zone is basically given by the curvature of this wave. As I said, it starts to become a plane wave, but if we go like near a bigger quiet zone, the error that we have due to the curvature is still too big. So if we are right at 2d square over lambda, then we have a very small quiet zone. If we go further away, the quiet zone grows, but at the same time, the path loss also increases. So ideally, we would not have path loss, but yeah, that's difficult. So we have path loss, bigger path loss the further we go away, but therefore also bigger quiet zone. So it's kind of like a trade-off. How big of a quiet zone do you need, and how big of a path loss can you accept? To give you some ideas about these distances, how far away are they? I give you here an example. For example, my 8x1 antenna should be, you see it over here, 8 antenna elements with phase shifters, should be 10 centimeters in size, just as an example, and it should transmit at 30 gigahertz. You see how the waves are emitting here and overlapping, and they are forming a plane wavefront at one point. And that point is the far field distance or the Fraunhofer distance. And with these parameters, so D is 10 centimeter and 30 gigahertz, that means lambda is 1 centimeter. You can then very easily calculate this distance from the top of your head. So 10 to the power of 2 is 100, times 2 is 200, divided by 1, it's 200 centimeter or 2 meters. So you have to be 2 meters away from the antenna. So if you are transmitting here, then you're measuring here, this should be minimum 2 meters away distance. And that means you have to have a chamber that is maybe 3 meters or even more in size. The reactive near field region, by the way, in this example would be 20 centimeters. So if you do measurements in this radiated near field region, you don't want to be closer than, yeah, say 20 centimeters, so about here. As soon as you go closer, you start to measure not this antenna anymore, but the resulting radiating element that is influenced by your probe antenna. Okay, so if we look at this now, what can we do with that? So if we do a direct far field measurement, so we have a device that's radiating, we have a measurement antenna that's measuring, we have this distance 2d square over lambda in between. How big of a chamber do we actually need, or how much distance do we need to bring between these two antennas? That depends, of course, on D and on lambda, of course, on the frequency, but the frequency range for FR2 is 24 to 53 gigahertz about. So it depends on D. D is the radiating aperture size, and if I assume you know the size of your radiating aperture and you know where it is located in your device, and in my example that should be 3 centimeters here in the top corner, then we call this a white box approach. That basically means you can look inside the box and you know what's happening inside. So with a 3 centimeter quiet zone size requirement or radiating aperture size, you would then end up in a range length in the range of 10 to 30 centimeters about. So depending on the frequency, these are all the frequencies from 24 to 53 gigahertz. These are all the curves, the resulting range length curves, depending on the quiet zone size. And now, depending on which frequency you use for a 3 centimeter quiet zone, you need a range length of below half a meter, let's say. So within half a meter distance, you can do far field measurements fine. But it means you know where your antenna is and you know how small it is. And it should be fairly small, otherwise those range lengths grow dramatically. And you can see this in the other example where I say you do not know where the antenna is. Because in this case, you don't know whether you should focus on the top left or on the bottom right corner. And therefore, you basically have to take the entire device size into account as a potential radiator because you don't know where the radiation is coming from. So you take the whole thing in the focus. In my example, that should be 14 centimeters. And that then already means your range length is somewhere between 3 and 6 meters, depending on the frequency. And that, of course, then requires a 5 or 10 meter chamber just to test a small cell phone because you don't know where the radiator sits in this cell phone. So a so-called black box. It's like an element that's radiating somewhere, but I don't know exactly where. So in black box, direct far field, you need really big chambers, and really big chambers means also big range length and therefore high path loss. And high path loss, not so good for doing precise measurements, so the dynamic range shrinks, etc., etc. To summarize all that, so if you want to do a white box testing typically in direct far field, you can do this. Not a problem. We have also chambers that support that. For example, the ATS-1000, that's where this picture is coming from. You have a probe antenna here. You have your device antenna or your device down here. You know exactly where it is. You focus the two antennas to each other, and you can test in a small quiet zone. You can do direct far field measurements with this, measure directly, for example, EVM or power or whatever it is. So that's fine. Typically, you use that for testing antennas and not devices, because if you just test the antenna, then it's fairly small. If you test a device, as long as it's white box, it's possible. But as soon as you don't know exactly where which antenna is and which antenna is radiating at a given moment in time, that becomes a problem. And therefore, you can do what is called indirect far field measurements. There you can do black box with a given quiet zone size. And this is using now a trick. This is the so-called cut-R reflector. A reflector, you see here this gold surface. This is our cut-R reflector. And this helps now to increase the quiet zone to a bigger size, even in a compact setup, a small setup. This is why it's called compact antenna test range, or cut-R. So the size of the quiet zone basically only depends on the size of this reflector. And with this, you can then very easily do black box, because you just say, okay, in my example, that was 14 centimeter. If I have a 14 centimeter quiet zone, I maybe need a 30 centimeter reflector, and I can do this in a very compact, small setup. Rohde & Schwarz offers solutions for this as well. That's the so-called ATS-800B, ATS-800R, or ATS-1800C that we will take a closer look at a little bit later. How does it work? It sounds like black magic, but it's actually only physics. So you have a feed antenna that is in a direct far field directly looking at the device, and in an indirect far field, or cut-R, it's looking at a reflector. And this feed antenna is emitting a spherical wave. That spherical wave is reflected or bounced from that curved surface of the reflector, so it's a parabolic shaped surface, and it's bounced off towards the device, and then it is a plane wave. So the reflector is basically turning the spherical wave or the curved wavefront into a plane wavefront, and it does it on this given section of the reflector surface, because this is the parabolic shaped surface section, and then it goes into the edge treatment. It's typically, in our case, it's an elliptical surface. So if a radiation hits outside the parabolic surface, the wavefront or the waves are reflected into the absorbers on the chamber wall. And only this section is, so to say, the active section of the reflector, creating the quiet zone. And the size of this quiet zone is basically only depending on the size of the reflector. Of course, you have to have an antenna that kind of matches to this reflector, so you should have a half power beam width that is wide enough to also illuminate the surface of this reflector. But if you do that and you place the feed at the right position, so in the focal length of this parabola, then you can create here a nice quiet zone. There is some certain geometry to meet between the feed, the reflector, and the device, but this is all very easily defined along the size of the required quiet zone. So this is the best possible way of doing OTA in a convenient environment, because it gives you a big quiet zone, but still is a compact setup. So now if we have that, how do we test RF in OTA? If we want to know the RF performance of our device, what do we do? And besides RF, what else do we maybe want to test? or how can we test, and what does 3GPP say how we have to test or what we have to test, and maybe also some other test specs. We will take a look at CTIA test plan as well for a moment. So first of all, if you have an emitter, like here in my case, this is a cell phone emitting here with an active antenna array in a certain direction. I have a transmitter, that is the cell phone, is transmitting a certain power over a given antenna. And then I can do different types of measurements. EIRP, equivalent isotropic radiated power. That would be basically the transmitter plus the gain of the antenna. In an ideal case, of course, normally you have losses, but let's just forget about the losses here. 10 dBm I want to transmit, I have a 20 dB gain antenna, then I would have an equivalent isotropic radiated power of 30 dBm. Or I measure the total radiated power, TRP, that is, of course, the transmitted power, 10 dBm in my example. So how do I measure that? EIRP is basically measured in the beam peak direction with a receive antenna, with your measurement antenna. So it's like a beam going towards this antenna, or in a cut R, of course, via a reflector. And you measure just in this one direction. And then you can measure, for example, EVM or other parameters. But this is active antenna array, so it can do beam forming and beam steering, so the beam could go in different directions, and you can also do that. Then it's called EIRP CDF, so you do a cumulative distribution function over the EIRP measurement in different directions. That's another way of measuring, of course, and that's also defined for certain tests like spherical coverage, or this is then also called spherical coverage. Or you want to test the total radiated power, then you have to measure all around the sphere of the radiation of that device. So in our case, the mobile would radiate. We measure once all around the entire sphere, and then we can do a total radiated power measurement. Now, these are different measurement metrics. Which one to use for which test is then defined in a test specification. So in 3GPP, for example, we define an EIRP in beam peak direction for these tests that you can find in the 38521-2, for example, for UE testing, or for those tests, or for reference sensitivity, for example. These are like transmitter tests and receiver tests. So you have to know the beam peak. How do I know the beam peak? Well, either you know it, you can switch your device on in a way that you know the beam peak is always, for example, bore side. In this case, it's great because then you don't need a positioner. But if you don't know that, then you need a positioner. So you have a device on a positioner, and first of all, you do a scan by moving the device around to see where is the beam peak. And then you turn it into this direction that you really receive the beam peak, and then you can do these tests. So either you know it, then you don't need a positioner, or you don't know it, then you do need a positioner. You will need a positioner in any case if you want to do some of these tests here on the right-hand side. They are using total radiated power as a matrix, so you have to measure spherical around, or spherical coverage, or this EIRP CDF functionality. So depending on which test you want to do and how well you can control your device, you might or might not need a positioner inside your OTA setup. But if you want to do full coverage of all these tests, you will anyway need a positioner. If you look at some certain tests, like for example, max output power or also reference sensitivity, then you find that they also occur multiple times. So for example, for max output power, we have to measure EIRP in beam peak, or spherical coverage, or TRP, all three of them. For reference sensitivity, it's also EIS and actually spherical coverage. So some of these tests have different requirements, some of them have multiple requirements. It really depends on the test, and you can find all that in the test specification. Looking at what else the test specification describes, not only 3GPP, but also others, there is additional functionality required, or additional test need. There is, for example, if we look at CTIA test plans, always the need to also take the user influence into account. So how much energy is maybe absorbed or blocked blocked by the user holding the phone next to your ear? How do you hold it? And this, of course, is like more a real life environment, I would say, a scenario where you also see how the user impacts the radiation or the performance. And this is defined in CTIA test plans. And for example, if you want to sell phones to the US, you also have to comply with the CTIA test plan. So you will have to do tests with so-called phantom heads or phantom hands. Then there is also extreme temperature conditions that are tested. This is also defined in 3GPP, for example, that you say the device has to be cooled or heated to a certain range. 3GPP defines -10 to +55 degrees centigrade. And in this case, the background is that you have phase shifters in these active antenna elements, and the performance of these phase shifters might be temperature dependent. So in colder environment, they might work differently than in hot environment. And in order to test this, there is these extreme temperature condition tests defined as well. Then there is also, of course, out-of-band test requirements. So you want to know how much energy is emitted outside the used band, so to avoid interference with other bands. Typically, you test this up to the second harmonic, depending on the band that you use, that is maybe in the range of 90 gigahertz, and down to, sorry, that should be 6 gigahertz. And last but not least, for example, radio resource management tests, RRM, 3GPP defines to test in multiple angles of arrival. So the device does not only see one base station signal, it sees multiple. In the RRM test specification, it's 2 base station signals, but out of different physical angles, so in a different geometry. So this is multiple angle of arrival tests. Now it depends on what you have to test, but if you have to cover everything, then this is all that you need. You need to have phantoms, you need to have extreme temperature, you need to have out of band, you need to have multiple angles of arrival, you need to have RF, and maybe even more protocol, whatever else. But these are all these different requirements that have also an influence then on your OTA setup. Now, if we look at, or we try to summarize all that and look at what we have to put on our shopping list in order to select the right OTA test environment, then we basically need a chamber because we have to test OTA. And ideally, this chamber would be rather compact and small. So maybe we want to favor a compact antenna test range, be quiet zone, small footprint. We will need a positioner in most of the cases, at least if we want to cover all RF tests, but also depending on, as I explained before, what you know, how you can influence the beam, the radiation direction, the beam peak of your device. You might need it for any RF test. Then maybe also phantoms and temperature. That would be good if I can have a chamber that can manage also with phantoms and with extreme temperature, just in case I want to test those, or for example, test CTIA test plans because I want to address American markets. Out of band is something that we will need to cover. If you want to test only in band, fine, but for the entire tests in RF, you also need to cover out of band. And ideally, it would be great if we can do multiple angles of arrival. So we have a chamber that fulfills all these different test requirements that we can see at the moment. So now the question is there a product that can do that? And which product is best fitting my requirements? Rohde & Schwarz offers 3 different cut-R solutions. There is a so-called ATS 800B. That's here on the top, a benchtop setup. It's more like an entry level. It's a very open setup. It's great for research use because it gives you a lot of flexibility. Also in academia, this is well adopted. Maybe it's not so industry proof. Maybe you want to have it more covered up and more solid. Then you can use the so-called ATS 800R, which is this exact same setup put into a rack in an anechoic environment, like you see down here. So here, up here is the reflector that on the benchtop you see here on the side. So this I would call the mid-range setup. And then we also have the ATS 1800C, which is very similar to the 800R, but just everything on the next level, so to say. So we have a parabolic reflector up here that is bigger, so it provides a bigger quiet zone. We have a positioner down here that is bigger and more rugged than the positioner in the 800R, so it can move also more heavy devices. We have a very high shielding environment chamber around it, much higher shielding than here in that rack, of course. So this is what I would call the high-end CAD-R chamber in our portfolio. On these chambers, you can add additional features like a 2D positioner on the benchtop setup or a 3D positioner in the rack setup. The rack setup can also accommodate a temperature test solution, but it's 1D. That basically means the device is stationary inside the temperature solution. And we also can put phantom heads in there, also stationary. And in the high-end ATS 1800C, you have a 3D positioner. You can have a temperature test solution put on the 3D positioner, so you can do 3D temperature tests. We can have a phantom put onto the positioner. You can do 3D phantom tests. We have an out-of-band solution, and we even have a multiple angle of arrival solution in the ATS 1800C. And how we do all that, I want to show you now in the next maybe 15 minutes to introduce you to those different functionalities that you can have in an ATS 1800C. And of course, with the certain limitations, they also apply to the 800R or 800B even. So ATS 1800C, as I mentioned already before, we have a big CAD-R reflector on the top. We have a feed antenna here. We have a big positioner down here that can also move more heavy devices. As mentioned earlier, the size of the reflector defines the size of the quiet zone that it can create. In this case, we have a quiet zone of 30 centimeter. In the smaller version, the 800B, it's 20 centimeter quiet zone. We gold plate all our reflectors, and we do this to provide a very good quality and a very high frequency accuracy also for the high frequencies, also over a long time. So the reflectors don't oxidate. So there is no oxidation on gold, as you all know. Oxidation would be a problem because oxidation increases surface roughness, and if you have a more rough surface, you cannot use it for very high frequencies, means very short wavelength. So gold plating is ideal because it gives you a good performance on high frequencies, stable over the time. So this is why we do gold plate all our reflectors. The positioner inside the ATS 1800C, as I mentioned, is a full 3D. So you have here this white star, if you like. We call it the snowflake. This is basically our azimuth rotation. So this thing spins. And the other, here you see a little bit of a swing. This is the other axis. So this is the elevation. So this wheel basically turns. And with this elevation goes up and down like this. And with having the elevation and the azimuth together, you can then do full 3D spherical measurements. The positioner can move devices up to 15 kilo in weight. Normally, of course, a cell phone is not that heavy, but this has to do with phantom testing. I will come back to this later. But if you have ever touched a phantom head, you know it's pretty heavy. It's in the range of 8 to 10 kilo. So if you put this on there, there is still no problem with moving this precisely and fast, as you see the values up here on our positioner. We can hold devices up to 45 centimeter in diameter on the positioner, so even a tablet or a laptop is no problem to put on there. On top of the positioner, we can also put now a temperature test solution. So like here, you see now what we call the temperature bubble. It's a dome. This dome is made out of RF transparent material. So the radiation, because here you see the feed antenna, it radiates to the top to the reflector and is bounced down. And the radiation is coming here, but it passes through this dome with basically no impact or nothing is happening to this RF radiation. You don't see this dome in the RF. It's RF transparent. So this material is a special material. It's a foam type of material. It's temperature isolating, but it's RF transparent. And that basically means inside, if we open the lid, you see here inside, we have now again this star or the snowflake where you can put your device. So this thing can spin. This is the azimuth rotation. And here you put your device and then you cover it with this dome and then you exchange the air inside with an external climate machine. You pump in hot or hot air, and then you can go up between -40 and +85 degrees centigrade in here. Device size is a little smaller, 41 centimeter, because of course the cover takes up a little bit of space as well. So instead of 45, 41 centimeter device size, but the bubble is put on top of the positioner. So you can do full 3D measurements still while the azimuth is spinning and the elevation is still going up and down like this. So no limitation in the movement of the positioner. I'm sorry. The air is exchanged or coming from an external climate machine. You see here an example. So this thing is providing cool or hot air, pumping into the dome that sits inside the chamber on the positioner. Phantom, as mentioned, you see we can put phantoms on top of the positioner, head phantom or hand phantom, different types. As I mentioned, the main important part here is that these things are really heavy, and therefore you need a very rugged positioner to be able to test devices while having phantoms in place. So for CTI test plans, this is of course very important, and we optimized our positioner in a way that we can have, as I mentioned, up to 15 kilo of weight. So even with a head or hand phantom, not a problem to move it fast and precise. For outer band measurements, we have what we call an automatic feed switcher. And you see this here. We have a rail, and on this rail you have movers. You can have up to 4 movers, and these are motorized. So on each mover you can mount an antenna, and since these movers are motorized, you can remotely just say, I want to have this antenna now in the center position so that it looks at the reflector, and I can use the frequency range of this antenna to do my testing. And if I want to go out of band, I switch over to another frequency range by just putting another mover in the center position. You can't have just one antenna covering the entire frequency range because, as I mentioned earlier, the antenna has to have a big half-power beamwidth to illuminate the entire reflector, and therefore these antennas are band limited, maybe something like 30 gigahertz wide, so 20 to 50, and then I don't know, 30 to 60 or something like that. But you cannot have just one antenna of this precision that goes over the entire frequency range, and therefore you have to have multiple antennas, but you want to have a convenient way of swapping them. And I show you here how this works. This is a prototype still on this video, but you see I switched now from this antenna in the center very simply to another antenna in the center by moving these motorized movers with a remote command to switch over from maybe 40 gigahertz to 60 gigahertz antenna. So outer band measurements, you require such a feed switcher. For multiple angles of arrival, as I mentioned earlier, there is this test requirement in the radio resource management, RRM, test specification that you have 2 angles of arrival. But you have to have a different geometry between these 2 signals, these 2 different angles. The specification calls for 30, 60, 90, 120, and 150 degree between the 2 signals. And what we do here is we have an ATS 1800C in the center, and we can upgrade it with 2 side chambers. And each of these side chambers, if we look inside, accommodates 1 or 2 additional reflectors. These are the same reflectors like the one in the center. So each of them can create a 30 centimeter quiet zone of this with a signal that is coming from its dedicated antenna. So if you look at this reflector here on the left side, there is a feed antenna that illuminates this reflector, and it creates a 30 centimeter quiet zone of this signal. And likewise for all the other three. So in total, 4 reflectors means in theory you can have 4 different signals at the same time. The test specification requires 2 different signals, and the relative angle between these 2 signals is either 30 degree, then you activate these 2 antennas. It can also be 60 degree. You can, for example, use these 2 antennas or maybe also those 2. 90 degree, that's these 2. And 120 degree, that's these 2. So, and 150, of course, yeah, then it's these 2. So you can create all these different angles with these 4 reflectors. We can take a look how this works, but before doing so, the ATS1800C with its side chambers, we called it then ATS1800M, M for multiple angles of arrival or multiple reflector setup, is, by the way, the only CAD-R solution on the market with multiple angles of arrival. It provides the biggest quiet zone for multiple angle of arrival, 30 centimeter out of each direction. And this is resulting in the smallest measurement uncertainty, because with a big quiet zone, your measurement uncertainty is much smaller than if you use a small quiet zone with a direct far-field antenna. I did record a video of this chamber, and I want to show this to you now. Here, let's take a look how this works. In millimeter wave, it's all about over-the-air testing. And in many cases, a compact antenna test range is the chamber solution of choice, since it conveniently provides a big quiet zone. In the ATS1800C, we do this with a big CAD-R reflector on the top of the chamber, and with this vertical setup, we have a very compact footprint. But what do you do if you need a millimeter wave test setup that can provide different signals out of different directions? Like, for example, in radio resource monitoring, where you need 2 angles of arrival. Well, if you have an ATS1800C, this is actually no problem at all. You can simply upgrade it with 2 side chambers to what we call an ATS1800M. So how do we do that? I show you. Let's take a look inside. Each of the side chambers of the ATS1800M accommodates 1 or 2 additional CAD-R reflectors of the same high-end design as the main reflector in the center chamber, thus providing another 30 centimeter quiet zone out of all the resulting 4 different angles. Each of the reflectors has its dedicated feed antenna, and with this you can create any multi-direction test scenario that you require. The 4 reflectors have a fixed relation to each other to meet the requirements of the 3GPP RRM test specification. This means there is 1 reflector at 0 degree, 1 at 30 degree, 1 at 90 degree, and 1 in the other side chamber at 150 degree. Depending on which pair of feed antennas you activate at a given time, you can then create 2 angle of arrival scenarios with all 5 3GPP defined relative angles. The big advantage of the ATS1800M is that it provides the same big 30 centimeter quiet zone out of any angular direction. So regardless if you do a single angle of arrival or a 2 angle of arrival test scenario, you always have a very low measurement uncertainty. And since the side chambers are upgrade options to the existing ATS1800C, this makes this solution unique on the market and very convenient to use. Right, so this is our solution for multiple angle of arrival testing for example, radio resource management, but also, for example, for other R&D test cases. If you look inside, and you saw that already in the video, in the center you have an 1800C, and then left and right you have these additional reflectors. Here you see a prototype view, that's why the reflectors are not gold-plated. In the video you already saw the official product, so all the reflectors gold-plated. To come to a conclusion of my presentation, OTA is a centerpiece in FR2 testing. It becomes very important because of millimeter wave. if you use a CAD-R solution like the ATS1800C, for example, you have a lot of advantages over direct far field, such as a shorter, a bigger quiet zone, let's put it this way, a lower, because it's more compact, a lower path loss, a higher dynamic range, and more easy and convenient use and placement of the device because you have a big quiet zone and you can do black box testing. Since the test requirements and the different test specifications are multifold, it's very good to have a chamber that is flexible and expandable, such as the ATS1800C is, and especially in the ATS1800M, so the side chamber additions to the ATS1800C makes the Rohde & Schwarz ATS1800C a unique solution on the market and the most flexible chamber you can have. So I hope my presentation gave you good inside view on different test solutions for FR2, why you need them and what to take care of. And I'm looking forward of hearing back from you once you make your decision on your chamber environment of choice. Thank you very much.
예, 지금까지 5G 오버 더 에어 테스팅이라는 제목으로 저희 본사 군터 파이퍼 씨가 설명하는 내용들을 쭉 들으셨습니다. 예, 그 코멘트도 올려주셨네요. 좀 어렵다는 얘기도 말씀을 해주셨는데요. 예, 저희도 사실 어떨 때는 어려운 부분들이 있습니다. 네, 그런 부분에서 또 반대로 저희는 또 저희 나름대로 또 공부해서 또 여러분들께 필요한 부분들 또 말씀을 드릴 수 있도록 준비를 하고 있는 상황이니까요. 그런 부분들은 이제 허심탄회하게 또 말씀해 주시면은 저희가 저희 본사 쪽 어떤 기술팀이랑 혹은 제품팀과 협의를 해서 또 답변을 드리기도 하고 이런 식으로 처리를 하고 있습니다. 그래서 여러분들께 어떻게든 도움이 될 수 있는 부분들로 진행을 하고 있으니까요. 그런 부분들 감안해서 또 함께 해주시면 더욱더 좋을 것 같습니다. 먼저 다시 한번 감사드리고요. 예, 지금 세션 5G 오버 더 에어 테스팅 세션을 이제 정리하기 위해서 저희 로데슈바르즈코리아의 기술팀 인원입니다. 남찬우 매니저님과 함께하고 있습니다. 인사해 주시죠.
네, 안녕하세요. 남찬우입니다.
예, 그래서 지금 쭉 말씀을 드렸습니다. 아까 처음에 시작할 때도 말씀드렸던 것처럼 이 전 세션이었었죠. 그 테크니컬한 부분들, 티어리틱한 부분들은 이제 쭉 말씀을 드렸고, 이번 세션에서는 이제 좀 더 프랙티컬한 내용들을 말씀을 드렸던 것 같아요. 그래서 한번 쭉 정리 한번 부탁을 드려도 될까요?
네. 이제 전 세션에 이어서 이번 세션에서는 OTA에 대해서 측정뿐만 아니라 OTA 환경을 구축하는 내용 내에서 많이 포함이 되었었는데요. 우선 그 5G FR2가 OTA에 있어서 가장 중요한 어플리케이션이거든요. 그런데 이러한 5G FR2에서 OTA가 왜 필요한지에 대해서 이 세션에서 설명이 됐었어요. 추가적으로 간략하게 한 번 다시 설명을 드리자면은 5G FR2에서는 더 높은 데이터 레이트를 위해서 더 높은 주파수와 더 넓은 대역을 필요로 하게 되었는데요. 이러한 더 높은 주파수에서는 아무래도 패스로스가 심하기 때문에 그 패스로스를 개선시키기 위해서 5G FR2 단말은 액티브 어레이 안테나라는 시스템을 도입을 하게 되었습니다. 그런데 이 액티브 안테나 어레이 시스템이라는 게 케이블을 연결하는 컨덕티드 테스트에 있어서 상당 부분 제약사항이 있기 때문에 이러한 것들이 OTA로 테스트를 하게 되었다. 이런 배경들을 보시면 좋을 것 같고요. 그 다음에 추가적으로 그 OTA 측정에 있어서 기존의 컨덕티드 테스트에서 없었던 개념들이 많이 나왔어요. 예를 들어서 파필드 조건이 될 수도 있고요. 그 다음에 콰이어트 존에 대한 개념, 그리고 블랙박스나 화이트박스와 테스트와 같은 개념들이 추가적으로 나왔었어요. 근데 기존에 이제 저희가 일반적으로 알고 있는 챔버에 대해서는 이런 파필드 조건이나 넓은 콰이어트 존 이런 것들을 요구사항을 만족하기 위해서는 상당히 큰 사이즈의 챔버가 필요로 하게 되었는데요. 근데 이러한 제약사항을 조금 더 개선하기 위해서 캐달 반사판을 이용한 챔버 솔루션이 이번 세션에 같이 소개가 되었습니다. 이런 개념을 통해서 3GPP에서 요구하는 파필드 조건이라든지 블랙박스 측정이라든지 이런 것들을 캐달 솔루션을 통해서 측정을 하실 수 있고요. 그와 추가적으로 같이 나온 내용이 3GPP뿐만 아니라 CTIA에서도 나온 내용인 온도 환경이라든지 그 다음에 사람의 손이나 머리를 모사하는 팬텀 핸즈, 팬텀 헤드에 대한 내용도 포함이 되었고요. 그 다음에 대역 외 테스트인 OOB 테스트, 그리고 다중 각도를 모사하는 AO, A 테스트가 같이 소개가 되었었습니다. 그런데 이러한 환경 구축에 있어서 저희가 그 ATS 1800C 그리고 ATS 1800M이라는 솔루션을 통해서 이런 환경 구축을 조금 더 이제 컴팩트하고 조금 더 간편하고 좀 더 좋은 성능으로 제공하고 있다는 게 이번 세션의 가장 좀 주안점이 될 수 있겠습니다.
예, 그 중간에 그 비디오에서도 쭉 설명이 되었었습니다만은 그 멀티플 AOA였었죠.
네네.
이거 되게 특이한 측정인 것 같아요. 제가 기억하기로는 이게 기존의 4G나 3G 같은 기존의 이동통신에서도 그 필요로 했던 시험 항목인가요?
그런 3G나 4G 같은 경우에는 기존의 RRM 테스트에 있어서 컨덕티드로 테스트를 했던 것들이 대부분이었기 때문에 이런 요구사항은 따로 없었던 걸로 알고 있고요. 네.
그러면 지금 이게 5G로 들어와서 OTA에 대한 이야기를 하기 때문에
네.
굉장히 유니크하게 얘기가 되는 부분이다. 뭐 이렇게 볼 수 있는 상황이겠네요.
네, 맞습니다. 그렇기 때문에 이런 다중 AOA 테스트라는 데 있어서도 여러 챔버 공급사에서도 다양한 컨셉의 솔루션을 지금 발표하고 있는 상황입니다.
네, 그래서 질문에도 지금 저 봉성함님께서 질문을 올려주셨어요. ATS 1800M의 장점을 설명해 주시면 좋겠다라고 하셨는데 지금 말씀드렸던 이 멀티플 AOA가 지금 사실 가장 큰 특징이 아닐까 싶은 생각이 드는데요. 혹시
네네.
이외에 또 뭐 얘기할 수 있을 만한 어떤 장점이나 특징이 있을까요?
일단 기본적으로 캐달 반사판의 장점이라고 하면은 이제 패스로스가 적고 콰이어트 존이 크다는 장점이 있는데요. ATS 1800M 같은 경우에서는 이런 멀티플 AOA를 구현함에 있어서 여러 개의 반사판, 여러 개의 캐달 타입의 챔버 솔루션을 제공을 하고 있습니다. 그렇기 때문에 조금 더 큰 사이즈의 단말을 측정하시거나 이제 패스로스 다이나믹 레인지를 확보하기 위해서는 이런 캐달 솔루션을 도입하시는 게 가장 좋은 솔루션이다 보니까 ATS 1800M의 장점이 될 수 있고요. 앞서 이제 세션에서도 소개가 되었던 ATS 1800C라는 솔루션도 아마 보셨을 거예요. 근데 ATS 1800C 같은 경우에서는 캐달이 반사판이 하나 있어가지고 실제 각도가 하나만 모사가 되거든요. 근데 실질적으로 이 ATS 1800C에다가 옆에다 사이드 챔버를 담으로써 ATS 1800M으로 업그레이드 할 수 있다는 장점이 추가적으로 있습니다.
예, 특히 5G 같은 경우에는 FR2 이 고주파 대역, 밀리미터 웨이브로 이야기하고 있는 이 고주파 대역 때문에 정말 기존에 이야기하던 이런 이동통신에서 요구하던 사항들 이런 쪽과는 좀 다르게 지금 말씀드린 이런 그 챔버라든지 OTA 시험에 대한 이야기들이 이제 계속 이어지는 것 같은데 좀 정말 기술적으로 필요한 부분이고 검증해야 되는 부분이긴 하겠습니다만은 참 재미있는 분야인 것 같아요. 예, 그래서 한번 그런 내용들은 이제 다시 한번 쭉 말씀을 드렸고요. 예, 지금은 그래서 이제 시간상 지금 3시 15분부터 25분까지는 약 한 10분 정도 쉬시고 또 나머지 세션들을 지금 25분부터 이어서 시작을 해야 될 것 같습니다. 그래서 지금까지 쭉 그 관련된 내용으로 남찬우 매니저님께서 내용을 설명을 드렸고요. 지금부터는 약 한 10분 정도 쉬신 다음에 이어서 또 다시 말씀을 드리도록 하겠습니다. 오랜 동안 고생하셨습니다. 다시 한번 참석해 주신 여러분께 감사드리며 10분 휴식 후에 다시 찾아뵙겠습니다. 예, 뭐 비록 10분 짧은 시간이긴 합니다만은 잠깐 리프레시하고 오시는 정도로는 좀 괜찮지 않았을까 싶습니다. 예, 이제 마지막 2세션 남았네요. 아침에 시작할 때는 언제 다 하나 싶었는데 어느새 이제 2세션밖에 안 남았습니다. 예, 우선 그 세션 시작하기 전에 제가 보니까 지금 마지막에 또 질문 올려주신 분이 또 계시더라고요. 그래서 요거 간단하게 먼저 말씀을 드리고 시작을 하도록 하겠습니다. 먼저 백경훈님께서 그 UI 말고 기지국을 시험할 수 있는 캐달 솔루션이 있는지 이제 문의를 주셨어요. 근데 예, 있습니다. 지금 현재 그 저희도 지금 준비하고 있는 상황이고요. 첫 번째로 이제 생각해 볼 만한 부분은 이제 기지국 같은 경우에는 당연히 그 핸드폰, 스마트폰보다는 덩치가 훨씬 커질 거기 때문에 아까 그 세션 비디오에서 말씀을 드렸습니다만은 결과적으로 이 콰이어 존이라고 하는 이 부분이 이제 가장 중요한 부분이거든요. 그래서 기지국을 대상으로 하는 캐달 챔버 같은 경우는 이 콰이어 존의 크기를 어느 만큼 크게 만들어야 되는 거냐, 이 부분이 가장 큰 관건이라고 얘기할 수 있습니다. 그래서 이 부분에 대해서는 현재 관련된 내용으로 저희가 조만간 또 어떤 내용들을 말씀을 드릴 수 있을 것 같고요. 그리고 정영균님께서도 질문을 주셨어요. 컨덕티드 테스트 시에는 측정 오차를 이제 생각하기 쉽지 않다, 뭐 충분히 안정적으로 측정할 수 있다라는 의미로 말씀을 해주셨는데 OTA 경우에는 어떻게 할 거냐 이제 이런 얘기를 해주셨는데요. 사실 그런 부분 때문에 OTA 같은 경우에 챔버 솔루션이 굉장히 중요해질 것 같아요. 결과적으로 이 그 에어 상태에서 방사 로스가 어느 정도 될 거냐, 그리고 얼마만큼 이거를 정확하게 이 콰이어 존 안에서 매핑을 시켜줄 거냐, 이런 부분들이 이제 가장 큰 관건이 될 거기 때문에 제가 뭐 어떤 말씀을 드린다기보다는 내용상으로 봤을 때는 결과적으로 얼마만큼 안정적인 환경을 이 챔버 솔루션이 만들어 드릴 수 있을 거냐, 얼마만큼 그 휴먼 에러가 발생하지 않을 수 있도록 자동화 시킬 것이냐, 이제 이런 부분들이 이제 가장 큰 관건이 되지 않을까 싶습니다. 그런 면에서 본다면은 그 아까 뭐 보셨겠지만 ATS1800M 같은 경우를 보더라도 이 반사판 위치를 미리 세팅을 해놓기 때문에 이제 그런 면에서 훨씬 어떤 그 오류를 줄일 수 있는 이런 부분이 아닐까 싶고요. 블랙박스와 화이트박스 측정에 대해서 이제 말씀을 해주셨는데요. 이 블랙박스와 화이트박스는 어떤 특정한 환경을 보려고 한다기보다는 목적은 똑같습니다. 동일하게 OTA 측정을 해야 하는데 이 특성상 우리가 정확히 안테나의 위치와 방사 패턴을 알고 접근하지 못한다면은 어디에서 신호가 나오는지를 정확하게 잡을 수가 없기 때문에 그런 면에서 봤을 때 이 핸드폰이라고 하는 이 스마트폰이라고 하는 폼팩터에서 이 위치를 우리가 정확히 알고 들어간다고 하면은 화이트박스 측정이라고 이름을 붙여서 우리가 그 방법을 이제 이름을 붙이고 있는 거고요. 반대로 이 스마트폰 내부의 안테나 위치는 얼마든지 위에도 있을 수 있고 아래도 있을 수 있고 위치가 다를 수 있거든요. 이 위치를 모르기 때문에 이 전체를 다 커버할 수 있는 어떤 균일한 패턴의 영역을 만든다. 그럴 경우에는 이걸 블랙박스 어프로칭이라고 이제 이름을 붙이고 있는 그런 어떤 접근 방법론의 차이라고 보시는 게 맞을 것 같은데요. 이건 이제 특히나 개발처럼 혹은 중간에 나왔습니다만 안테나 측정처럼 확실하게 우리가 방사에 대한 어떤 패턴이나 위치를 알고 있다라고 한다면은, 그래서 딱 집어서 얘기할 수 있다라면은 화이트박스로도 얼마든지 측정을 할 수 있겠지만은 그렇지 못한 경우이길 경우에는 어쩔 수 없이 이 영역을 크게 가져가는 콰이어 존을 크게 가져가는 블랙박스 방식으로 접근을 해야 한다. 그러려면은 캐달이라고 하는 컨셉이 필요한 거다. 뭐 이런 정도의 내용으로 말씀드렸던 내용을 좀 이해를 해주시면 좋을 것 같습니다. 예, 여기까지가 일단 그 앞선 세션에 대한 내용으로 말씀을 드렸던 부분이고요. 예, 그래서 지금부터는 뭐 시간이 약간 그 Q&A 마무리 해드리느라고 조금 더 걸렸네요. 지금부터는 그 Empowering the Mobile Device Experience with Wi-Fi 6, 7 그리고 UWB 이런 내용으로 이제 말씀을 드릴 겁니다. 오후 첫 번째 세션 아마 기억해 보시면은 그 5G 단말 자체가 이제 더 이상 5G만 가지고 있는 건 아니잖아요. 뭐 와이파이도 지원되고 블루투스도 되고 뭐 이런 이야기들을 말씀을 드렸는데 그 중에서도 특히 와이파이에서 어떤 발전이 있을지, 어떤 개선이 있을지, 그리고 UWB에 대해서 좀 더 깊게 들어갈 수 있는 이런 정도 내용으로 아마 여러분께서 내용을 접근해 주시면 좋을 것 같습니다. 그래서 관련된 내용으로 오후 첫 번째 세션 발표자였던 요그콥 씨의 내용으로 그 발표 내용을 보시겠습니다. 지금부터 비디오 같이 시청하시겠습니다.
Hello, welcome to the next session about empowering the mobile device or mobile application experience with Wi-Fi 6E and Wi-Fi 7 and ultra-wideband. 2 or 3 quite new technologies which are becoming more and more important in this area. My name is Jörg Köpp and I'm wireless device testing market segment manager at Rodeschbarzkooperative Schwarz. Let's start. If you are looking on actual devices or also future mobile devices, for example on future smartphones, there's a couple of wireless technologies that are necessary to really enable the full application experience. Of course, there's 4G and in the future and 5G technologies, especially for mobile communication, mobile internet, mobile voice calls, and so on and so far. But also Wi-Fi is very important in this regards, because especially at homes, in the office and so on, most people are using Wi-Fi to get high-speed access to the internet. Of course, for positioning, GNSS is very important. Bluetooth low energy. Bluetooth is still the dominant technology for connecting peripheral devices. NFC for payment, and we see, of course, also charging application more or less on every modern phone now. And quite new, ultra-wideband. The first phones are out with this, with quite nice applications. Today in this session, I would like to look a little bit on ultra-wideband, where this is coming from, what is behind this technology and how you can test this, and also on Wi-Fi 6E, and also already giving a kind of outlook on Wi-Fi 7, the next generation of Wi-Fi, which is actually in standardization. If you are looking on the 6th generation of Wi-Fi, which is the actual one, or which is also known under the term IEEE 802.11ax, this technology introduced for a couple of years, but the final version just coming out this year, was mainly focusing on improving the efficiency of Wi-Fi, especially in dense area. Over the last couple of decades, Wi-Fi was more or less focusing on providing more and more speed throughput to the users by adding more streams, using higher modulation schemes, and also adding more and more bandwidth, and also using operation in different spectrums. But with the kind of success of Wi-Fi, with so many Wi-Fi access points around, so many clients, it becomes becoming more and more difficult to really leverage this technology, because due to the concept listen before talk, more or less, in Wi-Fi, most of the devices, if you have a lot of them, are mainly waiting to get access. Therefore, this standard was really looking how to improve this efficiency, and also to address the upcoming demand for using Wi-Fi in outdoor environments regarding covering or handling multi-path environments in a smart way. What were the cornerstones of Wi-Fi 6, which I'm calling the Wi-Fi 6 revolution, because it is really bringing Wi-Fi to the next level. First of all, for the efficiency, they are introducing Wi-Fi OFDMA, which means now the access is not only controlled via time or distributed over time for the different clients, it is also distributed over frequency. For this, they introduced so-called resource units. And of course, for this you need also a kind of management. That means communication and control between the access point and the station. So which device can use which resource unit, so which frequency at which time, and so on and so forth. Needs, of course, a kind of synchronization, but makes the use of the available spectrum much more efficient. The other thing about this multi-path environment, especially outdoor environments, we're introducing a longer guard interval. To deal with, this has the impact that it becomes less efficient, because if you have a guard time, then you cannot transmit data. Therefore, they were also changing the subcarrier spacing, and with this the symbol time. And by this way, it was also becoming more efficient, because the relation between guard time and symbol time become nicer, I would say, so that you can improve in two sense. One is that you can more avoid this inter-symbol interference, and the other is that you can use the resources, available resources, more efficient. If you look just on the physical parameters between the different Wi-Fi standards so far, Wi-Fi 4 or 802.11n, Wi-Fi 5, which is 802.11ac, and Wi-Fi 6, Wi-Fi IEEE 802.11ax, then you see essentially what I mentioned before, that only the introduction of OFDMA together with the new subcarrier spacing and the new guard interval were the main changes. All about this efficiency and outdoor support. On the other side, for the higher speed, they were also doing a little bit by introducing the next modulation scheme, which was 1024 QAM. But as you see on the maximal data rate from Wi-Fi 4 to Wi-Fi 5, we had a really jump of a factor of 10 more or less, just because of more bandwidth and more special streams and so on. But from Wi-Fi 5 to Wi-Fi 6, that's just a minor part which is only related to the higher modulation scheme that we can use here. Now, because the available bandwidth or spectrum channel bandwidth was the same, 160 megahertz in AC and AX, and also the number of parallel layers or streams in MIMO scheme was 8x8 and 8x8 in both standardizations. Then, based on this, with the introduction of OFDMA and also the resource management, we saw also a couple of new test requirements, because you have to make sure that all this works smooth together and also in the right timing and so on. Therefore, there was, for example, or is a new requirements about the accurate start time. If you see, for example, the communication between the access point and the devices, so the devices would like to send something to the access point, they have announced this, and the access point is sending then out a trigger frame, and the trigger frame contains information which resource units the devices or the station can use, and a kind of timing. And then it is of course necessary that all the devices send out or send back their packages, the trigger packages in a certain time frame, which is just in a frame of 400 nanoseconds. This of course needs to be tested. On the other side, or in addition, there's also a kind of demand that all the signals from the stations receiving more or less on the same power level on the access point, which makes RF handling much easier. To ensure this, there is a kind of power control between the access points and the station, which also required a kind of accurate power measurements on this side, and the possibility to really to tune the power accordingly for this related test cases. And of course, there's a need that a station which should send on a certain resource units is also transmit the signal just on this resource unit, so that you have certain requirement about the spectrum that you are occupying, and this is about the clean RU spectrum or unused tone error. So additional requirements that we believe you can best address, for example, with our signaling test solutions. If you are looking now what is actually happening, there's a lot of discussions around the world about additional spectrum. Or if you look what was available so far, we had this famous 2.4 gigahertz spectrum, probably still the most used spectrum in Wi-Fi, but very limited. And then we had a 5 gigahertz spectrum, much more spectrum available. But if you think about the latest standard, Wi-Fi 11ax, 160 megahertz channel use, you have just 2 channels available, or probably 3 in the future. There's some new spectrum available, for example, for FCC. You have, of course, always to look on the regulatory requirements in the regions. And now, with Wi-Fi 6, there are coming much more spectrum, additional spectrum available. So this started with FCC, but also Europe was adapting this. For example, in FCC, you have now 1.2 gigahertz additional spectrum available under certain rules. And in Europe, it is around 480 megahertz spectrum, the part from 5.9.45 to the 6.4 gigahertz is for Europe, and in the different regions you see different requirements. If you look on the different requirements that we have there, you see, I would explain just two examples which fits very well in the overall scheme. For example, Canada is going a little bit in the direction of FCC or based on FCC, and they have essentially three different categories of devices. One is the standard power access point with 36 dBm, but this is allowed only under AFC, which is this automated frequency coordination. That means the access point has first to contact a database and gets the information for this position, which kind of channel they are allowed to use. Then is low power indoor. This is something that we see globally with a reduced power in the spectrum, but only allowed in indoor locations. And then there's an additional one which is very low power. So it is a kind of extreme low power over the whole spectrum, indoor and outdoor. You see in Canada, they are using more or less the full spectrum of this 1.2 gigahertz. And for LPI, for standard power, this is a little bit reduced. If you look now on South Korea, then you see the actual standard is saying they are not supported this standard power AFC-based stuff, which is, by the way, also applicable for Europe. But they are supporting the whole spectrum 6 gigahertz band with 1.2 gigahertz for low power indoor and for very low power. And for low power indoor, there's a requirement for ERP max of 24 dBm and the power spectrum density for 2 dBm per megahertz. And then you can make some math, and then you see this kind of different ERPs for the different channels. For very low power, it is this 40 dBm max and the PSD of 1 dBm per megahertz. As mentioned, there are quite different requirements around the world. Here you see a map, which is the status more or less of July 2021 in the different countries where it is already adopted, and a couple of countries which are considering to use the 6 gigahertz band as well. So if you look especially on the American market, they are typically using the full spectrum of 1200 megahertz. If you look on Europe, it's always just using this 500 megahertz or 480 megahertz. And if you go more in the direction of Asia, then it's a little bit distributed. Now Wi-Fi 7, that's the next generation, and the standardization just started, and I think the first draft version was just published. Now the main point is again extreme high throughput. So after Wi-Fi 6 focusing on efficiency, they are now looking on improving the throughput again, especially for applications at home, offices, for example homeschooling and something like this, and also factories as a kind of new application for Wi-Fi, at least new in the sense that it gets more support from the standard. If you would like to improve the data rate or the throughput, then you have essentially three dimensions that you can manipulate or that you can improve. One is, of course, the number of data bits per subcarrier or per symbol that you can transmit. That depends on the modulation scheme and the coding. Then you can improve the bandwidth, and you can add a number of spatial streams that you can transmit. These are more or less the three dimensions that you have. In this figure, you see what we actually have if we are just looking on 11N AC. For example, in 11AC, as mentioned before, you have this 24/6 QAM with a coding rate of 5 to 6. You get around 6.9 megabits per second. This is based on 160 megahertz channels and 8 spatial streams. If you are looking now on Wi-Fi 6 or Wi-Fi 6E, means Wi-Fi 11AX, as mentioned before, the only dimensions that we have changed now is the modulation scheme with 1024 QAM. the encoding rate and a little bit on the symbol time, which is improving the efficiency as well and has some positive impact on the data rate. And then you get around 9.6 gigabit per second. In Wi-Fi 7 now, they are going to improve all 3 dimensions. They add the possibility of to support 320 megahertz channels. That means they are doubling the available bandwidth. They adding also 4096 QAM. That means you have now 12 bits per symbols. And they are improving also the number of supported spatial streams from 8 to 16. So in the end of the day, if you make some math, and this is just based on the model and is also ignoring the signaling overhead and something like this, with 60 by 16 MIMO, 4096 QAM, 300 megahertz channels, you can theoretically achieve around 46 gigabit per second, which is of course a lot. How they are doing this, if you look on the 6 gigahertz channels and the 320 megahertz, even in this wide band, it is not easy to place some 320 megahertz channels. Therefore, they decided here to have overlapping 320 megahertz channels, as you see on the bottom. And if you are just looking on Europe with this 500 megahertz or 480 megahertz, in fact, there are just 2 300 megahertz channels available that can be used by Wi-Fi 7 in Europe based on the actual regulation. Probably there will be some changes. In North America, based on FCC, where we have the whole spectrum, 1200 megahertz, for example, for low power indoor, you have up to 6 channels, so always 6 overlapping channels, if you like. If you are looking on the modulation scheme, then it is of course nice to have higher and higher modulation scheme, but of course this is kind of stressful for the RF design, because the EVM requirements are becoming stronger and stronger if you would like to transmit these signals and of course have the possibility to receive these signals on the receiver side in a reliable way. You see here the different EVM requirements. In 11AC, 264 QAM, we had minus 30 dBe or less than 3%. With 1024 QAM, it was already a kind of challenge with minus 35 dBm, and now with 4096 QAM, we are already in the range from 38 dB, minus 38 dB EVM, which is of course a challenge for the RF design. Having also in mind that we are talking now about much wider channels, that means you have to support this kind of EVM over the whole spectrum of this probably 1.2 gigahertz and also the channel of 300 megahertz. So this is really an RF challenge and of course needs also the related test and measurement equipment to verify this, that you are able to do this on the transmitter side and also on the receiver side. If you are now comparing the main parameter on the physical layer on Wi-Fi 6 or Wi-Fi 6E in this case and Wi-Fi 7, then of course with Wi-Fi 6 we have 11AX, no big changes there, just adding also the 6 GHz band. In some regions with Wi-Fi 7, now we have more channel bandwidth, 320 megahertz, we have 16 spatial streams, and we have this 4096 QAM. And as I explained before, this is then allowing a maximal data rate for a single link with all these parameters of 46 gigabit per second, theoretically. But there are some other changes in Wi-Fi 7 worthwhile to mention. One is here that they changed or modified the tone plan for channels wider than 80 megahertz and equal 80 megahertz. Because of some regulatory topics and also to have a better dealing with puncturing and so on and so far, that you see here. Just that you are aware of this. Then they introduced so-called multi-resource unit. The In Wi-Fi 6, they introduced the resource units, as explained before, like the resource unit 26, consisting of 26 tones, or resource unit 52 with 52 tones, and so on and so forth. But if you, for example, if you would like to serve 8 users with a resource unit of 106 tones, then you can do this, of course, but you see that a lot of tones are not used for data transmission because just of the size of the resource units. So that is not very efficient, I would say. Therefore, they introduced, especially for the smaller AU sizes, the possibility for multi-resource units. So you combine 2 resource units, for example, here 106 plus 26 AU. And with this, then in this example for 8 users, you can serve 8 users with this multi-resource unit, and the other 4 users with a single resource unit of 106. And by this way, you can have the full use of the available bandwidth of the available spectrum. This is especially for the small AUs. For the large multi-resource units, as you see on the bottom, for example, a multi-resource unit consisting of 48.4 and 242. This is especially for puncturing stuff where you would like to get rid or not use a certain part of the bandwidth, for example, because of interferences or other Wi-Fi networks. To summarize this, what are the essential features for Wi-Fi 7? I mentioned already the physical layer, 320 MHz, 4096 QAM, and also 16 spatial streams. I mentioned also the new channel plan and multi-resource units per user. This is all on the physical layer. If you look more on the MAC layer, then they introduced also a feature, and this is still in the beginning, what they would like to do with is multi-access point coordination. That means there's communication between the access points to coordinate the communication to the stations. For example, one station could operate in parallel with 2 access points, as one example, or the access points can coordinate the beamforming or multi-user and resource units that are used to a certain station. Also interesting is a multi-link operation. That means an access point can establish several links to a non-access point or the station. For example, as indicated here in this figure, one link on the 2 GHz band, a second link on the 5 GHz, and a third link on the 3 GHz. Of course, we can also establish just 2. This can be used for to have more bandwidth, but also can be used to communicate, to receive and transmit at the same time data from and to one access point and one device to another. And by this, of course, you can also improve your data throughput because you simply can use several channels in parallel. Then, shortly mentioned, there's this preamble puncturing. This was already introduced in Wi-Fi 6, but especially with this even wider channels that we have now, it becomes more important. That means if you have, for example, 2 access points that are working closely together, one would like to use an 160 MHz channel, the other just a 20 MHz channel, then without this puncturing, if the access point 2 uses the 20 MHz channel, access point 1 is not able to use the 160 MHz channels. But with puncturing, that is possible because access point 1 is then just skipping this 20 MHz part out of his signal, and they can operate both together. Another point is, especially if you look on very low power in the 6 GHz band and so on, then this coverage becomes a problem with this low power access point, and therefore this dual carrier modulation that was also introduced in Wi-Fi 6 already and also in Wi-Fi 11AH, I think, becomes more important. Essentially, you transmit a symbol twice on different subcarriers on the left and the right-hand side of the spectrum. You need doubling the bandwidth, but in this way you can get a better coverage. If you're looking now on the Wi-Fi test solutions that we are offering, of course we have a conformance test solution, RF performance test solution with the CMW 500 and 270 for non-signaling and signaling test. CMP 180, I will come to this in a second as a new product. We have solutions in productions, we have generator analyzers, and of course also for the digital design, power supplies with power analyzer function and scopes and so on. What we are offering now for Wi-Fi 7 already, of course also for Wi-Fi 6E, is our spectrum analyzer. The FSW is supporting Wi-Fi 7 already based on the latest specification, as you see here on this diagram with the full constellation diagram and 320 MHz channel bandwidth. The same with our generator, the SMW, and also the SMM, which is our new spectrum analyzer with just one channel. And as you see here on the screen, this is also an 11BE signal. And for example, you can use here, and this is just an example, this multi-resource unit configuration, for example, for the puncturing. Then we have really a brand new product. This is the CMP 180. And this is really designed to serve the future market in this, with a demand for higher spectrum, higher frequency, up to 8 GHz, and also more bandwidth, what we see more and more in all this kind of technology. And therefore, we are supporting here with this design up to 8 GHz, 500 MHz bandwidth, and also a high output power, which is probably very important, for example, for OTR measurements. In a very compact design, it is equipped with 2x8 ports, inside 2 generators, 2 analyzer, and a built-in controller. You can test with this 5G FM1 radio, Wi-Fi 6, Wi-Fi 7, stations and access point, and of course other technologies like Bluetooth and many more that you probably know from the CMW 100 as well. It's a common platform, it's using Linux, CM2, system-wide licenses, and so on. How this looks like, you can use this in new instruments, for example, in R&D, like in this configuration, if you would like to use MIMO testing on different channels, because you have 2 generators, 2 analyzers, all these ports, that's easy going. And you have a nice user interface, web-based user interface that you probably know from the CMX or from the CMP 200. Quite new from Rohde & Schwarz, very comfortable, which should fit to all your needs in the development in R&D, including sequencers and so on and so forth. And of course, this product is also designed to fulfill the requirement in the production environment, especially with a number of ports, so that you can make parallel testing, broadcast testing, and so on and so far. And we are offering a service, a kind of software as a service with a wireless manufacturing test, where we offer for our customers that we make sure the integration of chipsets and in the production environment with our instruments, like indicated here. And by the way, I have not shown this, CMP 180 is also supporting Wi-Fi 7 already. We are working on this, not commercially available, but you can see this here. And if you look here on the details, a quite good EVM of minus 40 dB, which is very, very good and fulfills the requirements for Wi-Fi 7 testing in a 320 MHz channel. So this was Wi-Fi, just a quick view on our solution and on the technology. Now I would like to spend the rest of the time to look a little bit on ultra-wideband. What is ultra-wideband? Ultra-wideband is a quite, I would say, mature technology as such, but we recognize now, after we saw this before, mainly in industrial applications, that it comes to our smartphones. For a couple of applications, hands-free access, digital key for cars, asset finding, navigation, mobile payment probably, sharing, artificial augmented reality, virtual reality, and so on. And there's a couple of devices already on the market. I can say I have at my home already a couple of UWB ultra-wideband devices, for example, to find my keys and something like that. What is behind this technology? Let's compare this to Bluetooth. In Bluetooth, It's operating in a 2.4 gigahertz band, has a quite long symbol time of 1 microseconds, and that is a quite small signal bandwidth of just 1 megahertz. Compared to this, ultra-wideband is a pulse technology, so there are very short pulses of 1 to 2 nanoseconds, and this creates a very wide spectrum of 500 megahertz and more, but with a very low power density. If you just look on the numbers, Bluetooth power density of 20 dBm per 100 kilohertz. Here we are talking about minus 41 dBm per megahertz EIRP. On the right hand side, you see some ultra-wideband signals on our analyzers, in this case on the CMP200. If you look on the operation of ultra-wideband, where it is defined, of course it is always dependent on the regional regulation. There's one channel in a sub-gigahertz band, there's three 500 megahertz channels in the low band. Main applications is in a high band, which is in the range from 6 gigahertz to 10 gigahertz, with a couple of channels, so most are using this. We can differentiate between HRP and LRP, which is about the pulse repetition rate. Most applications are using HRP. If you look on the standardization, the IEEE standardization over the time is covered by IEEE 802.15.4, which is covering a lot of technology, including, for example, ZigBee and so on. Here, as I mentioned, there's HRP and LRP. I would like to focus on HRP because this is of most interest. And the latest standard which were coming out and defined in the Z group is 802.15.4Z, which is now defining and using ultra-wideband for enhanced ranging devices, ERDEV, for BPRF, which is base pulse repetition frequency, and HPRF, high pulse repetition frequency. And these are the both that I would like to focus on now and give you some insights. An additional part of 802.11.4Z was also ensuring interoperability and security, and therefore they introduced also additional feature and described this here, including the secure ranging. How this looks like, this both standards. If you look on the BPRF mode, you see here how the PDU looks like. There's a synchronization header, physical header, and the PSDU. As usual, worthwhile to mention the RM marker, which is the first symbol of the physical header, which is used for time of flight measurement that we will explain later. I would not like to go on the details here. I mean, you anyway get the slides, you can have a deeper look on this. If you look on the modulation of the BPRF mode, this principle looks like this. You have a certain symbol duration, in this case of 128 nanoseconds, and this symbol duration is separated in two parts, left and right hand side if you like. And even these parts are also separated in the time where burst can happen and a guard interval. So in the end of the day, as you see on the top, you have four areas: first burst position, guard interval, second burst position, and guard interval. Now you have the related coding, a Rad-Salomon encoder, convolutional encoder, and BPSK. Modulation BPSK, BPM BPSK means that you have a certain pulse sequence, and the outcome of the convolutional encoder is first saying what is the burst position. Is this burst position on the first or on the second? And the second output of the encoder is saying what is the pulse polarity of this pulse sequence. And this is how the modulation works. If you look on HPF, looks very similar, a little bit changes in the physical header to cover the needs here, but there is a little bit different modulation. Here it is not really the burst position because compared to BPRF, where just one of the both position is used, here always both positions are used for a burst. You see this here on the left and on the right hand side, and dependent on the output of the encoder, they generate a kind of polarity map where these pulse sequences are sended with different rates and so on and so forth. Here there are two possibilities that are supported. The first one was with a higher mean pulse repetition frequency of 250 MHz, and here with 125 MHz. In addition, they introduced the so-called STS, the scramble time sequence. This purpose is mainly for security, to make sure that not somebody else is hijacking you. This was especially important for secure ranging applications. How this looks like, the devices exchanged related keys and seed values, and based on this there will be an AS128 data memorandum bit generator creating this kind of secure sequence, and this is then transmitted in this STS fields, and this could be a single segment STS or also more, up to 4 segments. And you see here indicated how this works with some spreading and so on and so far. Coming to one of the main applications for ultra-wideband, this is really fine ranging and positioning. They are essentially supporting two. One is the time of flight measurements, and the other is angle of arrival. As indicated here, time of flight based on the propagation speed of radio wave, then you can calculate the distance. And angle of arrival mainly because of phase difference measurements. How this looks like in the ultra-wideband specification is there are essentially two possibilities. One is single-sided two-way ranging, and the other is double-sided two-way ranging, and it's mainly about exchanging messages between both points. Between both devices and making independent time measurements on each of the devices, which makes it quite robust, and there's no need for time synchronization between the devices to make this kind of measurements. How this looks like for angle of arrival, also known from other technologies, you can use angle of arrival by measuring the time difference, but also the phase difference. If you have two antennas with a certain distance d, you can, based on the phase difference, calculate the angle of arrival. Then, if you are looking on testing requirements for ultra-wideband, there's of course ultra-wideband conformance, regulatory conformance, and standard conformance. As listed here, I don't like to go in the details so much. This is more or less what you know. Typical measurements are transmit power spectrum density. A little bit more special for ultra-wideband is this normalized RC cross-correlation magnitude, which is a kind of quality of the pulses. And also here, a time domain mask for pulses, which is also about the quality of the pulses. Worthwhile to mention that there's a FIRA organization, the FIRA consortium. Rode and Schwarz is also a member, and they have as one of the tasks providing a certification framework. And there are essentially three certification areas. One is physical layer compliance, one is MAC layer compliance, and additionally is an interoperability compliance and related test specification. Interesting also that they develop an interface to the devices between tester and interfaces, so that you have a common interface how you can run with all devices this kinds of tests. Similar things like we know from Bluetooth. And Rode and Schwarz is also working on providing a physical layer compliance test tool for FIRA certification. Worthwhile to mention, if you especially would like to make this time of flight measurements, it is necessary to calibrate the devices, because the measurement of the time should happen when the radio signal goes out of the antenna or is received on the antenna. In fact, the measurement will be done on the processing part. That means there's a certain delay between the real sending out and the measurement, or on the other way, between receiving and the measurement. This needs to be calibrated, and of course this is also varying over time. And therefore you have to make this kind of time of flight validation and verification. What kind of solutions we are providing? We have generators, analyzers supporting these technologies. You can also use our scopes together with the VSE software. We have everything for embedded design and power optimization, and we have also production solution for ultra-wideband in non-signaling test, including time of flight and over-the-air testing. Here I would like to highlight the CMP200. It's a wideband non-signaling test that you can use for 5G FR2 testing and ultra-wideband testing. So it's supporting the frequency range, has one generator, one analyzer, 3 switchable ports that you can use, and supports the measurements in the high band from 6.5 to 9.5 gigahertz for 500 megahertz channels, and also time of flight. Here, just a few how this looks like. The same user interface that I showed you already for the CMP 180 is also used here. And all this typical measurements which are required, whether by standardization or also by the FIRA. And we have also the possibility to make here this time of flight measurements with a kind of unique solution, making sure that we can very accurately measure this. This is very special things because we are using here a coupler which allows us to measure not only to measure in very accurately the T round and T reply time, because we are not only measuring when we are sending out the message to the device, we can also see when this measurements is going out by this kind of coupler. And this allows us to get rid of any uncertainties inside the tester, and we can make this kind of calibration very accurately. Please spend some time and look on this slide. I hope this is more or less self-explaining and you can verify it. What we are supporting, especially for angle of arrival testing, the conducted test, together with the delay shifter. We have here a partner that you can use for, so the CMP200 with this coupler, additional coupler over the delay shifter and then connecting to the both antennas. But we are supporting also an over-the-air mode, where you can use one of our chambers, for example, the CMQ200 or 500, together with the CMP200, with this coupler set up and, for example, 3 antennas, where you can then make the calibration and the verification for time of flight measurements. And with this, I would like to end for today. It was just a quick view on ultra-wideband and Wi-Fi 6 and Wi-Fi 7 and our solutions. If you need more information, please visit our webpage or ask your sales representative. We have, of course, much more. Also some webinars dedicated for the different topics. Thank you very much.
네, 지금까지 6번째 세션이었죠. 그 Empowering the Mobile Device Experience with Wi-Fi and UWB 세션으로 해서 저희 독일 본사의 요그콥 씨의 발표 내용을 들으셨습니다. 예, 그래서 이 세션 정리에 대한 부분을 위해서 저희 로데슈바르즈코리아에서 그 기술 지원팀 근무하고 계시는 김민철 매니저님 자리에 함께 해주셨습니다. 인사하시죠.
네, 안녕하십니까, 김철입니다. 네, 오늘 들으신 와이파이 6E랑 7 그리고 UWB 기술에서 확인하셨다시피 현재 새로운 기술들의 추세는 그 대역폭 많은 160메가 혹은 320메가까지 사용하시고 있는 광대역 대역폭과 전체 대역폭이 1기가 이상을 사용하는 그런 기술들을 다루고 있습니다. 더불어서 1024캄 혹은 4096캄까지 좀 더 하이 어큐리시에 해당되는 퍼포먼스를 요구하고 있고요. 이에 저희 로데슈바르즈에서는 FSW 하이 퍼포먼스의 스펙트럼 장비와 그리고 CMP180이라는 아주 최적의 양산 솔루션으로 제품으로 여러분께 이제 지원을 해드릴 로드맵을 가지고 있습니다. 네, 이상입니다.
예, 그래서 이번 세션에 대해서도 제가 아주 간단하게 내용을 정리를 해주셨습니다. 그래서 그 내용상으로는 앞으로 뭐 사실 뭐 와이파이도 그렇고 UWB도 그렇고 앞으로 먼 미래에 나올 기술은 사실 아니거든요. 이미 여러분께서 쓰고 계시는 내용일 수 있어요. 그래서 그런 면에서 좀 더 현실적으로 어떻게 시험을 할 거냐에 대한 부분까지 포함을 해서 말씀드린 세션이었었고요. 질문 주신 분들이 내용이 좀 많으시네요. 그래서 질문들 잠깐 보겠습니다. 그래서 먼저 정영규님께서 와이파이와 5G는 서로 공존하면서 보완해 줄 수 있는 관계처럼 보이는데 UWB는 와이파이나 5G가 경쟁하는 것처럼 보인다라고 이제 말씀을 해주신 것 같아요. 근데 아마 제 생각으로는 뭐 사실 와이파이와 5G도 서로 사실 엄밀하게 얘기해서 서로 보완을 해주기 위해서 만들었다든지 그런 건 아니잖아요. 내용상으로 보면은 뭐 결국 모든 기술이 다 그렇지만 서로 경쟁도 할 수 있고 협력도 할 수 있는데 현재까지의 내용으로 놓고 봤을 때는 아무래도 UWB는 이제 와이파이나 5G와는 좀 다른 루트를 가져가는 게 아닌가, 뭐 어플리케이션도 그렇고요. 이런 생각이 좀 들기 때문에 굳이 경쟁이라고 얘기할 수 있을지는 조금 어렵지 않나, 이제 이런 생각이 들기는 하고요. 또 밑에 질문 주신 내용에서 이제 정영규님, 저 와이파이 관련해서 이제 주파수에 대한 내용 말씀을 해주셨는데요. 현재 뭐 제가 알고 있기로는 공식적으로는 2.4기가가 지금 메인인 걸로 알고 있어요. 맞죠?
네, 1.4기가 5기가, 이번에 추가된 6기가 돼요. 그리고 1.2기가나 5기가, 500메가 대역은 아마 와이파이 규격 내에서 IoT 제품을 다루는 규격으로 최근에 많이 이슈가 되고 있습니다.
이게 공식적으로 저희가 말씀드릴 수 있는 부분은 좀 전에 들으신 것처럼 이제 2.4기가, 5기가, 6기가를 이야기를 하는데 추가 주파수 대역으로 사용하려고 한다는 부분은 이제 드래프트에서 이제 언급을 되는 부분은 사실 확정된 부분은 아니기 때문에 이런 부분들은 이제 추후에 어떻게 확정이 되는지 이런 부분도 봐야 될 것 같고요. 특히나 뭐 보셨겠지만은 이 와이파이도 그렇고 뭐 사실 5G도 마찬가지고 6G도 마찬가지가 될 것 같습니다만은 각 지역별로 리전이라고 표현을 했었는데요. 지역별로, 국가별로 이런 규제나 이런 부분들은 계속 달라지는 부분이기 때문에 이런 면에서는 좀 더 시간이 걸려야 좀 구체적인 그림이 나오지 않을까 싶은 생각이 듭니다. 예, 그리고 그 밑에 이제 전승우님께서 UWB 관련된 실제 해결 사례 같은 걸 이제 문의를 주셨는데요. 예, 이런 부분들은 저희도 이제 어떻게 보면은 저희 고객분들과 연관이 되거나 이런 경우가 있을 수 있어서 이런 부분들은 구체적인 사례나 어떤 솔루션에 대한 부분이 필요하시면 따로 저희가 자리를 마련을 해야 하는 게 좀 더 나을 것 같고요. 시간 관계상 아마 이 정도가 마지막이 될 것 같습니다. 이 마지막 좀 이유성님께서 질문해 주셨어요. UWB 모듈레이션에서 QPSK도 있나요? 라고 말씀해 주셨는데 어떻습니까?
UWB는 이제 BPSK 방식이나 그 다음에 펄스 포지션 모듈레이션 방식, 이 두 가지 방식을 주로 사용하고 있고요. 뭐 아직까지 QPSK 방식은 적용 규격에선 다루고 있지 않습니다.
그러면 이거는 사실 이동통신 쪽에서는 QPSK가 상당히 베이직한 부분이라고 생각할 수 있는데 뭐 3G 때부터 이미 사용을 해왔으니까요.
이 UWB는 아주 짧은 펄스를 사용하기 때문에 그 펄스 위주의 변조 방식만 다루고 있습니다.
예, 그래서 좀 상황이 다르다, 뭐 규격마다 특성들이 있기 때문에 예, 꼭 일률적으로 QPSK를 쓴다라고 얘기할 수는 없는 부분이겠네요. 예, 일단 뭐 처음에도 말씀드렸습니다만은 지금 오늘 시간이 좀 타이트하기 때문에 모든 질문에 저희가 여기서 현장에서 라이브로 다 답변드리기 조금 어려울 수 있다는 점을 먼저 다시 한번 양해를 구하고요. 뭐 그렇지만은 저희가 질문해 주신 내용들은 저희가 다 갈무리를 해서 추후에 다 회신을 드릴 수 있도록 그렇게 진행을 할 거기 때문에 이런 부분에서 좀 양해를 부탁을 드리도록 하겠습니다. 그럼 마지막으로 말씀드릴 부분은 이제 요 아래쪽에 보시면 이제 세미나 자료를 말씀해 주신 분이 계시는데요. 저희 뭐 아까도 오전에도 잠깐 말씀을 드렸었는데 저희 한 일주일 정도 사이로 관련된 링크라든지 이런 부분들 다시 보기까지 포함을 해서요. 이런 부분들 내용을 정리를 하려고 합니다. 그래서 이 부분들은 저희 쪽에서 오늘 참석하신 분들께는 따로 저희 쪽에서 말씀을 드릴 수 있도록 그렇게 기회를 마련하도록 하겠습니다. 네, 그래서 벌써 시간이 이제 마지막 세션이네요. 마지막 세션 오늘 내용은 이제 6G에 관련된 내용입니다. 그래서 제목은 뭐 보시는 것처럼 Path Toward 6G 테크놀로지 컨셉이라고 되어 있네요. 그래서 오늘 뭐 계속 말씀드렸던 내용이긴 합니다만 6G는 사실 정말 초기 단계예요. 그래서 정말 베이직한 얘기들을 하고 있는 상황이다. 뭐 이렇게 보실 수 있는 거고 규격이라든지 이런 얘기를 하기엔 좀 많이 이른 감이 있는 그런 상황이 될 것 같습니다. 그래서 저희 독일 본사에서 테크놀로지 매니저로 근무하고 계시는 타로 아이클러 씨의 6G에 관련된 내용으로 발표를 보시도록 하겠습니다.
Welcome to this technology seminar. My name is Taro Eichler. I'm technology manager for wireless communication, also covering photonics. And today I would like to talk about the path towards 6G, technology concepts, and the relevant aspects for test and measurement. Let's have a quick look, what topics we are going to cover today. I will start with an introduction about beyond 5G and 6G research areas, and then cover the properties applications of terahertz waves. This is one of the topics which are interesting and relevant for us. There are different ways to generate terahertz generation by electronic and photonic technologies, which I will cover. Optical wireless communication is one aspect, and finally I will talk about channel measurements in the high frequency region at 300 gigahertz. So for the future communication standard 6G, what could be possible applications? That's always one of the drivers, let's say, of new technologies. One aspect could be high definition augmented reality, extended reality. So this kind of combination of sensing with communication. Autonomous driving is already existing or is supported already by 5G, but this will be further extended because certain requirements are not yet fulfilled, such as very low latency. And the same is true also with industrial networks. Also here, even lower latencies than currently possible with 5G are necessary. Urban air mobility, that's another aspect, and sensing holograms. This is a picture, for example, taken with the QPS scan. It's a QPS. It's a scanner working at between 70 and 80 gigahertz. Remote healthcare already exists today, but will be further extended, of course, in the future. And digital twins, like combination of having the digital world and the physical world. So in 5G already all these applications, or some of these applications, existed as a kind of target, and there were kind of three pillars regarding requirements. One is enhanced mobile broadband. So video streaming is one aspect, one application where enhanced mobile broadband is necessary. Another area, for example, for the industrial applications is URLLC, ultra-reliable low-latency communication. Then you have for gaming, car-to-car communication, and so on. And another area is massive machine-type communication for example, meters for gas, home automation, and wearables. But for 6G, their further requirements will come and will become important, such as, of course, a further extension of the user data rates in order to allow these extended reality applications with very high definition video and so on. We mentioned almost zero latency, so very small latency to enable really industrial scenarios and also autonomous driving. Even lowering the energy consumption, the energy footprint, extending the battery lifetime up to 20 years. And then there's some aspects like universal connectivity, native AI, high precision positioning as well, and sensing, and all at the same time with very high availability with many nines. Let's have a quick look at the roadmap and time evolution of 6G. So currently we're in 2021. Fundamental research has already started. And applications are still a little bit in the future, but fundamental research has started. So in the upper part, you see the 6G timeline. In the middle part, you see the ITU, so the International Telecommunication Union timeline, and 3GPP. And it's expected, 6G will evolve over the next decade, or will be standardized over the next decade, and the plan is that it will become commercial probably by 2030. And the first step started already at the World Radio Conference 19 by allocation of additional spectrum for 5G, and also a first, frequency allocations have been done also for future standards. So at least candidates. And yeah, the next step is for our ITU that report on the technology concepts and future requirements will be finalized in 2022. And this is again the basis to look into more details at the World Radio Conference 23. So probably first demonstrator, for example, for terahertz communication could be or need to be realized until then to make or to pave the way to allocate frequency bands or to consider frequency bands for finally maybe making it available at the World Radio Conference in 2027. So that will be also the basis when potentially with release 22, the first 3GPP standardization will start. And this will be based by the requirements defined by the ITU. So what are the technology candidates for the next generation wireless communication? There are some technologies which are already known from 5G, which have been discussed there already. One of them is ultra-high speed channel coding. New waveforms have also been discussed already in 5G, multiple access schemes, ultra-massive MIMO. So massive MIMO was already part of 5G that will be further extended with higher frequencies. Of course, it will become even more massive, and full duplex communication already was discussed for 5G. Sending in both directions at the same frequency simultaneously. How to realize that was already a research area that we also realized. Then new network topologies like cell-free massive MIMO will be a topic. And then what we'll focus more on today is terahertz sensing and communication. So using higher frequencies, visible light communication, so optical technologies, photonic technologies, intelligent reflecting surfaces. There's a technology where you use metamaterials, so maybe very thin layers of artificially designed kind of structures which are on the order of the wavelength, and you can tune the amplitude and phase, and by this can have some kind of intelligent reflection in a certain area, for example, which you cannot reach by line of sight. Distributed processing is another area of research, and of course very important is AI and machine learning, for example for network optimization. Generally the network will become more complex, and in order to reduce the human human factor in the sense that the human has to optimize these networks, of course the machine learning factor has to come in, but also machine learning could be used, for example, to optimize or dynamically change the waveforms depending on the channel conditions. There are many ideas, but it will become an integral part of 6G. So in Germany also a lot of research activities have started, and just 1 month ago the so-called 6G hubs in Germany have been announced. So in total 250 million euro for 4 hubs in 4 years will be allocated. It's by the Federal Ministry of Education and Research. And one of them is from the Technical University of Munich together with Technical University of Dresden. So they will focus on 6G communication networks. So especially the human-machine collaboration aspect will be highlighted. New approaches for sustainability, security, resilience, latency. I think these are major factors in 6G. There is a 6G Research and Innovation Cluster, 6G RIC, which is headed by the Fraunhofer Heinrich Hertz Institute. They looking into open interfaces beyond technology boundaries, so extension of ORAN, AI by security, so AI and security by design, joint communication and sensing, and so on. Another is the Open 6G Hub, which is headed by the German Center for Artificial Intelligence and the Technical University of Kaiserslautern. They have similar topics again, intelligent networks, and the last one is 6GEM, Research Hub for Open, Efficient and Secure Mobile Systems. So yeah, it is by the cluster of RWTH Aachen and other universities and at areas. They have interesting test beds. One of them is autonomous driving test bed, logistics and robotics, and also smart hospital. So in the similar manner as in 5G, so the allocation of new spectrum will become very important in order to be able to allocate more bandwidth. For 5G already there has been extension of FR1 to FR2 in the millimeter wave range, where a lot of contiguous bandwidth has been available or is available. This will be further extended also to frequencies beyond 50 gigahertz. So there are already potential new 5G bands allocated, and for example FR2 has been defined up to 71 gigahertz. Then there's a 60 gigahertz unlicensed spectrum. And for 6G, the frequency band beyond 100 gigahertz will be very interesting. So one of them, that area, is the D band, where you have a lot of free spectrum still available. So that's one of the hot research area for sub-terahertz communication. Then the H band, some bands have already been considered by in WRC 19. And interestingly, there's also IEEE standard, which already is defined for 100 gigabit per second point-to-point links. In the spectral area between 250 and 320 gigahertz. So let's have a look at terahertz waves. Application of terahertz wave, well, there are a lot of applications which are possible. One area is joint communication and sensing. Already it was mentioned the fusion of communication and sensing, so radar, of course, radar capabilities in the sense of, for example, for gesture recognition or other positioning aspects will become important. This can be combined in, let's say, one device. Another area is spectroscopy. Well, this is kind of independent of communication, but it's an interesting area because in the frequency area of these terahertz waves, for example, lie molecular, the molecular spectra, rotational spectra, where you can, for example, distinguish between different types of molecules in the terahertz spectrum. So it's a kind of tracer or a fingerprint of certain materials. This could be used also for example, for scanning, for different applications in medical, but also for example, detecting explosives. And imaging, of course, is a own area which we are already covering with QPS 100. Here's an example of a three-dimensional picture. It's kind of tomography, which could be used in production lines as well. Now, for communication, what are the use cases in the terahertz frequency region? So one very straightforward application is backhaul and fronthaul links, point-to-point connections, but this could also be infrastructure in remote locations. And another area is intra-device communication. So, for example, chip-to-chip communication. You can also imagine that you have a vending machine where you, when you do the payment, simultaneously can do a very fast download of ultra high definition video content and other applications. And I think one interesting area is also wireless links in data centers. So as you know, the communication in data centers between memory and CPU could be a bottleneck, and that makes, let's say, the whole architecture very, very complex. And you could facilitate this design by allowing also to communicate wirelessly within these data centers. Very quickly, I mentioned already that in this terahertz or sub-terahertz frequency region, you have, of course, the molecular rotational spectra. Here shown, for example, for water as example, oxygen and also other molecules. But the attenuation by the atmosphere is not such a critical factor, because mostly anyway, one looks at the short distance communication, maybe up to 200 meters or maybe more. We'll show some examples later on. But anyway, still also there are some frequency bands, frequency windows for the Ka band, W band, and so on, which can be used where at least there are not these kind of absorption peaks from the atmosphere. But generally, this is not a real problem since anyway, for these high frequency bands, one looks at rather short range communication. Interesting is to look at what are the ways to generate terahertz radiation. So there are, let's have a quick look. What is the definition of terahertz radiation? So by IEEE and ITU, the terahertz spectrum starts from 300 gigahertz, so 0.3 terahertz, up to 3 terahertz. But often in publications, even just having 0.1 terahertz, so 100 gigahertz is considered already the terahertz radiation area. What different ways are there to generate terahertz radiation? So from our perspective, we usually having electronic sources. So we are probably using some kind of upconversion processes in order to create terahertz radiation coming from the lower end. But there are also ways to create terahertz radiation coming from the higher frequencies, for example, from the optical region, using lasers and doing down conversion by mixing two lasers and using the beat signal. And there's also a different way to directly generate terahertz radiation similar to a laser diode, but these are special quantum cascade lasers we will have a look at later on. But in the right top, you can see that, let's say, the energy equivalence. So 1 terahertz energy corresponds only to 49 Kelvin. So it's very low energy, and that's why it has certain difficulties to create that frequency compared, for example, to the optical frequencies. Very briefly, the upconversion process, that's our core technology. We have a demonstrator, for example, for the D band and products very soon. And for the different areas, so for the OTA, we have already products today. And here on the right top corner, you can see an example of a RPG, so radiometer physics. It's a company of Rohde & Schwarz, which already makes since years components for satellite communication, and for example here local oscillators also up to 1.1 terahertz. You know that there's the so-called terahertz gap, and why it is called terahertz gap is that if you look at this graph, which shows the output power versus frequency, if you look at the terahertz frequency region here, starting from 100 gigahertz up to 10 terahertz, then there's a sudden drop of the different ways to create terahertz radiation, sudden drop of power. And so it is difficult to create high power in that frequency area, and that's why it's called terahertz gap. But there are ways, and we are going now to look at the different ways how to generate terahertz radiation. But it is at the boundary between electronics and photonics, and so it has a kind of special, it's a special position. So looking at the electronic way to generate terahertz radiation, let's have a look quickly at the semiconductor situation. So as you probably know, the material properties of semiconductors for high frequency applications, there are different material areas or material groups which can be used. So one material area is a 3,5 semiconductor, for example, gallium nitride or indium phosphide, and there's a silicon world. So on the right side here, you see the radar graph of the different semiconductor areas. For example, if we take indium phosphide, it's in orange. It has the highest electron mobility and saturation velocity. You see here it is in the left corner. It's rather easy or to hit the highest frequencies. Then if you look at gallium nitride, it has still a very high electromobility, but the biggest advantage is that it has a very high breakdown voltage and a very good thermal conductivity, and is the perfect material to create power amplifiers for high frequencies. And then you have the area of silicon germanium, so in green, which still has a very good electromobility and is possible to generate high frequencies. But the biggest advantage is the combination or the potential possibility to combine it with CMOS for low-cost commercial applications. And if you look here at the overview of the state-of-the-art millimeter wave power amplifier. So here on the left graph, you see the different, or each data points represents a measurement from a publication for the different materials. You see here gallium nitride, silicon germanium in green, and so on. And you see that the data points, they are not equally distributed to certain frequencies, but they are bunched around certain frequency groups. And this is, of course, because of the driving applications. For example, you have 5G millimeter wave at 28 gigahertz and also 39 gigahertz. Then you have 60 gigahertz WIC. That's why there's a line around that area. And then you have also automotive radar, for example, at 77 gigahertz, and also E-band backhaul. Yeah, but still you see, if you look at the data points below, above 100 gigahertz, it's quite sparse. Yeah, so not so many data points. But the situation has changed. So this has been the situation until 2016. But if you look at the situation in the last 4 years, from 2016 to 2020, then you see above 100 gigahertz, a lot of more data points. A lot of has happened. And so there's really a lot of improvement, especially in the area of the D-band and also H-band, so up to 300 gigahertz, which is especially important for going towards 6G. So we already mentioned these kind of areas, but one of, let's say, the interesting areas for test and measurement is the D-band, of course. Yeah, D-band over-the-air measurement for sub-terahertz research. And since we have this trend going towards higher frequencies, and then in combination with communication and sensing, device under tests, which combine highly integrated active antenna systems for massive MIMO and sensing applications, you can only test over the air. Yeah, and we have these solutions, for example, the ATS 1000 in combination with additional test and measurement, which allows you to measure the amplitude and phase coherent, the response of the DOT in the frequency range from 110 to 170 gigahertz. So that's one area where the test and measurement range is extended. So let me quickly talk about photonics for wireless communication. So the different areas, you see here on the left side, one area where you have integrated photonics and waveguides, and in the future probably you can also use this for computing. So you have integrated photonic circuits, but there's a lot of development in this area. And also for 6G, there are photonic technology candidates, and one of them is, for example, visible light communication, which is not new, which has been developed also already in the last years, where you modulate commercial LEDs. And the advantage, it's very cost efficient because you have already infrastructure which allows easy integration. And there are other extensions I will talk about later on. And the other application area of photonics is generating terahertz radiation via optoelectronics. So optical wireless communication, or VLC, visible light communication, or also Li-Fi, I mentioned already, is not new. It has been developed also using, for the higher layers, for example, power line communication standards, and currently it's being extended. Here mentioned is the standard, it's the ITU-T standard G9991 or GVLC. And it will be extended also in the future that it to use Wi-Fi as a higher layers, because the Wi-Fi chipset, of course, is it has a much bigger market, and probably is more promising, let's say, to have a commercial product. So there are already, as you see in this picture, commercial prototypes available, but honestly, it has not picked up yet. And here on the right side, you see a very simple graph, or where you have this kind of transmitter, receiver, and in between the free space channel, you can even increase your data throughput by using different colors, and you can then, as in optical fiber, separate that later on by filters and to increase your data rate. But currently, still the data rate is limited by the LEDs. So if you use commercial LEDs, the maximum bandwidth is about 200 megahertz, and that's not yet something for 6G. So that needs to be improved. But one possibility to improve the bandwidth is to use these vertical cavity self-emitting lasers, or arrays of that, because these allow much higher modulation bandwidths in the gigahertz range. And just again, one of the advantages why one could use visible light communication is that in the optical region, of course, there is a very, very large frequency bands available, which are license free and allow then high data rates. So I mentioned before the different ways to generate terahertz frequencies or terahertz radiation, and one of them is to use direct terahertz generation by quantum cascade laser. You may wonder, why cannot I use a normal diode laser, as you know from optical frequencies or infrared frequencies? But the problem is that with these terahertz photon energies, they are 100 to 1,000 times smaller than visible photons. So there are no materials which have such a small band gap. On the left side, you see the standard semiconductor approach, where you have a conduction band, so the electrons, and the valence band, so the holes, and you have recombination, and then the photon is emitted. But that is not possible for these very low energies in the terahertz region. So what is done there, that you design by a quantum well, by designing a special kind of quantum well, by multi-layer structures, and you have within the conduction bands energy states, so the excited and ground state are within the conduction band, and then you can design your special terahertz photon energy, which is shown also on the next slide. So here in this picture you see on the top right this kind of special designed multi-layer structure. So you have here the active region and injector region, and it's a periodic structure. And so what happens here is that you start with the electron tunneling from the neighboring injector region. Then you have this inter-subband transition. So within the conduction band, then you have the emission of a photon, then electron tunnels to the next active region, and the same process happens again. So you have stimulated emission, and this is a cascaded process. That's why it's called a quantum cascade laser. And it's very neat, because you can kind of tune your energy difference between the excited and ground state, and thus the photon energy, by the design of the multi-layer structure. The disadvantage of this is that you have a the energy is very low, and there are also interactions with phonons. You need to cool the structure. Yeah, you need to cool it, but there are research activities to also allow this at higher frequencies. At higher temperatures, even coming to the area of minus 23 degrees. I think this was a publication from this year, and which you can reach with normal Peltier cooling and not liquid nitrogen, something like that. Okay, so let me quickly talk about another alternative way to generate terahertz radiation. So this is a down conversion process by using optoelectronics. So what happens here that you have two lasers at different frequencies, slightly detunes, and the difference frequencies is actually then the terahertz frequencies. So both lasers you mix on a photodiode, and then the beat frequency is at the terahertz region, and then directly on this photodiode connected to an antenna, and then propagates to the receiver. This is just a picture which shows optically how you can make visible this kind of terahertz radiation by fluorescence. But it is not related to the direct generation process. And on the right side here in the inset, you see how it is done, like the schematic. You have a channel generator, so the arbitrary waveform generator. Then you have here one of these is a local oscillator. Then you have the data modulation. You can also have different frequencies and combine this with the local oscillator, and then again do the same thing on the receiver side. It actually works even over large distances. So here on the right side you see a transmission link. This was done by Professor Ducornon in France, in Lille. Here you have a 300 gigahertz live link. So a live video link was transmitted over a distance of 850 meters. The data rate was not yet that high, but it was a high definition video. So a few tens of a megabit per second. But in the lab already what has been demonstrated is also even up to 100 gigabit per second at 320 gigahertz. This is also now being extended to larger distances outdoors as a next step. So in the last part, let me talk a little bit about channel measurements. So always when a new standard emerges, and this was the same like in 5G, that the first step is to generate channel models, because that's the basis of designing a new physical layer. Because the channel models are needed for system performance evaluation. Then you have the link and system level simulations for the new physical layer. You decide how the pilots are distributed in time and frequency and so on. And then these channel models are input or are defined by 3GPP. Also later on, they are standardized for comparison of the simulation results. And that's what is done now also for 6G. So this is, you have a transmitter, receiver, this is kind of the environment, but you also have reflection, diffraction, scattering, and so on by the environment. What we do is time domain channel sounding. So you have a very t equals 0, a transmitter signal, a very short transmitter signal, and then we measure the channel impulse response. And we see not only the line of sight, but also the reflected signals from the different environment, the obstacles environment, and measure the time delay. So this gives a very nice picture of the channel, and this can be then used to define the channel model. From the test and measurement perspective, how does it look like? So on the left side, we have the transmitter. On the right side, we have the receiver. We have the, in this case, it's SMW, vector signal generator. it's then the IF is connected to a terahertz transceiver. In this case, it's from the EIF, Institute for Applied Solid State Physics, and the HHI, the Heinrich Hertz Institute. We have an input, another local oscillator, and a very precise time reference, which, because we want to calibrate the zero time, because we're talking about nanoseconds here in the delay. Then you have the radio channel and kind of the symmetric setup on the receiver side. We did measurements in the factory, so this was for 5G together with, in this case, NT-Docomo and the Fraunhofer HHI. We provided measurement data and from our factories, which were done at different frequencies, 3.7, 28, and 67 gigahertz. We provided this as input for the industrial IoT channel models to 3GPP. And we have also here two publications you can have a look at. One is covering the industrial measurements and the other is covering the terahertz channel sounding. This is another example done in our factory. You see kind of the typical indoor signature where you have a very, of course, a very strong line of sight, but then a very broad shoulder with many reflections, in this case about at 28 gigahertz line of sight. But you also see we also measure the time of the direction of arrival. And you see below, it's kind of the waterfall diagram where you have the line of sight, again, moving farther away from the transmitter, but also you have the back reflection from the wall, which comes closer the farther you go away from the transmitter. So this is an example of the channel impulse response at 300 gigahertz. This was an indoor measurement. You see again the direct path, the line of sight on the, but then you have a broad shoulder of multipath components, also indoor. Let's have a quick look at the line of sight. The line of sight is around at a time delay of around maybe 12 nanoseconds, which corresponds around to the distance of 4 meters, which actually was the situation in the indoor environment. And here on the left side is a picture also of the transmitter we use from the Institute for Applied Solid State Physics. So the next step we did already, and just last week we had measurements on our Munich campus. You see here one scenario we covered. So in the upper picture is a TX view, the transmitter. So directed in a kind of, it's a kind of between two buildings, but a kind of street canyon scenario. And we can cover quite large distances. And then in the lower picture, you see the receiver on a kind of cart, which you can pull to measure at many different distances. So of course we measured the path loss, but not only the path loss, but also the direction of arrival. So to see at certain points the reflections from the buildings and so on to get a real good picture of the environment. And we did this last week in the D-band at 150 gigahertz. And we will continue this also for the 300 gigahertz band. So outdoor is one scenario, but also indoor, we do it in one of the buildings. We have a large atrium, which is maybe similar to a kind of shopping mall environment. And the first measurements we did, this was not at our RNS campus, but this was done in the HHI. We published already, you can see here in this publication from the ICC workshop. And here on the right side, you see some examples where you have different time delays at different distances also and at different angles. And you see behavior with multipath as well. Okay, so that I will summarize now my presentation. So I talked about the future of mobile 6G. Of course, there will be many new application scenarios, connected vehicles, robots and drones, with a lot of digital information which has to be exchanged between the different entities. and we are already on the way to pioneering these technologies, what can be used for sensing and communication. But it's not only to have higher data rates and lower latencies, but also it will be important to reduce the energy footprint, also very secure communication, because our whole infrastructure will depend on this. It will be important then we have scalability, but also affordability for to make it accessible, actually not only for let's say the most developed countries, but also to the whole world. And with this, I would like to conclude my presentation and thank you for your attention. So thank you.
네, 지금까지 마지막 세션이었었죠. 패스트워드 6G 테크놀로지 컨셉에 대해서 저희 본사, 독일 본사의 타로 아이클러시가 발표하는 내용을 들으셨습니다. 예, 마지막 세션 정리를 위해서 저희 로데슈바르즈 코리아의 그 기술 지원을 맡고 있는 유승근 매니저님 함께 자리해 주셨습니다. 인사하시죠.
네, 안녕하십니까, 유승근입니다. 반갑습니다.
예, 그래서 지금 쭉 오늘 그 7번째 세션까지 마무리를 했네요. 한번 간단하게 내용 정리를 좀 부탁드릴 수 있을까요?
네, 금일 마지막 세션에는 현재 이제 상용화되어 있는 5G랑 이 5G가 어떻게 발전해 나가는지, 그리고 이 최종적으로 이 발전해 나가는 5G가 6G에 어떻게 이르는지에 대한 기술적인 부분과 그리고 영역에 대해서 다뤘고요. 그 영역적인 부분은 새롭게 이제 추가되는 영역, 센싱을 통한 고화질 증강현실, 그리고 실질적으로 현재 5G에서 언급되고 있는 오토모티브 자율주행, 그리고 인더스트리 분야가 앞으로 6G에서 또 어떻게 발전될 건지에 대한 부분도 언급이 있었습니다. 그리고 이 어플리케이션을 가능케 하는 기술들에 대한 언급들도 있었는데요. 기존 5G, 4G에서 많이 저희가 다뤘던 하이스피드 채널 코딩, 그리고 풀 두플렉싱 커뮤니케이션 등등등이 있었는데, 결론적으로는 이 부분들에 대한 설명보다는 6G에서 새롭게 언급되고 있는 테라헤르츠 커뮤니케이션, 그리고 비주얼 라이팅 커뮤니케이션을 위주로 저희가 우선 오늘은 설명을 드렸고, 그리고 마지막으로 이러한 6G를 이루기 위해서는 보통 이제 채널 에스티메이션을 해야 되는데, 이 채널 에스티메이션을 하기 위한 채널 사운딩 테스트를 어떻게 하는지에 대한 언급이 있었습니다. 그리고 이쪽 부분에서 지금 오늘 진행한 본사 담당자가 채널 사운딩 쪽 어플리케이션 담당자다 보니 요 위주로 설명을 드렸는데, 로데슈바르즈는 당연히 6G 테스트를 하기 위한 다른 장비들과 내용들을 이미 준비를 하고 있고, 만약에 그런 부분들에 대해서 궁금하신 부분들이 있으면 저희 쪽으로 따로 연락을 주시면 저희가 솔루션을 보여드리고 제공도 가능한 수준에 이르고 있습니다.
예, 간단하게 정리 감사합니다. 오늘 뭐 내용을 들으셨겠지만 사실 이 마지막 세션 같은 경우 저도 그 동영상들을 이제 감수라고 리뷰를 하면서 좀 많이 어렵더라고요. 뭐 반도체 얘기도 나오고 또 뭐 이런 부분도 어떻게 보면 또 전문적인 분야이기도 하기 때문에 이런 부분들이 이제 어떤 식으로 앞으로 발전해 나갈 것이냐, 이런 면에서 좀 전망이라고 해야 될까요? 현재 현황 진행되고 있는 내용들을 잠깐 보신 걸로 생각하시면 될 것 같고요. 특히 이 6G 같은 경우에는 현재 뭐 정말 초기 단계입니다. 그래서 앞으로 또 어떻게 변화가 있을지, 어디까지 할 수 있을 것인지, 이런 부분이 정말 흥미롭게 보여지는 그런 부분이 아닐까 싶습니다. 특히 뭐 테라헤르츠 같은 거 아까도 말씀해 주셨습니다만은 현재는 뭐 사실 매우 어려운 이야기인 것처럼 보이는 부분이지만 또 어떻게 이걸 또 가능케 하는 기술이 나올 것인지, 이런 부분도 흥미롭게 우리가 볼 수 있는 부분이 아닐까 싶습니다. 예, 그래서 지금 뭐 오늘 오전 10시부터 시작해서 오늘 지금 벌써 5시가 넘었네요. 지금 뭐 시간상으로 봤을 때 거의 한 7시간가량을 이렇게 저희가 세미나를 진행했습니다. 뭐 저희도 사실 진행하는 입장에서 이 7시간 동안 세미나를 한다는 게 쉽진 않은 부분이었습니다만은 오늘 이렇게 참석해 주시고 지금 이렇게 계속 코멘트 올려주시고 질문해 주신, 참석해 주신 여러분들께서 함께 이렇게 봐주셨기 때문에 또 저희 또 힘을 얻어서 이렇게 끝까지 진행할 수 있었던 게 아닌가 싶습니다. 뭐 다른 부분들은 말씀드리기가 좀 어렵습니다만은 뭐 어쨌든 간에 저희 같은 경우에는 계속 국내에서 독일 로데슈바르즈 본사의 한국 지사로서 여러분 곁에서 함께 하고 있는 부분이 있기 때문에 필요하신 부분들이나 궁금하신 부분들은 언제든 말씀해 주시면 좋을 것 같고요. 유승근 매니저도 아까 말씀드렸습니다만은 필요하신 부분이 있으시면 저희 쪽에서 최대한 그 내용들을 같이 보실 수 있고 같이 발전할 수 있도록 그렇게 준비를 할 수 있을 것 같습니다. 예, 참고로 말씀드리면 아까 한 40분경에 보셨던 것처럼 설문이 나왔었어요. 그래서 여러분들 꼭 잊지 마시고 설문 입력을 해주시면은 또 귀중한 정보로 또 저희가 함께 또 발전해 나갈 수 있는 부분을 찾을 수 있을 것 같고요. 네, 그래서 다시 한번 말씀드립니다만은 오늘 긴 시간 정말 고생 많으셨습니다. 저희 로데슈바르즈코리아는 다시 한번 여러분께 감사를 드리고 앞으로도 여러분께 가장 정확한 파트너로서 가장 신뢰할 수 있는 파트너로서 남도록 노력하겠습니다. 오늘 정말 긴 시간 동안 고생하셨습니다. 수고하셨습니다.
IT 전문 방송 토크IT에서 테크 분야별로 짧고 진한 시리즈 영상들을 편하게 골라서 보실 수 있습니다. 구글이나 네이버에서 한글로 토크IT 치시거나 토크IT.tv 사이트로 오시면 됩니다.